Okay, I'm gonna do 100 more integrals since the last one actually turned out to be pretty fun. So let's start off with number 1, but for 100 more integrals. Okay, so number 1, we have the integral of, open parentheses, x to the 2023 plus x all to the 2021 dx. Okay, what do we do? Expand it out manually? No. There's an x here and at least one x here, right? So let's factor out an x and then distribute the 2021 onto it since the x after being factored out, it's going to be multiplied in. So we factor out an x and then we distribute the 2021. And we still have this, but then we factor out an x. So we have x to the 2022 plus 1 and then to the 2021 dx. Okay, and for this one, what we do is, you notice that we can make a substitution, whatever's in here, right? X to the 2022, well, x to the 2021 is the derivative of x to the 2022 to some extent. So we can make a substitution. Let u equal to x to the 2022 plus 1. And du would be equal to, move this down, and then subtract 1 from the power, multiply by the derivative of the inside. Then notice we have x to 2021 dx here. However, we don't have the 2022. We're going to divide it on both sides. 1 over 2022 du is equal to x to the 1 dx. Okay, and then what we do is we can equal sign and then integral. 1 over 2022 is multiplicative, so I'm going to move it outside. Inside, this is our differential, so we're left with this, and the inside is just u. So we have u to the 2021, and then don't forget our differential. Okay, and then we have this guy being multiplied in from the outside. And then reverse power rule, divide by the power plus 1. So we got 1 over 2022, and then just add 1 to the power, right? Yeah. Okay, and then down here, what we can do now is multiply the 2 by squaring it, since it looks nice, it looks better written this way. And then we have u, which is x to the 2022 plus 1. So I'm going to put that down. And then all to the 2022nd power. Yeah, okay. Add c, and that's it. This is a pretty satisfying result to start off, well, the next 100. Okay, that's number 1. I'm going to open up the window really quickly. It's raining. Well, it looks like it's about to rain outside. I'm going to switch off this light. I think it might be. There we go. All right, that's number 1. Number 2, we're moving straight into some trig stuff. Number 2, we've got integral of sine of 3x over sine x. Now, there is a sine triple angle identity, so let's derive that, right? Because I don't think most of you would be able to tell me what it is just off the top of your head. So, sine of 3x, we can break this in 2. Sine of 2x plus 2, right? And this way we'd be able to use the angle addition formula for sine. All right, so the angle addition formula is, we've got sine of the first, right? And then cosine of the second. Add cosine of the first. And then sine of the second. Okay. From here, what we can do is we can expand both of these out with the double angle identities. Yeah. I think this one is just 2 sine x cosine x. And then, of course, we can square the cosine x because there's one being multiplied in here. Over here, cosine of 2x is, well, if we want to do a shortcut, then there's other ways we can express the cosine double angle formulas, but I'm going to derive that too. So famously, cosine of 2x is this. However, if you took this cosine squared and then turn it into a 1 minus sine squared, then this becomes a 1 minus 2 sine squared. So obviously, cosine of 2x is therefore equal to 1 minus 2 sine squared x times sine x. Alright, and everything's almost in terms of sine, and then we're going to be able to like multiply everything out and reduce just this. Let's replace that real quick. So you got 2 sine x times 1 minus sine squared x plus, and I'm going to keep the rest the same. Let's expand out on the next step. Alright, next step, distribute the 2 sine. You get 2 sine into the 1, right? And then minus 2 times sine, but it's cubed. Alright, next term we have 1 times sine, which is just sine, minus 2 sine squared times sine, which is minus 2 sine cubed. Combine like terms, got sine and sine. 2 plus 1 is 3. And then we have the sine cubed, negative 2 minus 2 is negative 4. Sine cubed. So therefore, sine of 3x is equal to this. All right. Now what we can do is we can replace it back in there. So we've got this is equal to the integral of the top is 3 sine x minus 4 sine cubed x. Bottom is still sine x. Notice since everything is in terms of sine, we are now able to reduce this quite nicely because this sine cancels with this sine, right? And then this becomes 2, the bottom one cancels. And we're, yeah. Okay, so this becomes the integral of 3 in the first term. And I'm going to break up the integral, right? And the second one right here is integral, well, let's bring the negative 4 out, sorry. Negative 4 times integral of sine squared. And famously, to do sine or cosine squared, we need to use the cosine double angle. And, well, I mean, if we want to derive that too, because we've got this right here, we know that this is equal to cosine of 2x, right? We want to isolate what sine squared is. We just add this on both sides, subtract this. Actually, what we can do is turn this into sine squared first, and then, we'll see from there. So, cosine squared is 1 minus sine squared, right? Yeah. Actually, you know what? We don't need to work from here. We can work from here, because if we know that this is equal to cos 2x, all we need to do is isolate sine squared. To do that, we add 2 sine squared on both sides and then subtract cosine of 2x. So we get that 2 sine squared is equal to, and then subtracting cosine of 2x, you get 1 minus cosine of 2x. And then now to isolate sine squared, all you need to do is divide by 2. So you get sine squared is equal to 1 minus cosine of 2x all over 2. All right. And now we know why that is, because of the cosine double angle. You can derive the cosine double angle however you'd like to. Anyways, we're going to replace this with that. Notice how there's a 2, and that's a constant multiple. Also, right here, the integral of 3, we can just convert that to a 3x, yeah? There's a constant multiple of 1/2. I'm going to bring that outside. 4 times 1/2 is negative 2. And then on the inside, we just replace it with whatever's in the numerator. We got 1 minus cosine of 2x dx. Okay, and then now we're able to integrate. Integral of 1 in the x world is just x. And don't forget that we have to distribute the negative 2, so we get negative 2x. Negative, negative makes a positive first, right? Cosine, well, on the inside we have 2 times x, so we need to divide by 2 when we integrate. Dividing by 2 and this 2 cancels, so there's no more coefficient, it's just a 1. And now we focus on the function part. This is positive cosine because negative, we already canceled it out. Integral of positive cosine is positive sine, and argument remains the same, so we get sine of 2x. Alright, and then finally, one last simplification. 3x minus 2x equals x plus sine 2x. Add c. Yeah, there we go. Very cool. Okay. So immediately we got into some, pre-calculus, crap. Especially trig-focused pre-calculus. Okay, and number 3 we got identity, I guess. Well, not necessarily an identity. I'll show you. We have a formula that we need to derive. We have integral of 1 over root of a squared minus x squared dx. Okay, for this right here, this is a trig subcase, right? Notice that we're working with x, not a, and this is difference of squares, and x is in the second term. So we use sine or cosine, and our a value, of course, is just a, since this is expressed as a squared instead of just a number. Square root of a squared, yeah, it's still a. So let's make a trig sub. I'm going to use sine today. You can use cosine, however your result is going to be slightly different, but the fundamental idea is going to be the same. Alright, let x equal to a sine theta, right? And that way, you also need to find the differential. Dx is equal to a cosine theta d theta. Okay, now what you can do is dx, 1 times dx is just a cosine theta d theta, right? On the bottom, root of a squared, and then now take this, square it, and subtract it off. You get 8 squared sine squared theta. Okay, and then next, what we can do is a squared factor it out. Root of a squared is just normal a. So there's an a on the bottom now. And I'm going to write down the top. Notice that on the bottom, you still have a 1 minus sine squared inside of the root. And 1 minus sine squared is cosine squared, and root of cosine squared is just normal cosine. So the bottom becomes a cosine theta. Notice that this cancels with this, so you're just left integrating d theta, which gives you theta. And to solve for theta, divide by a on both sides. Right, x over a is equal to sine theta. And then finally, take inverse sine on both sides, provided you're on the right domain, then this works. Therefore, the final result, that integral, antiderivative is inverse sine of x over a. And add c, and you're done. Alright, that's number 3. Alright. Number 4, we have another pretty difficult one. Maybe I should stop saying this is difficult considering the standard we were working at previously. Previously, we tried to, we were given e to the natural log of 2. E to the x times natural log of 2 to integrate. So I'm not sure if that was considered a standard or not. Hopefully not. Bottom we have 1 plus natural log of x. But this one it's pretty tricky. Alright, let's think about it for a second. All of the x's here are inside of a natural log. So it would be nice if we can make a substitution. U is equal to natural log, so we're just working with a pure variable instead of a variable nested inside of a natural log. But it's very difficult to make that substitution because we don't have anything to cancel our new differential out with. So let's give it 1. If we were to let u equal to natural log of x, then we'd want something to cancel, and that would be an x in the denominator, right? Because 1 over x dx would just be our new, 1 over x dx would be our new differential. So we can spawn an x in the denominator by multiplying an x both on the top and the bottom, and this introduces, well, I guess you can argue that it introduces domain problems, but notice that it's only undefined at 0, and this is also undefined at 0, so we're fine. Alright, so now fill in the rest of the integral. Alright, so that's step 1 that you have to recognize. Step 2, you have to recognize, well, now we have an x here. How the hell do we do this? Well, you can use integration by parts, but the tricky part is recognizing what to integrate specifically. And here's a hint. You don't want to integrate the entire thing, not including this, right? Notice that differentiating x ln x gives you something pretty nice, right? And integrating ln x over x times 1 plus, if you do that, it's going to give you something that's very difficult to work with. So if I were you, I would differentiate the top and integrate the bottom instead of integrating this whole block of natural logs. All right, so let's give that a shot. Differentiate the top, x ln x, subtract off. Derivative of x is 1, derivative of and then keep the natural log of x. Derivative of natural log of x is x, well, 1 over x, and then multiply by the x, and we just get 1. So this is ln x plus 1. All right, and then integration, sorry. We want the fraction, we want to integrate this fraction, 1 over x times 1 plus ln x all squared. All right. For this one, use substitution, let u equal to the inside, 1 over x to the outside, so you're integrating 1 over u squared. Integrating 1 over u squared gives you negative 1 over u, and we set u to be the inside earlier, remember, so it's just 1 over natural log of x plus 1, or 1 plus natural log of x. I'm going to write it the latter way. So negative 1 over 1, well, ln x plus 1. Okay, now multiply the diagonals and integrate the rows. And what you notice is that even though there's natural logs in both, and you're kind of difficult to integrate a natural log, they cancel. Very nice. Integral. Well, sorry, no, equal to, before we put down the integral, we gotta write this down. So the negative out front, and let's put the x ln x in the top, over ln x plus 1. There we go. And then our second term, negative makes a positive. Integral of this times that, which just gives you 1 because they cancel, and that means you're just integrating dx, which gives you x. So this all in all is negative x ln x over ln x plus 1 plus x plus c. Yeah. All right. So that's number 4. Pretty basic so far, right? Well, basic as in nothing non-elementary, nothing with, weird integration techniques. Yeah. Next we have question 5, and we've actually done this one before, I'm pretty sure, in the previous one. We have x cubed e to the x squared, and I'm not sure about how Black Pen Red Pen did this in his video. He might have used a different method, but yeah, don't use di. Notice you can't integrate that, right? Yeah, so let's just use the u substitution, since this is just the exponential function, and in the argument we have an x squared, and here this is x to an odd power, so we're always going to be able to pull out a bunch of x squares and then just a normal x to be our differential. Let x squared equal to u 2x dx is equal to du. And notice how we only have an x dx if you just make this x squared times x, right? So we have to isolate the x dx, divide 2 on both sides, x dx is equal to 1/2 du. Integral, and this is multiplicative, 1/2 is multiplicative. Let's bring it, well, you know what, fuck it, let's keep it on the inside. So 1/2, right? We took out one of the x's to be our differential. We're left with an x squared, and x squared is just u. Then we have our exponential function, e to the x squared. Of course, x squared is just u, so e to the u, and du. Now, this is pretty simple, since this is a case of a polynomial times an exponential, and we're integrating, so we just use integration by parts. You would differentiate the polynomial, 1/2 u, this goes to 1/2, and it becomes 0. Integrating e to the u, it stays e to the u. Multiply, don't integrate, goes to 0. Alright, now, 1/2 u, e to the u is our first diagonal, minus 1/2 e to the u is our second diagonal. And all that's left to do now is replace all the u's with x squares. So we get 1/2 x squared e to the x squared minus 1/2 e to the u, which is x squared. Alright, and add c. Feel free to treat the e to the x squared. Feel free to factor out an e to the x squared and 1/2 from both of these to get, e to the 1/2 e to the x squared times like, x squared plus 1 or something like that. But, yeah, that's number 5. Number 6, I need to remember how to do, because if I'm being honest right now, I don't remember if I know, but I have a gut feeling as to how to do this. Number 6 looks weird. We have 1 plus root of 1 plus 1 over x. Don't be too intimidated. No, don't make the substitution. It looks tempting, don't do it. I mean, you could. What happens if you do? Let the inside be equal to u. Your differential would just be negative 1 over x. Yeah, I don't think that would be pretty. Actually, maybe it would be. However, I think the way to do it is combine the fractions on the inside. And to do that, make this 1 an x over x, and then you just combine the fractions. So you get x plus 1 over x dx. And then let's just rewrite this by splitting the radical. Okay, and now what I think you can do, you might be able to make a substitution. I'm going to give that a shot. Let u equal to, which one should we use? I mean, it doesn't matter, does it? So, root x, right? Yeah, I mean, so first of all, let's solve for what the other guy would be. Let's square both sides, u squared. Actually, is it a better idea to use the top or the bottom? Well, let's try the bottom first, and then if it doesn't work, we'll try with the top. This is real problem solving skills. No, I think this would work, right? And then u squared plus 1 is equal to x plus 1. And then if you want to take the square root of u squared plus 1 is equal to root of x plus 1, which is the obvious equivalent form we're going for. And actually, it didn't need to be that difficult, but because you could have just recognized that the x in here is just the square of u, right? All right, well, we'll see how this works out for us. Don't forget, we need to find our differential. Well, u squared is equal to x. We can start from here. Simply differentiate both sides, 2u du, that gives you dx. All right. Yeah. So in here, what do you get? Integral of. So let's move the 2 outside. the u and the u is multiplied in on top. That cancels with this u on the bottom, so we're just left with this times our du. And this is expressed as this. So we just have this, yeah? And then our du. From here, there's definitely an easier way to do this than what I tried to, but this is completely improvised once again, so let's try a trick. So let tangent, because this is on the squares, equal to u, and then differentiating both sides, d-tangent, no, sorry, that's not, secant squared theta d theta is our du. Alright, and then what we get is integral. Plug a tangent into there, tangent squared plus 1 is secant squared, root of secant squared is just secant. Multiply that by our differential, you get secant cubed, which I'm pretty sure, well, in the previous 100 integrals we established, this should be a standard integral. I think most people would know this. If you've done integration, this is equal to 1/2 secant theta tangent theta plus 1/2 natural log of absolute value of secant theta plus tangent theta. We know what tangent theta is, now just find secant theta. And okay, this goes back to the trig sub we made down here. So let's let this angle be theta. Tangent of theta is opposite over adjacent, and that's also u over 1, right? Oh, and note there's a right angle there. This top right here would just be the square root of the sums of the squares, of the sum of the squares of each of the legs, right? Because it's hypotenuse. Right, so we were, secant is this over that, so secant is just root of u squared plus 1. Yeah. Okay, so now we know that secant is that, and tangent we already have is just being simply u itself. So we got 1/2. Tangent is u, secant is root of u squared plus 1. Inside of our natural log right here, this is u plus root of u squared plus 1, which if you took a look at the graph is always positive. So I'm just going to write parentheses, u, and then plus u squared plus 1, right? I changed the order of addition. Don't let that confuse you. Secant is here, and then the tangent is represented here. Final step, we have to go back to the x world. Notice we know what both u and this whole root in of itself is. We solve for it. So, finally we have 1/2. U is root x. And then right out here, this one is root of x plus 1. Add 1/2 natural log of u is root x, and then this root of u squared plus 1 is root of x plus 1. Yeah, alright, and I think that's it. Let me check my answer. That looks right. Yep, okay, I'm gonna just assume that is right. I have, yeah, okay. Add C and that's it. And because the 100 extreme integrals, the one that we're doing right now, is a little bit more difficult than our other one, I have an answer key pulled up with all the answers that I've done a while ago that I took pictures of. But yeah, that's it for number 6. Oh god, okay. Number 7 is a trig one, and it doesn't look the most fun. Alright, so yeah. 7 integral 2 secant x over, and I think it's sine x plus cosine x. I'm pretty sure if you multiply, well, if you divide both the top and the bottom by a cosine, right, that's equivalent to multiplying a secant on top, so this becomes secant squared. And then on the bottom, if you divide everything by cosine, then sine over cosine is tangent, and then cosine over cosine is 1. So if you manage to find that step, then you get yourself a very, very easy substitution. Let u equal to tangent x plus 1. Therefore, du would equal the top, secant squared x dx. Okay, so now the 2 stays, we have a du, and the bottom is u. Notice the 2, the integral is linear, and any integral is linear, so you can bring the 2 outside. Du over u is natural log of u, so 2 stays outside, and then a natural log of u, and the absolute value of u. U is tangent x plus 1, so let's just place that right back in there. And this one was relatively easy. Box it. However, not so easy is number 8, and number 8 almost looks the same. However, instead of secant, we've got sine. So this is integral of 2 sine x over sine x plus cosine x dx. Alright. How would you do this? So I think the first step, you could still divide everything by a cosine. You get tangent. Alright. And then, well, yeah, let's try that, and then I'll demonstrate what goes on afterwards. So dividing everything by cosine, here you would get, let's bring the 2 outside, just so it's cleaner. Sine over cosine is tangent. And then on the bottom you have sine over cosine is tangent once again, and then cosine over cosine is 1. Don't forget the dx. Alright, from here, what you can do is, if you think about it, if you let u equal to tangent x, then you can square u, get tangent squared, and then add 1 to both sides to get a very nice expression for your differential, which is secant squared, in terms of u, right? So let's give that a shot. And I'm telling you that if you do this any other way, it might work, it might not, but I would advise doing it this way. Maybe there's another solution, but okay, so let u equal to tangent, right? And this means du would equal to secant squared x dx. And we're trying to find a way to represent secant squared x in terms of u. So let's try to find some way to do it. And first step is to square both sides. You get u squared is equal to tangent squared. And then adding 1 to both sides, the tangent squared, add 1, that becomes secant squared. So there you go. You found your equivalent. Therefore, du is equal to u squared plus 1 dx. And then divide it on both sides. You get that. And this is kind of chaotic, but 1 over u squared plus 1 is equal to, times du, right? Because there's still a du on that side, keep in mind. And divide it out the u squared plus 1, you're left with the dx. Okay. Yeah. Let's do this. Okay, 2 stays outside. Top you have 1 over, not 1, u, because there's a tangent, over u plus 1, and then you have to multiply in your differential, which is 1 over u squared plus 1, du. And now my impression is that I think you should be able to do partial fraction decomposition, because this is a rational expression. You have u plus 1 times u squared plus 1. On top, you just have a u, and that's a lower degree. So yeah, let's give that a shot. You want u over, and in this case, I'm going to drag the 2 inside. So it's going to be here. So I'm also going to do that here. Right. Okay, you want u over u plus 1, u squared plus 1. And you can't reduce these all down to linear terms because this is already an irreducible quadratic. You want this to be equal to, first fraction is just this first factor. And this one just can just have a constant numerator because the denominator is linear. Second one needs a linear numerator, so we get bu plus c over this because it's quadratic. Right, now multiply the least common denominator on both sides. Right, so this implies that u is equal to a times u plus 1 cancel, you have a u squared plus 1, and then for the bu plus c, the u squared plus 1 and the u squared plus 1 cancel, you're left with the normal u plus 1. Alright, now expand out the right hand side. You get a u squared plus a, that's the first term. Bu times u is bu squared. Bu times 1 is bu. C times u is cu. And then c times 1 is c. Alright. And then here, what we can do is group them by the term degree. So we're grouping the quadratics together. There's an a and there's a b. I'm not going to go over how to do partial fractions again. There's 2 linears. There's a b and a c. And then we have 2 constants, an a and a c. Okay, there we go. Now notice how if we draw in this implication symbol, all of this is equal to just u by itself. There's no constant, there's no quadratic. There's just this linear term in the middle. So therefore, this coefficient must be 0, this coefficient must be 1 because the coefficient here is also 1, and this must equal to 0 as well. So let's set up a list of conditions. A plus b must equal to 0, right? This comes from the quadratic coefficients. B plus c must equal to 1, and this comes from 1 times u being equal to b plus c times u on both sides. Then finally, a plus b must equal to 0 because there is no constant on the left-hand side. All right. From here, what we can do is we can solve this system of equations. Add these two, subtract this from that. So you get b minus a is equal to 1 minus 0. I'm going to replace that with blank, I guess. 1 minus 0 is just 1, all right? And then add this and that. B plus b is 2b. A plus negative a just cancels to be 0, and then you have 0 plus 1, which is 1. Yeah. Therefore, if you divide 2 on both sides, you get b is equal to 1/2. All right. And then here you have the condition that b minus a must equal to 1. If you plug in 1/2 into b here, then you get that, subtracting 1/2 on both sides, you would get that 1 minus 1/2, which is just another 1/2, is equal to negative a. Take the negative on both sides, you get a is equal to negative 1/2. So finally, in this c term right here, let's plug in a is equal to negative 1/2 here. Well, for them to cancel out to be 0, then c has to be the opposite, so it needs to be positive 1/2. Alright, and just like that, we're done with the partial fraction decomposition. I'm going to draw a line down and across. It's slanted, but, this is just to give us room to work with. Start here, and you know what, it's probably not worth it to do that because I completely forgot about it, so let's just keep it outside. 2 times an equal sign, right? 2 times the integral of that, when we said this is equal to this, right? And then we just plug in the coefficients one by one. So, for the first term, I'm gonna just write it down in the first term. A is negative 1/2, and it is over u plus 1, and then du. And I'm breaking up the fraction, and that means I'm breaking up the integral, so that means I have to distribute the coefficient of the integral. Bu plus c over u squared plus 1, right? And then b is 1/2, and then u plus c is also 1/2 over u squared plus 1 du. Okay, now what you can do is this cancels with that. Notice how there's still a negative sign though, so we can move that negative out sign, and then this becomes 1 over u plus 1 du. Same thing here. If you distribute the 1/2 out, factor it out, then it cancels with the 2, so you're left with no coefficient in this one. And this coefficient is now 1, that is now 1, 2. So you get u plus 1 over u squared plus 1. Let's just break it up into 2, right? So this becomes u over u squared plus 1, and then plus 1 over u squared plus 1. Alright. For this one, for this one, top is the derivative of the bottom. Here we just use inverse tangent. This one is a little bit more difficult to do use up in your head with a quadratic. However, let's make the top the derivative of the bottom by multiplying a 2, right? Derivative of the bottom is not the top, but that means we have to multiply a 1/2 on the outside too. So we kind of swap the order of these coefficients. Notice that. All right. And then finally, here we have negative inverse tangent. This isn't inverse tangent, not yet at least. This is a natural log. And this is a natural log of the absolute value of, and don't forget the negative on the outside, that's my bad, u plus 1. And I should be doing this in red, so for the third time, let's redo this. Negative natural log of the absolute value of u plus 1. Second one, we have the 1/2 on the outside, then we have the natural log. Bottom's the derivative of the top, so we get natural log of, and it's always positive, so u squared plus 1. Alright, okay, and then here we have just inverse tangent. U, okay? U is tangent. Tangent plus 1. Tangent squared plus 1. This is, let's do this step by step. Plug in a tangent here. Get negative natural log of tan x plus 1, and then close the bar. Alright, if you plug a tangent into here, tangent squared plus 1 is secant squared, and if you take the 1/2 up here, then this becomes a root inside of the natural log. So you have natural log of the square root of, earlier we determined this was secant squared. The root and the square cancel, so you just get a natural log of secant. So all in all, this is natural log of secant x. And this needs to be absolute value bars actually, because secant is not always positive. And I mean, you may be wondering, well, we took a square root, right? That's always positive, and this is also always positive. Why is this not always positive? Well, because bringing an exponent up, sometimes it introduces domain problems, right? So yeah, that's the easiest explanation as to why. And right here, we have inverse tangent of tangent x. We just have x. And yeah, add c. And you might, wait, give me 1 second. If you have this on top and then have that on the bottom. Yeah, you know what? It's fine. I'll box this. It might not be the most elegant form of the answer because you might be able to combine the logs and do something like that. But I think for now, this is the best form I can come up with. That looks to be about right. All right, so that's number 7. Ooh. And this whiteboard is wobbly because it's mounted at an angle to the wall, so I think that's because there's a light switch back here. There's a light switch, so right? And it still needs to be accessible. Yeah. Okay, number 8, we have an integral of more trig stuff. This one I think should be easier. Sorry, number 9. We just did number 8. I'm confused because I put both 7 and 8 on the board. Integral of 1 over sine x plus cosine x squared. And first glance, there's nothing to work with on top. You can expand this out on the bottom, but, where do you get? Now, you can do the thing where you introduce a sine squared plus cosine squared on top, but I'm going to tell you right now, well, maybe that would work. No, it wouldn't. So, for now, let's just expand out the bottom and see how that goes. Alright, so, here we go. Bottom, first term, we have to square it, right? And then middle term, we multiply 2 times this times that. And then last term is just the last term squared, like that. Top is still 1, we're not going to do anything with that. Dx. Alright, notice that sine squared x plus cosine squared x is equal to 1. And then 2 sine x cosine x is equal to sine of 2x. Alright, now notice how we have condensed all of these inputs into just one x right here. And it is linear, so let's make a u substitution. Let u equal to 2x. Du is equal to 2 dx. So let's multiply 2 on top. So we have our 2 dx, but we also have to divide by 2 on the outside. Okay, so now we get the 1/2 stays. On the top, 2 dx becomes our du. On the bottom, 1 plus sine of, 2x is just u. Alright, this is our new integral. And whether you recognize it or not from the previous 100 integrals, we've actually done this before. Found the antiderivative, and it's actually really satisfying. And this is actually question, I think, number 100. If you'd like to refer to that, sure can, but I'm going to work this out the way we did it. Multiplying the conjugate, right? Since you get difference of squares, 1 minus sine squared, right? That's nice, because it's cosine squared. Top, it's blank right now, so multiplying the 1 minus sine squared, not 1 minus sine squared, multiplying the 1 minus sine u just gives you 1 minus sine u. In the bottom, get the sum of, difference of squares of these bitch boys. Alright, and then, now what you're able to do is, this is cosine squared, and then notice we can also split up the fraction. I'm going to keep it in the same integral though. So we have 1 over cosine squared, which is secant squared. Then we have a minus sign. Sine over cosine squared, if you think about it, you can write it as sine over cosine times 1 over cosine, which is tangent times secant. So this is a secant tangent. Oh, and sorry, the arguments should be u. So let's do that. Sec u tan u. That's weird. Du. Integrating secant squared, you get tangent. And meanwhile, I'm going to distribute the 1/2, so you get tangent u. Integrating secant u, tangent u, you get just secant u. And then, of course, you know that u is equal to 2x, so 1/2 tangent becomes tangent of 2x, and then minus 1/2 secant of 2x at C. And I'm going to back up so you can see what that looks like. Now, these both have I'm pretty sure there are multiple ways you can simplify this. However, this looks good enough to me. But the thing you have to keep in mind, if you do try to simplify this, is it has a denominator of cosine 2x, right? And you would use that, and then combine the fractions, and yeah. Alright, but I'm gonna stay with this answer for now. And what was I gonna say? One more thing. I think you can recognize this one's defined at pi over 2, right? Yeah, but this one is not. So there is like a problem with what we multiplied in, probably the conjugate, but you know, it should be okay. This like works for integration purposes. All right. That's number 9. All right, number 10. Number 10. Integral of, and we're moving on to rational expressions. Here we have our first one, 7 minus 6x minus x squared. There's 1 on top, there's a dx on the side. Factor this. And you get, well, you know what? Let's bring the negative outside first, so it's easier to look at and think about, because most people typically deal with the x squared in front. So the x squared is now positive x squared. Negative 6x is now positive 6x, and then the positive 7 is now negative 7. Other than that, nothing's changed. We're still able to factor this. Factoring this, you get 1 over x minus 1, x plus 7. Yeah, I can't factor that instantaneously. It still takes a bit of thought as to what numbers are required. Partial fraction decomposition. 1 over x minus 1, x plus 7 should be equal to constant over linear, right? And then another constant, sorry, this one's ugly, over linear. I think I just made it uglier. Let's use cover up. This needs to be 1, set x equal to 1, cover that up. 1 plus 7 is 8. So you get 1 over 8. 8 is equal to 1 over 8. Secondly, b, set x to be negative 7, cover that up. Cover this up, sorry. And then negative 7 minus 1 is negative 8, so therefore b is negative 1 over 8. Okay, almost there, because, well, we have a negative, and we have integral of, we just replace this, see, with that. So 8 is 1 over 8, and then x minus 1. And I'm going to keep this in the same integral. You're adding negative 1 over 8, which is b, over x plus 7 dx. Okay, and now what you can do is, yeah, okay. Just integrate, since the top is, well, a constant times the derivative of the bottom, but if there's a constant being multiplied in, you can just leave it outside. Also, I'm going to distribute the negative. Let's do this one first, because this is going to be a positive term. Negative times negative is positive. Move the 1/8 outside. And then you get 1 over x plus 7. You get natural log of the absolute value of x plus 7. Next, you have this right here. And by the way, this function, I don't think it's analytic. It's not analytic. This one, and that thought just popped into my mind for some reason, but distribute the negative, you got 1 over 8, natural log of absolute value of x minus 1. And feel free to combine them, although, you know, it's not completely necessary. I think this looks good enough. Add C, box it, and we're good. That's number 10. Alright, and let's move on to number 11. And the reason why I didn't touch the integral when I'm erasing, because we have a root. We just introduced a square root. Yeah. And this becomes number 11. Alright. For this one, we have a quadratic inside of a square root. Don't overthink it. Complete the square, because it's a quadratic inside of the square root. And try a trig substitution, right? Even though it looks very factorable, don't turn to that immediately if you see the root. And yeah, you know, it's still a quadratic. You're still going to need to complete the square. So let's complete the square. And to complete the square for this, we need a negative x squared, negative 6x, right? The value to complete the square is negative 9. we pull a negative 9 out, and then we have to add back 9, and then we also have to add 7, right? So we just add the 9 and 7 together, and it's very nice. We get plus 16. Alright, and everyone should know the next step. We can factor a negative out of these three terms, kinda, and then complete the square. So, factoring the negative out, we got this. And then, yeah, and then we have, this is x plus 3 squared, plus 16. And this is sketchy because the dominating term right here is negative and it's inside a square root. But all right, now let u equal to be the inside. So let u equal to be x plus 3. du would be dx. All right, so here integral of 1 over negative. Sorry, there's a root first. Let's write that down. Let's write the 16 down first. And yeah, 16 minus, so we're doing difference of squares, right? But it makes a lot more sense since the subtraction comes after. And then this is just u squared. And du is dx, so I'm just going to replace the dx with the du. Here is a trig sub case. And this is where question number 3 comes into play. Because this is a squared, that is u squared. And we can just use the formula. This is just equal to inverse sine of u over a, which is 4. A value is 4 because square root of 16 is 4. And then finally, one last modification real quick. U replaced with x plus 3. Yeah, that's it. Add C and you're done. Okay, that's number 11. All right. Now, number 12 is a quirky character because we're integrating a sign, but it's to an even power. So we're going to have to exercise some double angle identity to be able to do this. And to be able to employ that double angle identity, let's rewrite this as sine squared squared. Because we know how to deal with sine squared, we don't know how to deal with sine to the fourth, right? So let's write this as sine squared x all squared. Because it means the same thing. Now sine squared x, if you want to rewrite it, it's just 1 minus cosine of 2x over 2 squared dx. And, well, first of all, let's move this 2 squared, like 1 over 2 squared, outside. 1 over 2 squared is 1 over 4, and 1 over 4 is a constant multiple, so you're able to bring it outside of the integral, like this. And inside, you still have this thing squared, the top squared. So let's expand that out. We have 1 squared, we have 2 times this times that, and don't remember it's on negative sign, and then 2 times this times that. So these are both doable, right? And then that squared. So this is just cosine squared of 2x. So a little bit clunky. However, I'll show you how we can deal with this. And instead of just directly integrating that, let's just make a u substitution for all 3 terms. Let u equal to 2x. du is still equal to dx. Outside, 1/4 stays, and here we have integral 1 minus 2 cosine. Instead of 2x, we have a u. Then here, cosine squared u. All right, and then let's integrate all in one step, because here, we can't integrate it quite yet, because cosine squared, well, to be able to integrate that, we need another identity. We need to use the cosine double angle again. 1 over 4 times integral of 1 minus 2 cosine u plus, and then this is, well, and in this case, I'm going to split it up, right? I'm going to write 1/2 plus cosine of 2u over 2. Yeah, you know what? That's fine. And now, we just keep in mind that these are like terms before we integrate. All right, so 1/4 stays on the outside, but let's integrate everything now. 1 plus 1/2 is 3/2, and integrating with respect to u, you get 3/2 u. Integrating this with respect to u, you get, well, integrating cosine, you get sine, so sine u. And here, cosine of 2u, use the reverse chain rule, divide by the 2, right? So you get 1 over 2, and then you multiply 1/2 again, you get 1 over 4. And then integrating cosine, you get sine. Argument remains the same. Close, 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 close. And then from here, multiply this in, you get 3 over 8. U is 2x. So if we have a 2x here, that reduces with the 8 to make it 3 over 4. And then we have the x, yeah? Minus 2 sine of 2x. And then, right, okay, and then from here, distribute that in, we get 1 over 56, no, not 50, wait, what did I say? 1 over 16, 4 times 4 is 16, 1 over 16, and then sine of 2u, u is 2x, so you get 2 times 2 times x, which is 4x. Alright, and in these notes that I made, I did this question in a different way, and it's quite yeah, I don't know, it's really dumb, but I'm guessing this is probably the right answer. If not, I'll come back later and change it. Did I do this right? No, I didn't. Yeah, so multiply the 1/4 in, you get 2 over 4, which is 1 over 2. Add C, box, and yeah, that's your final answer. That's number 12. Okay, so let's move on. Number 13. Now we're dealing with exponentials. First time in a while. We got, well, not really first time in a while. We did it back in like question number 3, but maybe 3, maybe 4. It's one of them. 1 plus e to the x squared over, what was it, e to the x dx. This one, there's not much you can do with it except expand the top out. So to do that, we just get 1 plus 2 times the first term times the second term. So you get 2e to the x. And then the second term squared, which is e to the 2x. Don't forget, we're dividing by e to the x. And this is easy. 1 over e to the x, we can rewrite this as e to the negative x. And, well, we're all going to write these in the numerator now, so I'm going to just need the parentheses, right? And then 2 e to the x over e to the x, you just get 2, because e to the x is cancel out, and then e to the 2x over e to the x just gives you 1 e to the x dx. Alright, this one, reverse chain rule. You have to divide by -1, so it's just negative e to the negative x. This one, you multiply by an x, and e to the x is the same. Yeah, add C. Cool. And of course, feel free to write this in fractional form again, right? But I don't think that's necessary. Okay, and then number 14 looks very similar, so I'm gonna draw a line, do it over there. And I think it's equivalently as easy, maybe a little bit more difficult, but it's definitely not, it's nowhere as difficult as some of the other integrals that we're gonna face in the next, like, 10 hours or so. E to the x over 1 plus e to the x squared. For this one, notice that whatever is in the square, if you take the derivative, you actually get this exactly. So, if you just let u equal to 1 plus e to the x, then du would just be equal to e to the x dx, right? 1 plus e to the x dx, that's just du. So you get integral of this, as we said, and then in the bottom we have 1 plus e to the x, which is our u, and then it's squared. This is standard, we get negative 1 over u, and then u, of course, is 1 plus e to the x. Add c, and yeah, there we go. That's number 14. So takes about the same amount of work, but and the concept is very similar. All right, next up we have number 15, and 15 looks difficult at face value, but if you think about it for a second, it gets better. Now, the way black pen and red pen presented this made it look like it was a trick. However, I want you to recognize that, it's not really a trick. You're able to figure this out by yourself if you just give it a shot. The way he presented this integral right here, is, well, just let u equal to the root. And of course, you can do that. But yeah, I think maybe a better way to do it would be multiplying x to the 14th on the bottom and the top, because what you get when you do that is x times x to the 14th gives you x to the 15th, and on top you get an x to the 14th. And I mean, of course, his way is probably a lot more efficient, right? But however, now it's a little bit more obvious what to do, since x to the 14th dx is well, it's a result that you could have gotten from chain rule by having your initial well, the thing you're going to differentiate be the root, right? So now I think we've made it a little more obvious. Let's try it out. And also, the way we justify this x to the 15 right here is just by telling yourself, well, you're probably going to be able to isolate the x to the 15th, which you are, right? Just square it and then add 1. So yeah, okay. And also, you still have to deal with the differential. But here's what I'm going to do. I'm going to square both sides and then add 1 first. This is equal to x to the 15th, right? So you see, we found the equivalent form of that, but how you differentiate it, you have to differentiate it like this. 2u du, right, is equal to 15x to the 14 dx. And notice you have x to the 14th dx here. We don't have a 15, so let's just multiply it in. But we also have to divide by it if we multiply it in, right? So from here, 1 over 15 stays outside. And the 2 is multiplicative across everything, so I'm actually going to multiply that outside as well. Okay, from here, the top is just your big-ass differential, 2u du. So I'm going, and we already dealt with the 2, so on the top, I'm just going to plop a u. In the bottom, x to the 15th is u squared plus 1. You know what? Yeah, I'm just going to write it as u squared plus 1. And then this guy right here, we set to be u. That and that cancel, and we still have our du from the 2u du. Okay. And from here, yeah, and it worked out really well. And you kind of have some intuition as to why, right? Because you have your differential on top. So that's why. Okay, and from here, we're just integrating a standard form. Du over u squared plus 1. This is just inverse tangent of u. And inverse tangent of u, where u is root of x to the 15th minus 1 plus c. And that's it for number 15. All right. Number 16. For this one, let's slow it down and give it a little bit of thought. We're dealing with a bunch of signs. Sine x, sine 2x over 1 plus sine, is that cubed? Looks like cubed. All right, first of all, let's rewrite all of these trig functions with argument x. So we want to expand that out, basically. And 2 sine x, cosine x, right? That's how we expand it out. And then the 2 is multiplying, so we can move it outside for now. In here, we have sine x squared, right? Because we have another sine x here and one from in here. And then we have our cosine x that comes from us expanding out that sine of 2x. Bottom, so 1 plus sine cubed. All right, so the top, there's a sine squared, and then you have the derivative of sine, cosine. So it looks like it's something that happened through chain rule, right? And what you could do is let u just simply equal sine for now, and then treat this as a rational expression that you have to deal with after you make a substitution. However, it can be more elegant than that, and for that you need to slow down and observe. As I said earlier, this looks like it came from chain rule, and chain rule of what? Well, if you had a 3 here, then first it looked like you did power rule, right? You had sine cubed, and then you did chain rule because you took the derivative of the inside, sine. So it looked like you had sine cubed originally. Notice that you have sine cubed on the bottom, and this plus 1 actually doesn't do anything because, all it does is take the derivative, it goes to 0. So what I'm saying is the top is almost the derivative of the bottom. We're just missing a 3. So let's multiply 3 and then divide a 3. Therefore, and now we can make a substitution. Let u equal to the bottom. And then taking the derivative, du is equal to, well, let's prove this out. 1 goes to 0. For this one, power rule first, 3 to the front, and then sine becomes squared. And then take the derivative of the inside, and it's the sine that's being cubed, so we have to take the derivative of sine, you get cosine. So yeah, notice this is just the top, so this is du over u. And then finally, this just gives us natural log of u. So, and u is, I'm gonna keep it short, it's 1 plus sine cubed. All right, and there's one more thing to note. Notice that if you, sine cubed is, well, first of all, let's take sine, right? It's always between -1 and 1. Cube any value between them, all it's going to do is get smaller, and cube each of these, it's just going to stay the same. So therefore, this guy right here is always between -1 and 1, and these should be hard brackets. Add 1 to this, right? Then this entire thing, each of the bounds increase by 1, because well, you're adding 1 to the entire graph, shifting it up. So this becomes 0, 2. Yeah, and recognize that it's inside of the natural log. That's why we need the absolute value. However, the bottom, well, no, not the bottom. The inside is always non-negative. So we don't actually need the absolute value bars to keep it such that we're able to work on all domains that are defined for this function at least. So we can just get rid of the absolute value bars since the inside is never negative. There we go. Add C. And I think it could be negative if you're working with a complex valued sign. However, well, we're dealing with a normal, typical standard integral, so I don't think we don't need to take that into account. Yeah. Okay. For the next one, I might need to take a look at my notes, but I think I know how to do it. Okay, so, yep, we do a trig sub, and here's the integral written out. X squared minus 3 over x dx. Yeah, and I was saying we do a trig sub here for number 17. It looks kind of weird, maybe you could do some algebraic manipulation for that, but I think I would just do the trig sub and have it be over with. This is the difference of squares, so and the variable is in the first term, so you would use secant, right? And then secondly, this is not 1, this is 3. And so we need a value to multiply onto the secant, and that would be the root of that number, which is root 3. Okay. So just implement the substitution. In here, we have x squared, this thing squared, so you get 3 secant squared. And then minus 3 over, don't forget we have the x down here too, so we need to replace this with root 3 secant theta. Right here, we need to work on finding our differential. Root 3 is just a constant, it stays there. And then we have to find d secant first, which is secant theta, tangent theta, and then we have to find the d of the very inside, d of theta, which is just notated as such. Oh, right, and of course we have to multiply this in. Root 3 secant tangent, yeah. Root 3 cancel, secant cancel. Yeah. Alright, so here we can factor out a we can factor out a normal 3 inside of the root, and that just becomes a root 3 that we can multiply onto the side. What you're left with is a secant squared minus 1, which is tangent squared, which taking the square root gives you just normal tangent. So you're left with a tangent here. Notice how you still have one more tangent here, so it's kind of like squaring the deal. And then we still have our d theta. Alright, and this one is pretty simple. We just replace it with its counterpart, secant squared theta minus 1, both of which you're able to very, very easily integrate. You get root 3. I'll distribute. Secant squared theta is just tangent theta. Yeah? And then minus 1 in the theta world is minus theta, but don't forget to distribute the root 3. So it's root 3 theta. Yeah. Here, we should draw a right triangle and then find out what our ratios are. I just realized I haven't checked whether my camera is still recording or not for the past, hour, 20 minutes at this point. Alright, here, notice that, let's divide root 3 on both sides. Secant theta is equal to x over root 3. Right, however, and, we also need to isolate theta here, so let's just inverse secant on both sides. Inverse secant of x over root 3 is equal to theta. However, that's not what we're looking at for the right triangle for now. Right triangle, secant of angle, this angle, gives you hypotenuse over adjacent. And hypotenuse, therefore, would be x, and adjacent would be root 3. So this is x, this is root 3. It's this right here. That squared minus that squared. So you get x squared minus 3. All right, and all you need now is the tangent. Notice that tangent is this over that. Since the root 3 is in the denominator and you're also multiplying by root 3, those two can cancel. They can just cancel straight up. So all you're left with is a square root of x squared minus 3. Secondly, here you have minus root 3, right? And then theta, this is the reason why we did that up there. Theta is equal to inverse secant of x over root 3. And we're not going to rationalize the denominator. Hopefully we're all doing math that's, well, not baby math at least. That's it. Whew. That's number 17. Number 18. 18 is trigonometry once again. God damn it. Integral of top, you have cotangent. Kind of odd already. Bottom, you have sine. Yeah, and cosecant. This is simpler than you think because this has a denominator of sine. This has a denominator of sine. So you can just multiply by sine. Multiply both the top and the bottom by sine. Okay, cotangent times sine is just cosine over sine times sine. Sine and the sine cancel, you're left with the cosine. This becomes sine squared, since you're multiplying into sine. And then the cosecant x is 1 over sine, right? So it becomes just 1, because the sines cancel. And finally, cosine x dx is the differential of sine, so let u equal to sine, and then du would therefore be equal to cosine. And the chain rule dx. Alright, from here you get that this is the integral of du is on top. On the bottom you have sine squared, which is also u squared, and then plus 1. This is inverse tangent of u. And u is sine x. There you go. And unlike our trig of inverse trig functions, if you had it the other way around, that wouldn't apply so much. This just looks like a rockier like sine wave, I guess. Right? So yeah, there's no other way to formulate that unless, I mean, you can use complex analysis, but don't do that. Don't do that. Number 19. Is a little bit quirky looking. However, make the right substitutions and it all gets better. 1 over x squared plus 1 to the 3 halves power dx. Ooh. Alright. Tangent, right? You can have the sum of squares and it's inside of that weird exponent. Let u, sorry. This is a trig sub, let x equal to tangent theta. Dx would just be secant squared theta d theta. My red pen's running out. I'm going to replace it after this recording. From here, we get, well, let's pop the secant squared theta d theta down first. On the bottom, if you plug in a tangent into where x is, tangent squared plus 1 is secant squared, right? So, yeah, secant squared. However, notice that we still have it's to the 3 halves power. Okay, here's where this weird exponent gets taken care of. There's a 2 in the exponent here, and it's to the power of another square. So that means this 2 in the denominator of the exponent gets canceled with the 2 in the numerator of the exponent. So this isn't secant cubed to the weird power. This is secant to the 3rd power. Secant squared over secant to the 3rd. Well, you get 1 over secant, because you can divide both the top and the bottom by secant squared. And then, so now you get 1 over secant. I'm going to write this in black. Alright, for this one, it looks kind of weird, but that's because it's so elementary that you never, it's just integral cosine. And integral cosine in theta in the theta world is sine theta. And of course, now we need to get back to the x world. Draw a right triangle. This is a big right triangle. This is our theta. Now, tangent gives you opposite over adjacent, and therefore this x is opposite over adjacent. X over 1. Opposite over adjacent. And this side would be x squared plus 1, because Pythagorean theorem. Now we want to find the sine. Sine is opposite over hypotenuse. That's kind of odd. But don't worry, we've got this, because we still have a couple more tricks up our sleeve. Well, actually, do we even need to reduce that? That's my question. Well, I mean, if we started with that thing in the denominator, then I don't think it's necessary, so. Yeah. And cool thing is, the previous question, remember, and, well, actually, before I get onto that, let's rewrite this as sine of inverse tangent of x, right? Because recognize that, well, let's add c to both of these and box them first. But you recognize that sine theta, right? If you just took inverse tangent on both sides, you get inverse tangent x is just theta by itself. Yeah. So inverse sine of theta is inverse sine of, not sine of theta is sine of inverse tangent. Cool thing about this, and I should have noted this earlier, was number 18. The answer was inverse tangent of sine. Yeah. Cool thing to know. Sine of inverse tangent of sine. Yeah. I think that's a very nice Easter egg to keep in. Yeah. Okay, and I'm gonna do one more, and then after that we're gonna move on to the what'd you call it? I mean, the power reduction form, the integral power reduction formulas. There's a whole barrage of them, but this one is just nice and relaxing. Number 20. We're still in the easy phase of integrating. Root of 1 plus root x dx. Looks intimidating. Looks intimidating. It really isn't. It isn't. Let's let u equals 1 plus root x. Because, you know, it gives us a nice equivalent. The differential is nice. For this, I would do u minus 1 is equal to root x. Right, and then take the square on both sides. And if we expand this out, you get u squared minus 2u plus 1 is equal to x. Pretty simple so far. Taking the derivative, 2u minus 2 is equal to dx. We forgot chain rule. You need to multiply everything by du. This is equal to dx. Okay, and from here, I think it's easier. Yeah, it is. Because we are able to just do integration by parts. So from here, we get integral of, first of all, factor 2 out. Let's move that to the outside. Don't deal with that yet. So we have a u minus 1. Yeah, let's put that down. And then, secondly, we have this root. That's our original integrand. And the inside of that radicand, the radicand, is our u. So we can just replace this, replace the radicand with u. dx, we have this times that times du. And now, well, we don't even need to do integration by parts. Let's just distribute out the u, and then do it like that. So, root u times u is u to the 3/2. And then, root u times 1 is u to the 1/2. Still with respect to u. Alright. 2. Reverse power rule. Add 1 to the power, you get 5 over 2. Divide by it, so you get 5 over 2, divide by 5 over 2, you get 2 over 5. So 2 over 5. u to the 3, sorry, no, not 3. We added 1, so it's now 5 over 2. Here, add 1 to that, you get 3 over 2, divide by 3 over 2, you get multiplied by 2 over 3, u to the 3 over 2 du. Alright, now let's make a couple modifications. Multiply the 2 in first. Here you would get 4 over 5. And then, since it arrived to us in the radical form, I'm gonna put it in the radical form before we leave. So u to the 5 halves, well, the half would just be a square root. And then inside we just have a u, which is 1 plus root x. And because of this being the same as that, I'm going to put the power on the outside just for, you know, the fun of it. And finally, do the same thing with the second term. Multiply the 2 in, you get 4 over 3. And then this is now, same idea, root of 1 plus root x. However, it is now to the 3rd power. Add c, and we're done with number 20. And that is the end of it for, well, let me check. Well, not the end of it for normal integration, but we're gonna now move on to the integral power reduction bad boys. I got a fresh red pen in hand, and now, as I promised, let's move on to the power reduction formulas. And I'm pulling it up on my PC right now, just to make sure. Yeah. Okay. So, number 21, we have integral of x to the n, e to the x. So this is arbitrary. We're not going to be integrating the whole thing, even though it is possible. We're just going to be finding a power reduction formula to reduce the power. All right. So, integration by parts, because this is a polynomial times exponential case, and this still applies here. Differentiating a polynomial, you just get the power rule. Integrating an exponential, the exponential function, so e to the x. Multiply diagonals, integrate rows. Alright, so multiplying the diagonals, you get x to the n, e to the x. And then there's a subtraction there. Bring the n outside of the integral since it is multiplicative, and on the inside, you can just leave the x to the n minus 1, e to the x. What was that? dx. Okay. And this is actually the answer that we were supposed to get to, since this is a power reduction. We're getting the same exact form of the integral, just with a reduced power. So we can box our answer and be done with this one. Number 22 is almost as easy. So I'm going to do it on the same line. So, same board, sorry. Alright, we have integral of natural log of x to the nth power. For this one, typically how you do natural log of x is you would do integration by parts. You would integrate the entire thing, and then, you would differentiate the entire thing and then integrate just one. Alright? So, yeah. Differentiate this. And then what you get is power rule, take n down, and then you have an ln x to the n minus 1 power. And then don't forget to divide by x, because inside the function is ln x and chain rule. Alright. Now for the integrated function, it's 1, and then integrating 1, you get to x, right? Multiply diagonals and integrate the rows. For this one, x times ln x to the nth power, you can just write it as such, right? And then here you're subtracting off, notice that you want to integrate this times that. First of all, notice that the n is multiplicative, so we bring it outside, and also it's a constant. And second thing, x and x cancel, so you're left with ln x to the x minus 1. Ln x to the n minus 1. like that. And yeah, dx. And actually, this is it, because similar to the previous one, we have the same exact form inside of the integral, just with 1 degree less. And yeah, box your answer. That's it. Okay, so that's natural log. And we have 3 trig functions that we gotta deal with. And yeah, I'm going to erase this then. So that was 21 and 22. Now moving on to 23, we have to integrate sine to the nth power. Okay, for this one, let's try, I think we could differentiate the one sine x and then integrate the, we integrate most of them and then differentiate the other. At least that's how I remember it being. So I think we differentiate most of these guys. So sine to the n minus 1. And then differentiating this, relatively easy. You get an n minus 1 down here. Sine to the n minus 2. Don't forget to multiply by cosine because of chain rule, right? And then integrating, you would integrate, sine to the n minus 1 times sine is equal to this guy, so you need to integrate sine. And we chose to integrate sine because it's really simple. Negative cosine. And what this does is it gives you cosine times cosine, which you're able to manipulate into another sine. So from here, we multiply diagonals, integrate rows. Okay, and the diagonals, it's just negative sine to the n minus 1 of x times cosine x. Negative negative makes a positive. And then integrate. Well, first of all, n minus 1 is a constant factor. So we can bring it outside. And then we have sine to the n minus 2 times cosine. So we put down sine to the n minus 2. Notice that cosine times cosine squared, is 1 minus sine squared. And we want to write everything in terms of sine to be able to simplify it further. So let's try that. Include the argument first. And then 1 minus sine squared x dx. Alright, from here, notice that this is fine now. What about this? Well, if we distribute it out, then you have one term that is sine to the n minus 2, and then the other term is back to sine to the nth. And we only want one integral in the power reduction, and that is just simply sine to the n minus 2 times 1. So the other one, this is actually what you would call a repeating case of integration by parts. So I'm going to use the help of the left-hand side, which is sine to the nth of x dx. And do some work with that. First of all, let's write down this first term before we get too far. Alright, plus. I'm going to distribute this out so you get two terms, and then I'm going to split the integral and make sure we distribute this guy as well. So n minus 1 times, let's distribute it into the 1 first, so we get just integral of sine to the n minus 2 of x dx. Secondly, we want to subtract off, and then don't forget we still distributed the n minus 1, the integral of sine to the nth power of x dx. Alright, and we're almost done, but we have two integrals, right? And we only want this one, because this one was the reduced power. And so notice that if you add n minus 1 of these guys on both the left and the right hand side, it disappears from the right hand side. And you can actually rewrite it on the left hand side. So let's try that. So adding n minus 1 times that integral on both sides. 1 plus n minus 1 of them gives you just n, right? So this just becomes n of integral sine to the nth power x dx. And this part remains the same because we didn't do anything to these, right? And secondly, what you do from here, you just want to isolate integral of sine to the nth dx again. Just divide everything by n. And yeah, you've isolated the integral, and now you also only have one more integral on the right hand side. So dividing this first term by n, you get 1 over n times whatever we were going to write, plus n minus 1 over n integral of sine to the n minus 2x dx. And yeah, that's it, because we've isolated this, and this is a reduced power version of what we started with. So I'm going to box this in black to mark that we've finished this question. And it looks right. Yeah, it looks right. So there you go. And we're going to move on to number 24, which is tangent. Of course, cosine can be done in a very similar manner to sine because they work fundamentally the same. So, and tangent with cotangent too, and secant with cosecant too. So we're only going to be doing sine, tangent, and cotangent, not cotangent, sine, tangent, and secant today, because those are like the three primary trig functions. Their co-counterparts work around the same way they do. All right, next one is number 24, tangent to the n. For this one, I am pretty sure we don't have another repeating case of the integration by parts. Instead, what we can do is what we do for any tangent to the nth power. We would break off a tangent squared. So what this gives us is tangent to the n minus 2 of x, and then a tangent squared. Don't forget though, tangent squared, the reason why we break it apart, we split into secant squared x minus 1. Right? Okay, so that's step 1. Step 2 is to break it up into two separate integrals by distributing this out. So the first integral would be tangent to the n minus 2 of x times secant squared x. And you are able to make a substitution and then use reverse chain rule. And then for the second one, it just is what it is. You get minus, because negative 1 times integral of tangent n minus 2x dx. So this is what you want to keep, and this is actually doable through a substitution. You would let u equal to tangent, because secant squared x dx is your differential. Okay, so from here, what we can do is write this as integral of tangent is u, and then it is to the n minus 2 power, so it is still to the n minus 2 power. Secant squared x dx is just your du, so we can keep it like this. Alright, from here, add 1 to the power, and then divide by the new power. So dividing by the new power gives you 1 over n minus 1, and then this is u to the n minus 1. Don't forget, we still have that guy, so I'm going to write this down here. And here. From here, go back, right? You just get tangent, and you're done. So you get 1 over n minus 1 times tangent to the n minus 1. And then you just have your last term, which is the power-reduced version. And this one is arguably the easiest out of all three trig functions, because you don't have any integration by parts, and it's all pretty easy to think about in your head. Box it, and we are done. Yeah. Okay, that's number 24. All right, number 25, we've got secant, and I think secant we do need an integration by parts. All right, so number 25, did I say? Integral of secant to the nth power x dx. For this one, I'm going to split it up into secant to the n minus 2 x times secant squared. And the reason why I'm doing this is because if you split off the secant squared, well, you're able to integrate this, and then differentiating this isn't all that bad either. So here we go. let's use the DI method for integration by parts. Secant to the n minus 2x. And integrating, you would integrate secant squared x. Alright, differentiate. Secant to the n minus 2. This is power rule, right? So first take the n minus 2 down. Subtract 1 from the power. Subtract 1 from the power. Yeah, I think subtract 1 from the power. Jesus, you get secant to the n minus 3. But don't forget to multiply by the derivative of the inside. And the inside function is secant, since secant is being raised to a power on the outside. And the derivative of secant is secant x tangent x. And I'm going to quickly rewrite this as n minus 2 times secant to the n minus 3 times secant x is now secant to the n minus 2 x tangent x. Integrate secant squared, as I was saying earlier, I erased it for more room to complete this, and then integrating that, you just get tangent. Quickly, just multiply the rows, and then, multiply the diagonal, integrate the row. Alright, so the diagonal, in case it's unclear, it's just this times that. Secant to the n minus 2 of x times tangent x. Alright, and then this one right here, you would move the n minus 2 outside. Alright, and then the second step, we put this down, and then we put all this crap in here. Alright, notice, however, that tangent squared, you can't really use tangent squared in an equation, well, in an expression that, in an integral that looks like this. So we're going to change it back to secant squared minus 1. And very similar to sine, you now, if you distribute this out, you now get a repeating case. So we're going to drag that guy down here to help us. Integral of secant to the nth power x dx is equal to that of course, secant to the n minus 2x tan x minus n minus 2. And we're going to distribute this out. So first of all, let's put this times the negative 1 down. Negative makes a positive. So this becomes a positive. And then you have integral of secant to the n minus 2 times 1 is just integral of secant to the n minus 2. Secondly, we have this times that, and then don't forget that. So this is still minus n minus 2. And then we have, well, let me put this down first. And then we have integral of secant to the n minus 2 times secant squared. The negative 2 and the positive 2, they cancel. You just get secant to the nth power. So yeah. And this is the reason why we dragged the left-hand side down here to help us. That's a dx, by the way. Because we have two integrals, we only want to keep the one with the reduction in power. So to get rid of this, we add n minus 2 times the integral on both sides, right? Adding n minus 2, 1 plus n minus 2 gives you n minus 1, right? So left-hand side, n minus 1, integral of secant to the nth power, x dx is equal to. This stays the same. This also stays the same because all you really did was add a term and it doesn't affect any of the other ones. Alright. Okay, and finally, to isolate the integral of secant to the nth power again, divide by n minus 1 on both sides. Dividing n minus 1 by n minus 1, you just get a coefficient of 1. So I'm not going to write it down because no one ever does that. Alright, first term dividing by n minus 1, you have to just do this and then put down the secant to the n minus 2x tangent x. And this one, n minus 2 divided by n minus 1 is just what it is. It's just n minus 2 over n minus 1. Integral of secant to the n minus 2x dx. There you go. You isolated this, right? So, and this has the reduction in power, so we find that this is equal to that. And it's actually pretty easy, right? But yeah, that's it for the power reductions. Back to normal, or more or less normal, integration. Yeah. So number 26, we just have a bog standard one. I'm not sure why he included this, maybe to give us a short break. We have x squared plus x plus 1 squared dx. Maybe he wanted to talk about the trinomial theorem, which is less commonly known, of course. But for now, for this one, I'm just going to manually expand it out. I'm not sure exactly what it's called. I think it might be binary expansion, but it's just when you square something, you multiply this by itself, then this by the next one, then this by the next one. All right. So it's like counting. If you called it 0, 1, and 2, you would count 0, 0, 0, and then plus 0, 1, plus 0, 2, right? And then this is counting tertiary, so you're running out of numbers, so you would switch the first digit to a 1, 1, 0, 1, 1, 1, 2, and then you run out of numbers again, so 2, 0, 2, 1, 2, 2. You're just adding up all of the possible permutations. And if you think about it in the sense of expanding this out, then it makes some sense. So we're going to do it like that. X squared times x squared is x to the 4th. I'm not going to color code this. It's going to take too much time. X squared times x is x cubed. X squared times 1 is x squared. Second, work on this. Let's have this x. X times x squared is x cubed. X times x is x squared. X times 1 is x. Finally, 1 times x squared is x squared. 1 times x is x, and then 1 times 1 is 1, close that dx. This are like terms. So x to the 4th plus 2x cubed. And then we have this one and that one. They're all like terms. And we have 3x squared. And then we have this one and that one, which gives us 2x. And then just plus 1, close dx. All right. Simple case of reverse power rule. We are this one, first term, pretty easy. Add 1, divide by 1/5 x to the 5th. Second term, a little bit more thought required. Add 1, 4, divide by 4, 1/2. So you get 1/2 x to the 4th. This one's immediately recognizable as x cubed. And the next one is immediately recognizable as x squared. And the last one is also immediately recognizable as simply x. You know, these three are pretty standard. I find that pretty cool. Add c. And that's it for this polynomial. Polynomial, good break, I guess. And that recharges us up for the next one, which looks kind of sketchy. We'll see how it goes. All right, that's it. How should we do this? I think it should be okay, right? Next one, we have number, 28, 27. Integral of 1 over root x minus 1 over x minus 1. For this one, I don't remember what the strategy was. I'm pretty sure. Well, first of all, I think we can split it up, and then we can split it up first, and then we can try some other stuff with this junk. Yeah, I think it'll be doable. Yeah, all right. So let's split it up first. And this first term is this over that. And the denominator in a numerator means it multiplies with the bigger denominator. So this becomes x to the 3/2, and this becomes root x. So the first one, 1 over x to the 3/2 minus x to the 1/2. I'm going to just notate it as such. Dx. Second one, you're subtracting, right? And you have 1 over x minus 1. All right, how would we do this? You could. I think you could just let u equal to root x, and that might be it. You can factor out factor out a root x, I guess. So, I mean, we didn't need to distribute it in. So we factor out a root x. Here we're left with x minus 1, just like before. Yeah, if we just let u equal to root x, then I think it might help, because 1 over 2 root x is our differential, and then we can represent this using u as u squared, since u is just root x. So let u equal to root x, u squared equal to x, 2u du equal to dx. I mean, yeah, why not? Yeah, so from here we can do integral of, down here we'll turn this root x into the u for now. This x, notice that it's just u squared. Then is subtract 1. Up here we have our differential 1 times dx, which is right here, gives you 2u. I'm going to bring the 2 outside, u times du. This u and that u cancel, you're left with 2 times the integral of 1 over u squared minus 1 du. This one, should we use hyperbolic tangent? I'm not going to work out the domain of that. I'm debating whether or not to use the inverse hyperbolic tangent, because you absolutely can. Just factor out a negative and then you got inverse hyperbolic tangent of u. Or let's use the natural log equivalent. And in fact, let's start treating this as a standard form more or less, because this is seen more often than you would expect, and there's a variety of ways of representing it. So right here, we can do partial fraction decomposition, right? So this is equal to 1 times u plus 1, u minus 1. And then that means each one of these factors right here, in fact, you know what? Yeah. All right, because this is the standard form, I'm not going to put the 2 in, but the 2 I think it would be helpful. Anyways, each of the factors here sit in the denominators of each of these fractions. Now, to solve for what a would equal, you set u to be equal to -1. That would make that would zero the denominator, and then you would cover up your current factor, right? Plug in -1, you get a is equal to -1/2. Secondly, b, set u equal to 1 to zero out the denominator, and then cover up that factor. You get 1 plus 1, 1 over 1 plus 1, right? And then you get 1 over 2. So b is equal to 1 over 2. Alright, now all we need to do is 2 times the integral of, well, just replace it with this, and you're able to use natural logs to finish it off. 1/2. Well, let's factor out a 1/2. So if we factor out a 1/2, then what out of both, since this is -1/2 and this is +1/2, then that just cancels with the 2. So you're left with nothing outside. On the inside, you're left with -1 over u plus 1. Sorry, no close parentheses. And then plus 1 over u minus 1 du. Alright, and now we integrate using natural log. For this one, treat the negative as if it's outside of the log, so you get negative natural log of absolute value of u plus 1, and then add, this is also a natural log of absolute value of u minus 1. Alright, notice how coefficients are similar. This one's just negative, so if you were to combine the logs, this argument would go down in the denominator, and the absolute value would still persist. So here you would get natural log of the absolute value of, this is in the top, u minus 1, over u plus 1. Alright, so this is actually a standard form for this integral right here. However, we have a 2 outside. So if you divided both this side and that side by 2, then the standard form for integral of 1 over u squared minus 1 would actually be equal to 1/2 times this natural log expression. Remember this. This is important. This is important. We know sum of squares, right? That's important. However, difference of squares is also just as important. Yeah. You don't need a substitution to do this one. I don't know why you would do that. Alright. It's just this. Remember that. Okay, and if we refer back to our original question, let's just replace the u's with roots. And I think that should be the answer that we end up with. Yeah? Let me check, actually, because I'm not... Okay, yeah. So what we get is... Sorry, why did I write plus? Equal sign. Natural log of... Top is root x minus 1. And then the bottom is root x plus 1. Feel free to multiply in the conjugate to the bottom and see how that goes. But for now, I'm just going to not do that and add c. I mean, maybe multiplying the conjugate will make it look better. However, I think this is... I would consider this the final result, right? All right. So that's it for number 27. Let's go on to number 28. '28 is very, very similar in appearance. We've got integral of 1 over x minus 1 over root x minus 1. And I think in this case we would do something quite similar. Yeah, we would let u equal to root x. And it might be nice if we worked on this together. Well, actually, first of all, you know what? Let's... should we split this up? I'm kind of on the edge right here. I guess, why not? Let's try splitting it up and see how it goes. So, for the first one, 1 over x, we put the x in the bottom. So, x is now down here. Then you have the root x minus 1 dx. You subtract off integral of 1 over root x minus 1 dx. Okay. For this one, I think we would use the same substitution for both, if I'm right. Yeah. So we would let u equal to root x minus 1, since this is where it takes place in both of them. And, well, let's isolate x first. U plus 1 would be equal to root x. U plus 1 all squared would be equal to x. And then differentiating both signs. Well, let's bring the 2 to the front and then multiply by the derivative. There's no derivative, so it's just... Well, I mean, derivative is 1, so it's just 2 times u plus 1. And then the innermost derivative, du. And that's dx. And same thing applies for both. Maybe I shouldn't split them up, but, you know, I'm just going to do it for the sake of future proofing, because I don't exactly remember how I solved this one. I mean, yeah, I guess I'll work with it. Yeah, okay. So for this one, this first one right here, 1 over the x we notice is u plus 1 squared. And then we have the root x minus 1, which is just our u. We multiply that in. And in the top, we have 2 times u plus 2, which I guess we'll leave as such. Oh, okay. And then for this one, similar story. The bottom is just u, and the top is 2u plus 2. Right? Don't forget it's subtracting. Top is 2u plus 2. The bottom is u. And, yeah, du. And this comes from distributing out this. Alright, next step, let's split up each of these integrals. This is going to be kind of weird. So the first one isn't actually all that bad, since if we bring the 2 outside, then the u's cancel. So you're just left with 1 over u plus 1 squared du, right? Second one, add 2, and I'm going to bring this one outside because I think we need to do a partial fraction decomposition. Yeah, so this one is 2 times just this denominator. So 1 over u minus, plus 1 squared u. That was messy. Alright, this one, the u's cancel, right? So minus integral 2 du. Pretty simple. And this one, 2 over u, well, there's nothing to cancel, so you just minus, let's bring the 2 outside, and then integrate 1 over u. And I'm pretty sure this is a complicated way of doing it. There's definitely a more efficient way. Maybe you didn't need to split this up in the first place. However, I did it. You're able to integrate this, that, and that. And this one requires a partial fraction. So let's do these 3 first. And then get on with this one later. This one, notice that if you just make a substitution, another variable equals the u plus 1, then du equals d, like say t if you're using t. And you're just integrating 1 over u squared, which is negative 1 over u. So this is negative 1 over u. And because you're multiplying it with 2, I'm going to put the 2 on top. So you're getting negative 1 over u, u is u plus 1. Right? This one is the next one you're able to integrate. 2 stays outside. Integrating u in the u world gives you 2u. Yeah. This one is natural log of u. And the 2 stays outside as well. So negative 2 ln absolute value u. Alright, so that's those 2. Now let's deal with this one. So for this one, what we can do is in our partial fraction decomposition, I'm going to do it up here. I'm going to rewrite this for you guys. U times u plus 1 squared. We want this to be equal to an a over u, since the u is linear, plus, and then because this is a built-up power, I'm pretty sure what you can just do is, and I'm not too familiar, but you can do it to the first power once, but with the constant on top, and then a second, and then do it to the second power, but also with the constant on top. And I've explained why before, but this setup works if you have this repeated, if you have multiplicity of greater than 1. All right. And we're actually able to do cover up for this one and that one for this one. Plug in, play, and I'll demonstrate later. Set u to be 0 for the bottom to be 0. Cover up the u equals 0. You get 1 over 0 plus 1 squared, which is 1 over 1 squared, which is 1 over 1, which is just 1. A is equal to 1. This one, set u equals to negative 1. Cover up, This one, you would set u plus 1 to be equal to 0. So, actually, that's a good question. How would you cover up for this? I think, can we cover up for this or that? If we set that to be equal to negative 1, then it still works then. Okay, so we would let u equal to negative 1, right? Cover up this guy right here. And then this was just now negative 1. So 1 over negative 1 is just negative 1. C is equal to negative 1. Brothers. Do you need to multiply? Here. Let's choose a random value that we haven't used for u yet. Right? A value that wouldn't zero out any of the denominators. Let's use 1, right? We haven't used 1 before. So if you set u equal to be 1, and you just plug in what a is, and b you leave alone because you haven't solved that yet, and you're working on it right now, c is 1 plus 1 squared, and c is negative 1. So I'm going to make this a subtraction of a 1 over that. All right, so my explanation for why this works boils down to the point that because this side and that side are equal, right? And u is present on both sides, meaning regardless of what you set u to be, they're still going to be equal because there's a u on this side, there's a u on that side, the u must be the same as each other. And because it's a variable, it can be anything. And we're solving for b, not u. So we can't set b to be anything, but we can set u to be anything. We found both of these, and this is the only one left. Meaning, if we plug in these numbers right here, then the only variables we have left are u and b. And I think I've explained this before, but if we just set u to be something, right, as I explained earlier, it works, then b is our only variable left, and we're able to condense this and isolate b. So, 1 over 1 plus 1 is 2, 2 squared is 4, 1 over 4 is equal to 1 plus 1/2 b, right? 1 plus 1 is 2 in the denominator, that's just 1/2, minus 1 over 1 plus 1 is 2, square that is 4. Multiply everything by 4 just to make it easier on us. Alright, add 1 on both sides. Divide everything by 2. And then minus 2 on both sides. Negative 1 equals to b. Alright, so there's this. There's these two too. Okay. So now let's plug it in. Add 2, right, and then integral of. We saw that this is equal to that, and we solve for what a, b, and c each are. So, and yeah, you're able to integrate all of them individually. So let's just put it all in. So a is just 1 over u. B is negative 1. So we subtract off 1 over u plus 1. And then c is, I think, also negative 1. So you subtract off 1 over u plus 1 but squared. Du. Alright. For this one, let's dedicate it its own row. Alright, so here, let's distribute in the 2 as well as do all of that. Alright, integrating 1 over u, you get natural log of u. So you get 2 times natural log of absolute value of u. Notice that there's a like term, this and that, they'll cancel out. So let's cancel them out right now, right? That's what I'm saying when I'm saying this method probably has inefficiencies. Like we got 2 answers that just 2 terms that would have just canceled out either way. Anyways, here I have minus 1 over u plus 1, right? Distribute in the 2. The top is the derivative bottom. This is also a natural log case. So you get, notice there's a minus here too. Natural log of the absolute value of the bottom, since the top is the derivative of the bottom. Over here, if you set a new variable to be u plus 1, then you find that you get negative 1 over variable squared. And the antiderivative of that is 1 over that variable. Distribute in the 2, you get plus 2 times, just 1 over the variable, which is u plus 1. And over here, we have a negative version of that. We cancel this out and that out as well. So you're left with 2 terms, this one and that one. All right. Okay. From here, we move on. Negative 2u. If you set u to be back to that, right, and distributing the negative 2, you get negative 2 root x when you distribute into the root x. And then distributing the negative 2 into the negative 1, you get a plus 2. Next, we only have this term left. We have a minus 2 times natural log of absolute value of u plus 1. U is root x minus 1. And then the minus 1, the plus 1, they cancel. So just get that. If you bring this up, then it raises it to the power of 2, and that cancels the effect of the root. So at the very end. Oh, and one more thing. This guy right here. It's a constant. We can put it into the plus c we have at the end. So we don't need it. So we have our first term. We don't need the second term because it's going to be factored into the constant. And then we recognize that we can put the 2 up in the exponent. And we just get a minus natural log of the absolute value of x by itself. Add c and you're done. Alright. Alright, that's it for number 28. Let's move on to our last one that looks very similar to this. And these roots are, honestly, I don't like working with square roots. They're nice to make a substitution, but they bug me in every single other way. Number 29. We have the same exact idea, actually. Number 29, just one minor difference in the way it looks. 1 over x minus 1 over root of x minus 1. As we had earlier, right? This is what we had earlier. Now we just gotta give the 1 a roof, you know? How the hell do we do this? If we multiply both the x on the top and the bottom, then we can cancel this out. Maybe I should have done it this way the first time, but you know what? It's fine. Now, I'm pretty sure what we can do is we just make a substitution using, what was it? How can we do this? You know what? Let's split up the terms again, because if the second term, these x's cancel, and you're left with 1 over a root in the bottom with a linear term inside, and that is very nice to deal with. So, we're left with 1 over x root x minus 1 dx. You're subtracting integral of 1 over root of x minus 1 dx. This one is the one we have to deal with. And I think the way we do it is we let u equal to the entire root, because historically we've been able to solve for the variable by itself. So let's do it again. Let u equal to the square root of x minus 1, and then u squared plus 1 is equal to x. Yeah, okay, and then differentiate both sides, you get 2u, and then du is equal to dx. Alright, from here, implement the substitution. The 2 is multiplicative. Let's bring it outside. Inside, we have the x, which is represented by u squared plus 1, right, I think. Yeah, and then we have this, which is just a u. On top, we have 2u du. U and u cancel, and this one is actually nicer than the other one, because this one's just inverse tangent. For this one, yeah, let's just integrate it as it is. So, we're still subtracting. To integrate this, multiply 2 on the bottom and up here, right? So they cancel. Notice that if you let a variable equal to x minus 1, well, that's linear. That means your differential is going to be equivalent 1 over 2 times root of a variable. If you integrate with respect to that variable, what you get is simply root of that variable. And don't forget the 2 on the outside. So 2 times root of x minus 1. And yeah, that's the first part just done. Here, let's work on this. We have 2 times inverse tangent of u, but u is just root of x minus 1. And we still have this right here. Alright, add c, and that's it. I know the past 3 may have been kind of unclear and kind of slow, because I've been hesitant with the approach to these just to make sure I could do it the way I decided to, but that's these 3 done. Next one is kind of a break. Alright. Next one is number 30. We have integral of cosecant 2x dx. There's a short way to do this using what we know, and there's a long way to do this. However, I'm pretty sure you actually come to different results depending on which way you do it. So let's do it the long way, because everyone knows the short way is just, well, using the formula, right? Reverse chain rule, you have to divide by 2. I'm going to write this over here. So you have to divide by 2, then you have the integral of cosecant, which is natural log of the absolute value of cosecant 2x minus cotangent 2x, like that. So that's the easy way to do it. The more difficult way is to change this into 1 over sine of 2x dx. And this becomes 1 over, integral. And then there's, move a 1/2 out sign, right, from the 2 sine x dx. So it's 2 sine x cosine x. And inside here, all you're left with is the sine x cosine x part of that. And from here, it's tempting to go backwards, but for now, take my word for it. Just change this one using the Pythagorean identity into a sine squared x plus cosine squared x. And what this gives you is sine squared plus cosine squared over sine cosine dx. Split up the fraction. First one, 1/2. First one of the signs reduces with one of the signs. You're left with sine over cosine, which is just tangent. Other one, the opposite thing happens. And, first of all, let's put down the 1/2. One of the cosines reduces with the only cosine. You're left with cosine over sine, which is cotangent. And I find that symmetrical pretty satisfying, I guess. Integral of tangent is natural log of secant. Integral of cotangent is natural log of sine, as far as I know. Don't forget the 1/2, of course. Yeah, because the top is the derivative of the bottom. Yeah, okay. From here on, we can combine these two. Secant x times sine x. Well, secant x is 1 over cosine, so you get sine x times 1 over cosine, sine over cosine, tangent. Don't you find this interesting? I'm not sure if they're off by a constant or not. That wasn't my job for today. So I'm going to add a C on both. But since this one is cuter, I'm going to box it. But I mean, I guess I can box that one as well. This one comes straight from the formula. And you might be able to weasel your way from this into this guy right here through like identities and stuff. But yeah, I mean, they're both, I guess, valid answers. I don't know if anyone actually expects you to simplify that. Okay, that's number 30. Ooh. All right, next up we've got number 31. 31. Integral of secant x dx. And this is our last easy one. There are 4 ways to do this. Ooh, boy, do I not want to do any of them. Because this one's so standard, we've done it like 20 times before. Everyone knows this is equal to the natural log of absolute value of secant x plus tangent x. Plus, right? This is formula. This is standard. What else can we do to this though? Well, okay. Here's what I'm going to do. I'm going to write this as 1 over cosine. And then let's multiply cosine on both of them on the bottom. Because if you remember integrating hyperbolic secant, then that's the strategy we did. We turned it into 1 over cosh. We multiply cosh on the top and the bottom. So why don't we do that here too? Multiplying a cosh on top. No, sorry, not cosh, a cosine, because we're working with normal trig functions. On the bottom, cosine times cosine, cosine squared is equal to 1 minus sine squared. Okay. From here, make a substitution. Let u equal to sine x. and differentiating both sides, du is equal to cosine x dx. And this means integral of the top, our du, over 1 minus sine squared. Of course, sine is u, so u squared. And this right here, this is the standard form. If you have 1 minus u squared, of course it's a difference of squares, and you can take the negative and do what we did earlier with the 1/2 natural log of x minus 1 over x plus 1. However, this one is, there's two ways of expressing it depending on the domain. But typically people use inverse hyperbolic tangent. But just know, based on domain, you're able to also use inverse hyperbolic cotangent. But for this one, let's use inverse hyperbolic tangent. And of course, argument is u. Okay, but then write it in terms of x again. U is equal to sine x. So we get inverse hyperbolic tangent of sine x. And add c. This is pretty cool. This and that are actually equivalent. Black pen, red pen, maybe a couple of other people have made videos changing, pretty sure it's this function to that function, and showing that they're equivalent. That's number 31 though. Alright. Oh my god. Alright, the next one is, well, something. We've worked our way into a world of integrals that I'm not sure are elementary. Well, I mean, they are technically elementary, but without any special like substitutions or tricks, you might not be able to find the antiderivative, and it's this one right here. Doesn't look too intimidating at first, but then you realize that you can't get anywhere with this. So, what do we do? Don't multiply 2 minus cosine x. That's not going to get you anywhere, since this needs to be a 1 for the identities to work well. Let's use something we call the Weierstrass. A Weierstrass substitution. And I'm going to introduce this like I think Black Pen Red Pen did in this video. It is spelled Weierstrass substitution. And it's just this. If you have a rational expression in terms of sine and cosine, then I almost just fell. Then what you do is you would let t equal to tangent of x over 2. And I'll show you how this works. Now, you can pull a bunch of triangle shittery, right? However, the point is to get you a nice value in terms of sine and cosine. So, here, if I remember correctly, do I remember correctly? Allow me to check. I wrote it on the back of this paper that I am putting these integrals from. Okay. Alright, so I think I do remember. This implies that sine x, in terms of t, is 2t over 1 plus t squared. Cosine x is 1 minus t squared over 1 plus t squared. And then finally, this is designed to work in terms of sine and cosine only. So, you can theoretically define other trig functions, including secant, tangent, all the other ones. But these are the two most important ones, right? And then you have your differential dx, because these are explicitly in terms of t. This is x in terms of t. Dx would be equal to, what was it? 2 over 1 plus t squared, I think. dt. Allow me to check this. And it looks right, so yeah. Let's use this in there, because this is a rational expression in terms of sine and cosine. So, this would be equal to the integral of in the bottom, you have 2 plus cosine x. However, 2, we'll just keep it like that. Cosine, we're going to use the Weierstrass substitution. Cosine is that thing. So we would write down 1 minus t squared over 1 plus t squared. All right, and then on top, we still have a 1. Then we want to replace our dx with this differential right here. And I'm going to move the 2 outside, right? Because it's multiplicative across everything. And I'm going to keep the 1 over 1 plus t squared dt. First of all, notice if you distribute this into the bottom, this and that cancel. However, with the caveat, because this also distributes into the 2. So what we get is 2 times that, 2, and then add 2 times that, plus 2t squared. So that's this distributing to that. And secondly, it cancels with this this like complex fractions denominator. So all we're left with is the 1 minus t squared. How we still have a 1, here we still have a dt. Here and here, 2 plus 1 is equal to 3. Combine like terms, you know. 2 plus 1 is 3. 2 minus 1 is just normal 1. So 3 plus t squared dt. Okay, and here we use inverse tangent property. So the 2 stays outside. We multiply by 1 over square root of this. And then inverse tangent. And then we have our variable over square root of that. Okay, and we're almost done. Now we just need to go back in terms of x. And this is nice because t is explicitly defined in terms of x. So here we got 2 over root 3 inverse tangent of t is tangent of x over 2. So I'm going to write the 1 over root 3 as a multiple outside of that. And here we have tangent of x over 2. And yeah, that's really nice. Feel free to look up how that's defined. However, that's not my job today. My job is just to get through all 100 of these integrals. Yeah, but keep these 4 in mind, right? Okay, so that's it for number 32. However, there's a few more that we can use to do, well, a few more we can use Weierstrass substitution on. Next one is, well, let me erase this one first. Number 33. Okay, so number 33, we've got integral of 1 over 2 sine x plus sine 2x. Nice, right? Okay, well, first of all, I would expand out the sine 2x, as always. And expand out into 2 sine x cosine x. Alright, on top you still have a 1, then you have dx. You can factor the 2 sine x, and then, I'm not sure if we need to use Weierstrass substitution here, because you might be able to weasel your way into getting a nice answer. From my experience, you can do that, but if you want to practice this Weierstrass substitution, which I guess this is for, since this is absolutely a rational expression in terms of sine and cosine. So here, let t equal to tangent of x over 2. Yeah, and then actually, if we know all this stuff like as a prerequisite, then I don't think it is required for us to list it as long as we know this. Okay, so from here we got, well, I think it's nice if we factor out the 2 sine x, and that would mean we get a 1/2 on the outside too, because the 1/2 also factors out. sine x becomes 2t over 1 plus t squared. And since we factored out and we're left with a 1 plus cosine, then we're left with 1 plus 1 minus t squared over 1 plus t squared. Okay, up on top you have a 1. And then your, what was it called? Your differential is 2 over 1 plus t squared dt. Notice that this guy and this guy cancel, right? And so do this and that. So let's rewrite this. What you're left with is, there's another 2 you can bring outside. So let's take that out. It's this one right here. You have a t in here, and then you have 1 plus 1 minus t squared over 1 plus t squared. So we're dealing with another complex fraction that we have to cancel out. So 1 dt. To do that, multiply in another 1 plus t squared. So here we go. On the top, well, no, let's work on the bottom first. So instead of multiplying into the t, I want to multiply it into the parentheses. So that means each of these terms is going to get a 1 plus t squared. So from here, that means for t, 1 becomes 1 plus t squared. And then for this fraction right here, it cancels. 1 plus t squared, 1 plus t squared cancel. You're left with 1 minus t squared. That also means this right here and that right there cancel. All right, so that's nice. And remember, we multiplied out 1 plus t squared into the bottom, so you have to multiply 1 plus t squared into the top, and you get 1 plus t squared up here. So what are you left with? This one and that one make a 2. You're able to bring that outside, and a 2 in the denominator times 1/2 is 1/4. Up here, you're left with 1 plus t squared over t. So what I'm going to do is I'm going to split this up, because they're both very standard. This one's natural log of t, and this one is, well, you can simplify this down to just t itself, dt. So now let's integrate both of them. 1/4. Let's distribute the 1/4 as well. Integrating 1 over t, you get natural log of t. And I'm going to just place t right back in. You get tangent of x over 2. All right, so that's term 1. Term 2, integrating t, you get, well, 1/2 t squared. 1/2 times 1/4, you get 1/8. And then t squared, t is just tangent, so you get tangent x, and then in the argument is x over 2, since this is from the Weierstrass substitution. And if I check my work, that looks right. So add c. Quick thing to note is that you still do get a very nice solution in terms of different functions, though, because well, yeah, in terms of cotangent and cosecant, if you do the thing where you factor that out and then work completely with the trig only, but this works as well. They're off by a constant. All right, that's number 33. And believe it or not, the first time I didn't actually use the Weierstrass substitution for any of these. So I put myself through a ton of work trying to manually integrate this, and I somehow did it for all of them. Except for the 1 over 2 plus cosine. That one, like, I had to look up the Weierstrass substitution to solve that one. Number 34, 1 over 1 plus sine x plus cosine x dx. All right, another rational expression in terms of sine and cosine. So let's use our identity guy. Well, not our identity. Let's use the Weierstrass substitution. I think for this one, I somehow got the answer without the Weierstrass substitution, but it looks like it has a Weierstrass substitution in it. And I don't exactly remember how I did it. I could try to work that out again. But for now, let's just use the Weierstrass substitution. Let t equal tangent x over 2. Okay, so this would be equal to integral. Let's work on the denominator. 1 plus sine is 2t over 1 plus t squared. Cosine is 1 minus t squared over 1 plus t squared. And then your differential is, well, 2. I'm going to bring the 2 outside. And then up here you have 1. Multiply in a 1 over 1 plus t squared dt. First of all, notice this, and that cancel, and you still have to distribute this into the 1. So that simplifies stuff a lot. Distributing into the 1, you get a 1 plus t squared. And then you still have these other terms. So you have a plus 2t plus 1 minus t squared. On top, you still have just a 1. Here you have a dt. Notice, this and that cancel. And if you make this and that like terms, so you get a 2, then you can factor out a 2, right? And then that cancels with this. So this becomes a 1. So it looks complicated, right? All the stupid cancellations I made, but all you have to realize, you can do the work yourself, boils down to 1 over t plus 1, I think, yeah. dt, which is natural log of t plus 1, which is, and t is tangent of x over 2 plus 1. Yeah, pretty simple using the Weierstrass substitution. Yeah, that's number 34. Let me see if I can figure out how we do number 35. Alright. I probably made notes for these. I'm going to refer back to those really quickly. Okay, number 35. Alright, so this one is integral of sine squared over 1 plus cosine x all squared. So sine squared over 1 plus cosine all squared. For this one, let's just expand the bottom and see how it goes. I think, yeah. Or no, in fact, what we can do is change the top into a 1 minus, I think. Yeah, 1 minus cosine squared. And then over 1 plus cosine x all squared. Because what you can do is you can actually factor this top guy into 1 minus cosine times 1 plus cosine and cancel one of them with the bottom. So what you get is 1 plus cosine, 1 minus cosine, and then on the bottom you just have a 1 plus cosine squared dx. So this right here cancels with this square. Alright, so you're left with integral of 1 minus cosine over 1 plus cosine. From here, you can, I think you multiply in a conjugate of the 1 plus cosine x into the denominator. So you don't need Weierstrass substitution for this. I think if I figure out that I do something wrong, then I'm going to come back and get it. But here, the top is squared because the top is the conjugate of the bottom. Right? Square this guy. And the bottom becomes the difference of squares. So you get 1 minus cosine, but now it's squared, and dx. This is sine squared. Okay. I'm starting to... Wait a second. Yeah, okay. The bottom is sine squared. And let's also expand out the top real quick. So top is 1 minus 2 times this times that. Let me write this in black. And then second one squared. So I don't know why I wrote the square first, but I mean, it works. So the bottom is sine squared. All right, let's break these up. So first term right here, you get what is it? Cosecant squared. Yeah. and this one's standard. This next one right here, you get minus 2. Let's put that down first. Cosine over sine gives you cotangent, and 1 over sine, we have sine squared, so we get to have 2 sines in denominators. So you get 1 over sine times cosine over sine. 1 over sine is cosecant. Cosine over sine is cotangent, so you get cosecant cotangent. And then cosine over sine is cotangent, but it's all squared, so the cotangent is also squared. Okay, real quick. This is cosecant squared minus 1. So what you can do is combine like terms with the cosecant squared. Cosecant squared plus cosecant squared gives you 2 cosecant squared. And then you still have this guy right here. And then you just add 1, right? Because cotangent squared is cosecant squared, minus 1. dx. Alright, finally, treat this 2 as a constant. Integrating cosecant squared, you get negative cotangent. Right? And then integrating negative cotangent, you get normal cosecant. So this becomes an addition sign, and I need the argument, add 2, and then this simply is cosecant. Integrating 1, you get x. So yeah, this is your final answer. If you were to do the Weierstrass substitution, however, you would get 2 times tangent of x over 2, which, I guess it would represent this part, right? Tangent of x over 2, I guess, would just be cosecant minus cotangent. And then the minus x is in both answers. So, plus c. Yeah, but there's still creativity behind rational expressions in terms of sine and cosine without needing the Weierstrass substitution. So, yeah, it's not 100% necessary every time you see a rational expression in terms of those 2 guys. So, that's for number 35. Alright. We're on day 2 of doing 100 integrals. Yesterday, I left off with the trig ones. But now we're going to move on to something completely different. Number 36. Got integral of, x over 1 plus square root of 1 minus x. And there's an x on top. Dx. For this one, let's just try making a substitution for the root, because that typically works out pretty well for us. You can multiply in a conjugate, maybe that would work. Actually, yeah, but the way I did it originally was to make a substitution for the root, and it worked well, so let's do that again. So you'd let u equal to the root by itself. Let's isolate x first, right? So, u squared is equal to 1 minus x. Subtract 1 from both sides. U squared minus 1 is equal to negative x. And then divide both sides by negative. 1 minus u squared is equal to x. From here, we can simply differentiate negative 2u du is equal to dx. Alright, and yeah. So, from here, we can start plugging stuff back in. I have integral. On the top, our x becomes 1 minus u squared. And on the bottom, we have a 1 plus u. Yeah. Additionally, notice that on top, we have, this negative 2u du, the negative 2 is multiplicative, so I'm going to bring it outside. And then we have a u, and then a du. Okay, notice that you can factor this difference of squares on the inside right there. And one of the factors would actually become the denominator. So if we factor it, then we can do some cancellation. this would be in black. 1 plus u du. Alright, and from here we can cancel and cancel. So all we're left with is a polynomial, and that's this right here. So what we can do is distribute the u in, so you get u minus u squared, and then you can take this negative, put it inside, and then reverse the order of subtraction. So instead of u minus u squared, you get u squared minus u. Okay, and then our final step, since it's just a polynomial now, let's do some reverse power rule. Let's put the 2 in as well. So integral u squared is 1/3 u cubed, and then don't forget the 2, so you get 2 times 1/3, which is 2/3 u cubed, minus, and then integrating u, you get 1/2 u squared, and then multiplying the 2 into the 1/2, that cancels, so you're just left with a simple u squared. Okay, and then finally we have u, so we put it back into that form. So right here, you can't do much with the cube, so let's just place u back the way it is. U is root of 1 minus x cubed. Alright, and then right here though, the square root in the u and the square cancel, so you're left with whatever's on the inside. You have 1 minus x, so you're subtracting off 1 minus x. After you distribute the negative, you get minus 1 plus x, and notice that the minus 1 is just a constant, so we can leave that with the plus c. So at the end of the day, this is plus x, I think. And it looks right, so yeah, that's your final answer. Add c and you're done. Now I'm pretty sure you can multiply the conjugate in and you get something even nicer to deal with. Well, this is the way I did it. So, and there's nothing necessarily wrong with it, so yeah. Okay, that's number 36. Number 37, we've got something that looks almost the same. Integral of, however, top is a 1. We still have 1 plus root of 1 minus x squared. And then on top we got a dx. Okay, for this one, it's a different idea since we have a quadratic inside of a square root. Just use some trig sub. And since this is difference of squares and your variables in the second term, you would let sine theta equal to x. What next? Here, differentiating both sides, cosine theta, d theta, that would be equal to dx. So from here, just plug it in. First of all, on top, 1 times dx is just cosine theta d theta. And then secondly, on the bottom, you get 1 plus. Plugging a sine into x, 1 minus sine squared, you get cosine squared. Root of cosine squared is just cosine. So you get cosine over 1 plus cosine. You just learned Weierstrass substitution, right? So it looks tempting, maybe a little bit of fun, but I think plain old manipulation is much better. So the cosine stays, and then you want to multiply into conjugate, right? So you have something to do with it. Yeah, okay. And from here, what you can do is multiply into conjugate on the top and the bottom. And on the bottom, you get 1 minus cosine squared, which is just sine squared, so I'm going to rewrite this as just sine squared. From here, distribute out the cosine into 2 different terms. So cosine times 1 is just cosine, and then you solve it over sine squared. We're also going to split out the fraction. We're subtracting off cosine times cosine is cosine squared, and then this is over sine squared as well. And parentheses d theta. All right. And from here, what we can do is we can break this up into cosine over sine times 1 over sine. Cosine over sine is cotangent, and then 1 over sine is cosecant. So this is integral of, this first one we can rewrite as cosecant theta cotangent theta, yeah? And then this one right here, cosine over sine is cotangent, and then it's squared, so cotangent squared. All right, close the parentheses and d theta. Okay, and from here, this is standard, this is standard. So integrating cosecant theta, cotangent theta, you'd get negative cosecant theta. From here, integrating negative cotangent squared, you get a positive, that's not standard, because this is cotangent squared, not cosecant squared. But it's almost just as easy, because what you can do from here is split this guy into 2. So that's my mistake. First term remains the same. This one you can split into cosecant squared minus 1, distribute the negative, so you get negative cosecant squared, and then minus, but negative is positive 1. Alright, now everything is standard. This first one, as we were saying earlier, gives you negative cosecant theta. Negative cosecant squared gives you positive cotangent theta. And then integrating 1 in the theta world gives you theta. From here, backwards into x, and first of all, we can find cosecant by. Okay, I'm wondering if this is really necessary, because notice if we take the reciprocal of both sides, right, basically cross divide, I guess, you get that this is equal to 1 over x. But you know what? I'm going to do it the standard triangle way. And actually, yeah, this is a valid way of making trig manipulations. You don't necessarily need the triangle if you know what manipulations to make the sign to make it this function and that function. In fact, why don't we give that a shot? First of all, for theta, to solve for theta, we just take the inverse sine on both sides, right? So this gives you inverse sine x is equal to theta. Not much you can do with that, so this is our first one. Next, for cosecant, notice that if you take the reciprocal of both sides, you get 1 over sine theta is equal to 1 over x. Notice that 1 over sine is cosecant as well, so 1 over x is cosecant. Alright, so that's number 2. Thirdly, you need this cotangent right here. Cotangent is cosine over sine. And how do we get a cosine from sine? Well, let's start with this. Squaring both sides gives you this. And then let's make them both negative. And then let's add 1 to both sides. Minus x squared. Okay, and from here, you can turn this into cosine squared. And this is still that. Then take the square root on both sides. You get cosine is equal to root of 1 minus x squared. So, sine is that, cosine is this. Therefore, cotangent, which is equal to cosine over sine. Well, cosine is this root right there. And then sine is in the denominator. It's simply x. Okay, and from here, we can just plug and play. So you don't necessarily need the triangle if you have this guy being something that you're able to manipulate. So from here, negative. Cosecant, we said, is 1 over x. And then cotangent, we said, was this right here. Root of 1 minus x squared over x. Theta is your inverse sine, so there's that. And one more thing, I think we can combine these since the denominators are the same. So we get negative 1 plus, and then you have the x. And that looks much better since it looks like the reciprocal of our integrand. So that's pretty interesting. That's it for this one. Alright, that's number 37. Alright, 38, we have something relatively lightweight. I guess it's well, I'll write it and then we'll judge it from there. Okay, number 38, we have a very simple rational expression. You have the integral of 3x minus 2 times x plus 2 over 3x minus 4x plus 2. As a reminder, if it's not a factor, you can't cancel it. So you may be tempted to cancel the x plus 2 with the x plus 2, but notice that the x plus 2, it's not a factor because there's a subtraction going on in the numerator. Of course, if you wanted to split this guy up, then you could cancel it, because then if you only took this part right here, then there's no adding and subtracting going on. So then you'd be able to cancel it, but if it's not, then you can't do that. So for now, let's expand at the top. The bottom's already nicely factored, which is what you want in an integral with a rational expression. All right, for the top, we get 3x minus 2x, which is normal x. Negative distributes onto the 2. And then on the bottom, we still have 3x minus 4x plus 2. And sorry, no, 2 times 2 is actually 4. So this becomes x minus 4. Yeah, dx. Now, you can cancel it since this is a factor in of itself. You can get 1 times that thing. So cancel. On the top you're left with the 1, the bottom you're left with that. The 3 is a constant multiple. Move it outside. So here you get simply the integral of 1 over x plus 2 dx. That's a natural log since the top is the derivative of the bottom, and don't forget the absolute value bars. Add c and you're done. So a nice break from reality, I guess. Whew, okay. The next one's a little bit fancy. Now, we've got integral of, well, this one's number 39 first of all. Integral of sine x plus cosine x over e to the x, dx. For this one, this is an obvious integration by parts case since you're dividing by e to the x, which is just e to the negative x, right, times sine x plus cosine x. And in fact, there is an identity that you're able to pull out from this. Okay, so we have the identity, well, first of all, let's rewrite this. Using the negative exponent that I just mentioned. So we can have this be e to the negative x times this sine x plus cosine x dx. From here, we have an identity that integral of e to the x times f plus df dx, assuming f is in terms of x, and of course we have to integrate with respect to x. This right here is equal to e to the x times f. And then of course add c. Alright, so notice that this looks very similar. Our f can be sine, and then our df dx is cosine. That makes sense. E to the x, e to the negative x. And that's the only difference. So let's make a substitution where u is equal to negative x. And then see where that takes us. So let u equal to negative x. And all this does is it makes the differentials negative, and then dx would be equal to negative du. So yeah, from here what we can do is implement the substitution. Negative is multiplicative, so let's take this outside. And then here now we have e to the negative x is just u. Alright, from here, x is negative u if you just divide both sides by negative, right? So sine of negative u, well, we know sine is odd, so sine of negative u is equal to negative sine of u, right? Right, like this. And then additionally, cosine of x is cosine of negative u, but cosine is even. So cosine of negative u is equal to cosine of u. So yeah. And you can see here that it gives way to a new form, but it's almost the same, where we have the e to the x or e to the u part, and then we have f being cosine, df dx is negative sine. So now we can use this property right here, where this is equal to e to the x times f. So right here, this would actually be, and don't forget the negative, negative e to the x times, and in this case our x is u, we're working with respect to u, times f, which we said was cosine because the derivative of cosine df dx is negative sine. Alright, don't add c yet, we need to rewrite this in terms of x, and u is equal to negative x, so let's just put down a negative x. Negative e to the argument becomes negative x, and then cosine of negative x is, well, cosine's even, so it's just cosine of normal x. This is negative exponent, we can put the e to the x down in the denominator, so we end up getting cosine x over e to the x. Alright, and then add c and you're done. Okay, now I'm wondering if we can try to derive this formula right here. Which, I mean, you could try to derive this yourself. I'm pretty sure this is a relatively simple case. Yeah. Okay, so that's it for number 39. And moving on to the next page of our packet, where we have a familiar looking integral that we also have seen in our previous 100 integrals. Inverse tangent of root u. So number 40, integral of inverse tangent of root x, sorry. Alright, and just like before, that u equal to, wait, I'm not sure if we did inverse tangent of root x or inverse sine of root x last time, but either way, this looks really familiar and we know what to do. We have a root x as our argument, so let's make a substitution for that. Clean it up. Let u equal to root x. U squared is equal to x. 2u du is equal to dx. Alright, and from here, 2 is multiplicative, so we can take it outside. The u du is equal to dx, so let's put down the u here first. And then let's put down our original integrand, inverse tangent of root x, however root x is u. And then we need the second part of our differential, the du. Now, let's do integration by parts. So we can integrate, let's use the di method. Differentiate the inverse tan, and then we would integrate, let's integrate 2u. Differentiating this, you get 1 over 1 plus u squared. And then here, integrating, you get u squared. Multiply the diagonals, and then integrate the rows. Multiplying diagonals, you get u squared times inverse tangent of u. And then here, subtract integral of u squared times that is just u squared over that. Like this. Similar to before, feel free to add 1, right? 1, and then minus 1. So this part right here gives you a big 1. In addition, we can also write this in terms of x. So u is root x squared is just x. And then inside the inverse tangent of u is just inverse tangent of root x. Here, minus the integral of inside, that just gives you a 1, and then the minus 1 over 1 plus u squared is just an inverse tangent as well. So here this remains the same, and then we're able to integrate both of these. So here we get x times inverse tangent of root x minus, well, 1 du is just u. Negative negative makes a positive. Integrating that with respect to u, you get inverse tangent of u. One last step. X inverse tangent of root x. Minus u is just minus root x. And then plus inverse tangent of u is just inverse tangent of root x. And yeah, that looks right. Add C and you're done. Alright, pretty cool. Alright, that's number 40. Alright, and from here, this is actually our last integral, which has an antiderivative in terms of elementary functions, at least until later on where we have Lambert W, the double integrals, but we have a lot of bounded integrals too. Yeah, so say goodbye to your traditional integrals, and let's start using some pretty cool stuff. The sine integral, the elliptical functions, we have, error function, logarithmic integral. Here we go. And we start off with the bang, since, honestly, the first one just absolutely shocked the hell out of me. We got number 41, which is integral of 1 over inverse cosine of x. What the hell? How did you do this? Is this inverse secant of x? No. This one, let's just make a substitution since this is an inverse function, right? So we can let u equal to inverse cosine. And if you've never seen this before, then just note that if you let a variable equal to your inverse function, you're very easily able to separate out your original variable. So if you take cosine on both sides, this implies that cosine u is equal to x. And then differentiating both sides, you get negative sine u du is equal to dx. So you have a u in the denominator now. Alright, so from here, notice that our 1 times dx is just this. So let's bring the negative outside. On top, we can put the sine u, and then to the right, we just have our du. In the bottom, inverse cosine of x is normal u. This is non-elementary. However, we do have a a special function to express this. And it is actually an integral from 0 to, x of that, right? That's the more formal definition, but if we want to simply find an antiderivative of our sinc function, right? Only difference between this and the sinc function is that sinc, it's defined as 0 to be 0. Is it 1 maybe? But regardless, we have the sine integral to define, that is defined for us. So this is negative capital SI of u. So we can put it like this. And then negative SI of u is just inverse cosine. And unfortunately, there aren't any identities that you can rewrite this nicely with. So it's just negative sine integral of inverse cosine x. Add C, and that's it. So yeah, this may be kind of cheating. That's kind of like saying integral of 1 over inverse cosine of x dx is equal to, integral of 1 over inverse cosine of x dx plus c, right? Don't forget that. But, this is a function defined in terms of integral. Natural log is as well. So just because we came up with a function to be able to have some way to express certain, a certain graph, doesn't mean it's cheating. We did that with natural log as well, right? Yeah, that's number 41. And, alright. (42). We got the integral of inverse sine over inverse cosine. looks even more nightmarish than before, and I would have to agree. But recognize that you are able to express inverse sine as a transformation of inverse cosine. And the identity right here is integral of and inverse sine is pi over 2 minus inverse cosine. And there's a pretty cool reason why. So before we move on, because I know this is, very nice looking now, I'd like to explain why this is. And if you draw out the graph of, let's try inverse sine first, then you get something that looks like, it looks like this. It doesn't extend that far. It extends to pi over 2. So this is what inverse sine looks like, right? And the endpoint's right here, just so you know. This is -1, negative pi over 2. Since at angle negative pi over 2, then the output of sine is -1. And out here, same idea. When the output, when the input of normal sine is pi over 2, then the output is simply 1. So you just reverse it since this is inverse sine. And for inverse cosine, you use the same idea. Inverse cosine looks like this. It's defined on the same domain because just like sine, cosine is between -1 and 1, right? So same domain, but it is shifted up because they're in different phases. Cosine is just sine, but phase shifted. All right, from here, this endpoint right here is 1, 0, right? Since inputting 0 into cosine gives you 1. And up here, this gives you, let me think, pi. So inputting pi into cosine, you would get -1, right? -1 pi. All right. And if you remember, a sine and a cosine are the exact same shape, right? They're just translated off a little. That means the inverses also have to be the same shape. And that means that is off by a translation of this. So how do we get from inverse sine to cosine? Well, first, let's see what we did here. We reflected it over the x-axis, since multiplying a negative on the outside of the function flips over the x-axis. So that makes it look like this, right? So, and you can see now that it's oriented the same way as inverse cosine is. It's just that this endpoint needs to be touching the x-axis, and that's what this pi over 2 does. Shifting it up by pi over 2, notice that the absolute minimum is at negative pi over 2. Shifting it up by pi over 2, it is now touching y is equal to 0, and that gives you inverse cosine. So that's where that comes from. So here, all we need to do is, you may have seen this already, split up the fraction and the integral. For the first one, pi over 2 is a constant. Let's bring it outside. And then we're just integrating simply 1 over inverse cosine, like we just did, dx. Second one, minus inverse cosine over inverse cosine cancels to make 1. So we're just integrating dx. All right, this first one right here, pi over 2. Earlier, we deemed that this is negative sine integral. Yeah, negative sine integral. Negative SI of inverse cosine. And the second integral right here, it evaluates to simply x. And that's it, you add c. So I think the most difficult part to see about this is the first step, since we don't typically deal with inverse straight functions a lot when it comes to calculus. So if you're in an integration mindset, it has the ability to make you, how would you even deal with that, right? So that's it for number 42. Number 43, it looks algebraic, so we'll see how this works out for us. Root of 1 minus x to the 4th one. Now, this is actually not elementary, but you're able to use an elliptical integral to solve this, and I'll show you how. The first step is contrary to what your intuition may tell you, since, you're used to it looking like a polynomial inside of a root. You can complete the square, but this is technically already in completed square form. Either way, this is not an elementary. So the first step is to actually break this up, and by factoring. So factoring this gives you 1 minus x squared times 1 plus x squared. And since they're multiplying, you can also split up the root. So root of 1 minus x squared times root of 1 plus x squared dx. And from here, I need to check this really quickly. What you can do is, well, let's focus on this right here. So, because we're more used to seeing this than that, let's let x equal to sine, right, for the trig sub. And then this, whatever happens to it, it'll just happen. So, dx is equal to cosine, and of course chain rule. Alright, from here we go. We get that there's a cosine on top, right? And a cosine. And well, cosine on the bottom, because if you plug sine into this, you get a cosine. So cosine over cosine cancels. To the top, you're still left with the 1. And on the bottom, you get square root of 1 plus sine squared. And you might be looking for identities to deal with 1 plus sine squared. But let me just tell you right now, sum of squares, you can't factor it, so it's kind of hard to find an identity that works well with that. Here's what we do. Remember the elliptical integral of, what was it called, the first kind? I'm not completely sure. But what it is f of x bar m is equal to integral of 1 over root of 1 minus m sine squared x dx. And the reason why it's called an elliptical integral is because it is used, well, it has applications in finding the perimeter of an ellipse, which is notoriously convoluted to try to figure out. So that's it right here. And notice that they're actually in a very similar form. M here would just be -1 since you're trying to subtract, right? So you can make it a double negative and m would be your -1. So, therefore, this would be equal to f of x is, well, your theta, right? Since here your argument is theta, well, your variable is theta, and then the bar m, and we want it to be negative, as I said earlier. M here would just be -1, so -1. Yeah, and from here, what you can do is go back to the x world. Going back to the x world, take inverse sine on both sides. You get inverse sine of x is equal to theta. From here, f of, well, inverse sine of x, and then bar -1. That's your final result. And yeah, I mean, it looks kind of odd. Maybe you're not used to dealing with it. However, I mean, it works, right? So yeah, that's this one, number 43. Yeah, so many more to go. I think the non-elementary ones are interesting since it teaches you how to, well, identify ways to take advantage of new functions. All right. The next one is, well, it's also non-elementary. We'll see how this goes. And I think that this one is particularly pretty when it comes to finding the antiderivative. Number 44. Integral of 1 over root of 1 minus natural log of x. So here, two observations. This is non-elementary because you have natural log of x sitting alone in the denominator. However, as I was saying, if you substitute a root, it looks nice. Substituting a natural log of x, well, your differential, if you think about it, it's just 1 over x dx. You can express x as e to the u, and that also gives you something really, really nice to work with. So let's substitute this entire inside thing and see what our differential pops out as. And in this case, since this is a little bit more complex, I would try to isolate x. So square both sides and then subtract 1, right? Take the negative and then raise it to e. So you get e to the, you subtracted you reverse order subtraction by getting rid of this negative. So you get 1 minus u squared equals to x. Differentiating both sides. Well, first of all, let's break this into using properties of exponents. E times e to the negative u squared. I mean, it looks weird, but it works. Differentiating this, the e stays outside as your constant multiple. Then you want to take the derivative of this, which is negative 2u, and then multiply on the outside, and then the exponential part repeats. And then, oh, don't forget that there's an innermost function since you're not differentiating with respect to anything in particular, so you have to multiply by the innermost function, which is just u. Finally, right here, we can put it back into there. So, here we go. Negative 2e is multiplicative across everything, so I would move that outside and go relatively slowly. You have 1 over u here. And then you have the rest of it. You have u times e to the negative u squared. And then du. This guy and that guy, they cancel because of the identity property of multiplication. And then here you're just left with integral of e to the negative u squared. Now, this may remind you of the Gaussian integral. It's integral from negative infinity to infinity, but that's with bounds. And we're trying to express this as a function, well, the antiderivative of that guy. So we came up with the name. I didn't come up with it. It's defined, this right here is defined as, well, the error function, ERF, root pi over 2 times ERF. And you might see why, because we're normalizing the area under this curve right here. Something along the lines of that, I guess. But this is ERF of u, and then finally we're able to put this back. Also, notice that this 2 and this 2 cancel. You're left with negative e root pi, and then the ERF of u is just square root of 1 minus natural log of x. Alright, and add c, and that's it. There we go. That's number 44. Whoa. How's it going? I didn't provide the sheet of non-elementary, the special functions, but it is on the worksheet, and there's a link in the description to the original video, and in the link, in the description in the video that I linked to, there's a download for the packet that I am currently using. Okay, the next one is kind of odd. Number 45, we have integral of ln x over x plus 1. How do we deal with this? Well, let's try integration by parts, since you're able to integrate 1 over x plus 1, right? And you're able to differentiate ln x. So let's use the DI method for integration by parts. Differentiate ln x, you would get 1 over x. Integrating 1 over x plus 1, you get natural log of, and for integration purposes, I'm not going to include that, the absolute value sign. This times that, and then this times that in an integral. Okay. So from here, what we can do is multiply those. So you have ln x times ln x plus 1, right, minus integral of this times that. So I'm going to put that in the numerator. Natural log of x plus 1 in the numerator. And in the bottom here, I think we should put this fraction bar in red. We have x dx. Alright, and now it's time to look at the form for another special integral, which I still need to refer to the cover sheet for. And that is the logarithmic, well, I'm not sure exactly what it's called, but it has a special notation to it. Basically, if you integrate natural log of 1 minus x over x dx, the worksheet just fell. This is equal to our special function li2 of x. So just keep that in mind. I'm gonna do that. Alright, so how do we achieve this form from there? Well, notice that this is almost the same. It's just that this x needs to be a negative variable. So let's let u equal to negative x. Du would be equal to negative dx. And the negative du would be equal to dx. So here we go. And also, well, we have x by itself. Well, I mean, we can just move this down here like that. So we don't need to mess around with this. All right. So what this does is let's rewrite our first term, ln x times ln of x plus 1. All right, and then for this integral right here, I'm going to put this down. We have natural log of x plus 1. However, x is now negative u, right? Yeah, I guess this was necessary to put down. X is equal to negative u. So this is 1 minus u. Additionally, the bottom right here, negative x is just u, so we can put that down like this. And one last thing, dx is equal to negative du. So because the negative is multiplicative and it's just represents a constant, I'm going to move it outside. So this is now subtraction, and then du. All right, and from here, we get ln x, ln of x plus 1, and then subtract. This thing is just, well, it's in this exact form, so we have li2 of x. This is actually negative li2 of x. Yeah. All right, so from here, this becomes, the minus sign stays, right? But then we have a negative li2, so I'm going to make this a positive since negative makes a positive. This is li2 of u, which is just negative x. And that's it for this one. So more special functions. Yeah, that's number 45. All right, and for number 46, we have more special integrals. I'm pretty sure this goes all the way until question number 60. All right. So, 46. Sine of x squared over x squared dx. Notice that you can differentiate the top, integrate 1 over x squared. Maybe that'll give us something better to work with. So differentiating sine of x squared, you get, 2x on the outside because of chain rule, and then cosine of x squared. Integrating 1 over x squared, you get negative 1 over x. Multiply diagonals, integrate rows. So multiplying diagonals, you get sine of x squared, negative, right, from here, sine of x squared over x. Negative makes a positive, so I'm going to put this down. The 2 is a constant multiple, I'm going to put that outside. And then multiplying this and that, the x and the x cancel, so you're left with the integral of cosine of x squared. And this, of course, is non-elementary. Okay, for this one, we have a special integral representation of this. We know that integral of, let me check the formula sheet actually, because there are a lot of, derivations that you might need to use. We have cosine of x squared is equal to root of, let me put this down first. root of pi over 2. So the error function, we have the root only over the pi and not over the 2. So take note of that. And I think this is also because of some area elements, because area under sine of x squared is something along the lines of that. Or maybe not. Regardless, I mean, that's the fact. And then we have c, uppercase C of root of 2 over pi times x. Don't question the notation, and these are the constants that we have to multiply in. So let's do that right here. First term remains the same, negative sine of x squared over x squared plus 2 times, and this part, the integral of cosine x squared dx, is equivalent to that. So we have root of pi over 2 times c of root of 2 over pi times x. And our variable here is x, and we're almost done. Notice that the 2, you can express it as root 4, and you can combine these. So 4 over 2 gives you a 2 in the numerator, so you can rewrite this as negative sine of x squared over x squared. Sorry, no, this isn't squared. My apologies. And then plus, this becomes the root of 2 pi. And then multiply by your special function, c of root of 2 over pi times x. And yeah, that's it. This is the result of that integral. Okay, so, I mean, I guess you could say the difficulty is increasing. But, I mean, not as much if you just know the formulas for these. So, yeah, that's number 46. Okay, for number 47, we have sine of 1 plus e to the x. Number 47, yeah. And now you want to make a substitution, but that leads you down a dead end. Like, it looks very, very promising, but I'll just tell you that it leads you to a dead end, and there's not much you can do. I would much rather deal with sine of e to the x by itself, so we don't have an additive argument to deal with. And so yeah, let's make a substitution. Well, not substitution. This is a sine. We have an angle addition formula, so we can break it up, right? Breaking this up, you get sine of 1 times cosine of e to the x, and you have to add cosine of 1 times sine of e to the x dx. So that is nice. And I think the next step would be to make a substitution. I'm referring to my notes currently. So yeah. Let u equal to e to the x, since, I mean, the argument is e to the x. Taking the natural log on both sides, ln u equals x. Finally, taking the derivative on both sides, du over u is equal to dx. And here, sine 1, well, it's just a constant, so we can keep that there. In fact, why don't we see, let's keep it like this. And then cosine of e to the x is just cosine u plus cosine 1 and then sine u. Close the parentheses, and then you have your differential dx, which is du over u. And now let's distribute this 1 over u out and then split the integral off. So, first integral, it's just this, and then don't forget the over u. Of course, sine 1 is just a constant multiple, so let's bring it outside, right? And then we have cosine of u still, but we distributed the over u, so that's now in here. Plus, similar case here, the cosine is just the constant multiple. Let's bring it outside. We have an integral, and then the sine u is there. Then we distributed in the over u, so that becomes like that, and boom, 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 boom. All right, from here, this is capital CI, similar to which stands for cosine integral. So sine 1 times cosine integral of u. And here, cosine of 1 times sine integral of u. And I think I'm on the right track so far. Right, okay, and then the very last step is actually just to replace the u with e to the x. So u is e to the x. And then same thing with the second term right here, we get cosine of 1 times si of e to the x. Boom. That is your antiderivative of sine of 1 plus e to the x. So yeah, your gut instinct maybe to treat this argument as 1, but sometimes think outside of the box and you get a nice answer, right? Alright. Next, we have sine x ln x, and that one is relatively simple. Since we know how to deal with ln x in an integral, we differentiate it. 48. Sine x ln x dx. Yeah, so as I was saying, differentiate the natural log of x. That means we integrate the sine. Here you go, differentiating, you get 1 over x. Integrating, you get negative cosine. Multiply diagonals and integrate rows. So, the negative in the cosine gives you negative cosine x ln x. But then here, the negative cancel, make a positive, and you have integral of this function times that function. You get cosine x over x dx. Alright, and this is just like we saw in the last problem, it is the cosine integral. So this is plus ci of x, yeah? Add c and box your answer. That's it, you're done. That's number 48. So this one is, relatively speaking, a lot simpler. Okay. Alright. 49. 1 over an ln squared of x. Integral of 1 over ln squared x dx. For this one, what would be the most appropriate technique to use? For this one, so you would make a substitution, because ln x, let's just give it a shot, right? Let u equal to ln x. Put an e in the base on both sides, you get e to the u is equal to x, and then differentiate both sides. E to the u du is equal to dx. Therefore, this is equal to integral of e to the u du. I'm going to put the e to u on top, and then the du on the side. And then on the bottom, ln x squared, that's just u squared. Now you can do integration by parts since you know how to differentiate e to the u and integrate 1 over u squared. So, like this, integrating this, you get negative 1 over u. Multiply, integrate. So, e to the u over u, that's your diagonal. Negative makes a positive, and then you have integral of e to the u over u du. Alright, from here, for this first term, let's write u back as ln x. E to the ln x is just simply x. And then u alone is just ln x. Alright, and with what's going on right here, this is another special integral called the exponential integral. EI, and your argument here would be u. integral of e to the u over u du is ei of u. However, our u is ln x. And there's actually a pretty special property, and I'm not going to fully explain it, but ei of ln x is actually equal to li of x. And by the way, this isn't the li we were dealing with earlier. This is lowercase li. This one is known as the logarithmic integral. And I'm pretty sure it's just that, if I'm not wrong. And yeah, it is. So, this is an important identity. These are both defined in terms of integrals, and if you did the integration, then you would find that this right here is true. And by the way, this function right here is not just defined through this, it is also the integral of, was it ln x? No, yeah, 1 over ln x dx. Right. So that's where this comes from. And if you just did some, well, fundamental theorem of calculus, you can get from here to here. Just add bounds, and that's all. All right, that's it for number 49. Yeah. Okay, so next up we've got number 50. We're halfway through. Number 50 is integral of, 1 over inverse sine x squared dx. Alright, for this one, since you notice that there's an inverse sine, that's your only place where x comes up. So, let's make a substitution. Alright, and then here you differentiate. Well, no, not differentiate. Take sine on both sides. And then differentiate. So you get cosine u du is equal to dx. Alright, from here, this is equal to the integral. Cosine u du is equal to 1 times dx. I'm going to leave the cosine on top and then the du on the side. Down here, you just get u squared. You're able to differentiate cosine and integrate 1 over u squared. So let's use integration by parts. And then what you get is, differentiating cosine, you get sine. Well, negative sine. And then integrating 1 over u squared, you get negative 1 over u. Multiply the diagonals, and then integrate the rows. Alright, and then what you get is equal to, multiply the diagonals, integrate the rows. Notice here there's a triple negative, which is still a negative. And then this is integral of sine u over u du. And this is our good old friend sine integral. In addition, right here, I would like to write this in terms of x again. Notice that this is cosine of an inverse trig function. Meaning there is a better way to express this using algebra. So let's figure out what cosine of inverse sine is. Okay? Let's draw out a right triangle. So if you take sine on both sides, notice that u would be our angle, right? Because argument of sine is typically an angle. And then this is equal to the ratio opposite over hypotenuse, since we're using sine, but it's also x over 1. So x here, 1 here. On the bottom, we solve for it. You end up getting root of 1 minus x squared. So cosine is adjacent over hypotenuse, which is just this over 1. So it's just this by itself. Alright, so for cosine u, we can replace it with this guy right here. And for u by itself, well, we saw that u is equal to inverse sine. So let's place it back. Alright, and then next we have this si of u. And then don't forget that u is inverse sine. So this is si of inverse sine. And there is no, identity for sine integral of inverse sine. It just is what it is, right? So add c and you're done. Alright, So yeah, that's number 50. And I think you are around halfway done with the non-elementary integrals. Okay. Okay, let's keep going. Right now, we're on number 51. And this one is famously non-elementary. Square root sine x. And I'm not gonna lie, it might look pretty hilarious to try to do this to anyone who doesn't have much experience working with these non-elementary integrals. However, this one, it takes some analysis as to what to actually do. Alright, so out of the non-elementary integral forms that we are given, we have one that looks maybe usable. We have another elliptical integral. However, this one is, I'm not even sure of which kind. It's just denoted with the function e. So we know that the integral of square root of 1 minus m sine squared x with respect to x is equal to e of x bar m plus c. What do we do with this information? Well, we see that there's a square root, right? And we have a square root here. We have trig function inside the square root. So what if we worked backwards? So take a look at the radicand. We have 1 minus m sine squared x. If we, let's just take a note of this, right? If we set m to, say, be equal to 2, then you notice that this is actually a kind of cosine double angle identity, right? So, yeah, because if you set m to be 2, then this becomes 1 minus 2 sine squared x, which is equal to cosine of 2x. So if you had cosine of 2x in here, then this is obviously a way to do it. So how do we turn a sine x into cosine of 2 times something? How do we turn a sine into a cosine? There is an identity. And we can do this now because we're working with just one sine here and one cosine here. And at the end of the day, we're still going to be able to make substitutions to make it work. So let's change this into something with the cosine inside of it. So the identity is sine x is equal to cosine of pi over 4 minus x, if I'm remembering correctly. And I think I am. Pi over 2, sorry. Oh yeah, that makes more sense. Pi over 2 minus x. It's shifted by pi over 2 and then reflected over the x-axis. Okay, so what next? We want it in the form of cosine of 2 times x, not just cosine of anything. So, well, I mean, just like I said earlier, when we're dealing with the argument here, since there's only one of them, one cosine function, we can do whatever we want and then just make a u substitution later on. So let's pull a 2 out of these two terms. So we have cosine of 2 times, and then pulling a 2 out, this would become pi over 4, and this would become minus x over 2. So we've got it, and the cool thing is we're able to make a substitution here because this is linear, yeah? And then we can bring it outside, and this will give us our cosine double angle. All right, so here we would want our variable to be that. So let u equal to pi over 4 minus x over 2. du would be, this goes to 0. This is negative 1/2 times x, so it would just be negative 1/2 dx. And then finally, multiplying by negative 2 on both sides, you get negative 2 du is equal to dx. All right, and here, notice that our negative 2 is multiplicative across everything, so we can take it to the outside of the integral, like this. And then we have integral of square root cosine of 2 times, well, in this case, it would be u. Okay, and then from here, what we can, and also notice we have a du instead of a dx. All right, and from here, we see that we can turn this into that, and then this into an integral of that form exactly. So from here, we turn the inside into 1 minus sine squared, 1 minus 2 sine squared u. And from here, we're able to go straight into the integral. Well, this is exactly the same as the integral of this form, so we can use this formula right there. So the negative 2 is going to stay outside. And then this entire integral right here is going to turn into e of u, comma, and in this case our m, right, which is being multiplied onto the sine squared, well, here's a 2, so u bar 2, right. Final thing would be to find what u is in terms of x, and it's just this. So our final answer is negative 2 times e of, open parentheses, u is pi over 4 minus x over 2 bar 2. And add c. Very, very nice and, well, satisfying, I guess. So this is not what you would traditionally expect it to be. Like, you don't do a lot of manipulation. This is relatively contrary to what you would expect out of a trig integral. All right, and that's it for number 51. All right, number 52. We have something of a very similar form, with just inverse sign instead. So how do we deal with this one? Well, if I were to check, I think because this entire integrand right here has a very nice inverse, right? If you let u equal to that, then if you were to square it, right, and then take the sign on both sides, then you get a nice expression as compared to what you have in here. So let's do that. So we made this substitution. Now we need to find our differential. So differentiate with respect, well, just differentiate implicitly. The derivative of the inside is 2u. Let's multiply that on first. Derivative sign is cosine. And then the derivative of u is du. On the right hand side, you just find the derivative of x. Okay, and that's our differential. So from here, what we can do is integrate. This 2 was multiplicative, so I'm going to take it outside. On the inside, you have a u, and then, well, you have the original integrand, which is another u. So you can write this as u squared. And then you have the rest. And then what I'm pretty sure you can do is, well, let me check. So here what we did was integration by parts. However, not in the sense you would expect. We don't differentiate that and then integrate this, since you would get to u times your c integral, which is really, really tough to deal with. So instead what you do is, well, let's drag the 2 inside again, and let's split it up. 2u is nice to differentiate, right? And then we can split the u up into u cosine of u squared. And sorry, in fact, I'm going to take the 2 into here, since you may notice that this actually, if you make a u substitution, this is just sine of u squared, right? And then you have this u over here. So, yeah, we changed up the way we express this. So now we can do integration by parts. You would differentiate one part, u, get 1. And then integrating, you would integrate 2u cosine of u squared. This is the derivative of that, and you can see this is just an effective chain rule. And in fact, you see that this exists here, and it actually came from sine of u squared. So we can do that. And then, so multiply diagonals and then integrate the rows. So multiplying diagonals, you get u sine of u squared minus integral of 1 times that is just that. So integral of sine of u squared. And this thing right here is your s integral. So, if we put this back to its original form, right? Sine of u squared. If you plug in root of inverse sine into here, the root and the square cancel, so you just have sine of inverse sine, which is just x, right? So let's put down the x first. That comes from this factor. Then we have the u, which is just that. All right, and then here we have our integral, which is equal to, I'm not sure if we went over this earlier. I think we should have. Yeah, we did, question 46. But we did the cosine. But here we have the sine version, so, well, I mean, sorry, is this a 2 over pi or a pi over 2? It's a pi over 2. Here it's an s instead of a c because we're integrating sine of u squared instead of cosine of u squared. In here, you multiply by that, and then you have your argument, which is still u in this case. Finally, what you can do is just put u in, right? U is inside of a square root. You can combine the roots, so this is root of all of that crap. So our final answer is about to take shape right here. Constant on the outside stays the same. S of, all right, in here you have the option of multiplying the sine into the square root, and I'm going to multiply into the numerator, so you get 2 times inverse sine x over pi. Add c, and that's it. All right. Yeah, that's number 52. All right, and now let's try integrating some of the special functions. What we can do is number 53. This one is actually pretty interesting. But as a tip, you know how to differentiate the special functions, so always try integration by parts before anything else. So from here, we can try out number 53. Which is integral of ei of x squared dx. And this actually turns out to be another very cool integral. From here, what you can do is integration by parts. Feel free to differentiate this one right here, and then integrate 1 since this times 1 is just the original integrand. Differentiating this, if you recall, the exponential integral, differentiating it, you get e to the x over x. So, however, our argument right here is x squared, so it would be e to the x squared over x squared, right? But you have to multiply by chain rule, and the derivative of the inside is 2x. So this square cancels with that x, and then here we have an x, and this x, the last x right here, cancels with this x. So, you multiply diagonals, right? You get x times ei of x squared, and then you would integrate the row. And if it's not clear, these 3 x's, these 4 technically, because there's 2 down here, all cancel each other out. And all you have left is this minus. You can bring the 2 outside, and on the inside you're left with an e to the x squared. Now earlier we did e to the negative x squared, but what about this one? Well, this one, long story short, we called it the imaginary error function, and it's the same idea as the error function. So, integral of e to the x squared dx is equal to e. And don't forget the constant on the outside. We have root pi over 2 times ERF I, imaginary error function. Because, there's an imaginary number here, that's being multiplied into your x, right? Because if you multiply that in with the normal error function, then you get the imaginary error function, which is that. And then, of course, your argument is just x. I think, at least. Allow me to check. Yeah, that looks right. So, from here, what do we do? Well, this and that are the same, right? So, from here, the first term stays the same. X times ei of x squared minus. We can replace this integral with this right here. Notice the 2 and the 2 cancel, so you're just left with a root pi. And then the function part remains the same. ERFI of x plus c. Yeah. So that's pretty cool. We went from one special integral to another. And box the final answer. There we go. All right, number 54. Number 54 is I think it's relatively difficult. Let me try to figure out how this one would work. Okay, I think I know. So you would make a substitution, right? Well, you know what? Here, let's write this down first. We have the integral of, in the denominator you have 1 plus e to the x. On top you have x. And this is indeed non-elementary. So my first thought would be integration by parts, since you can integrate 1 over 1 plus e to the x, and you can differentiate x. So why don't we give that a shot? And we've actually integrated 1 over 1 plus e to the x. So that makes it easier. Differentiating x, that gives you 1. So all you need to do is integrate 1 over 1 plus e to the x twice. Integrating 1 over 1 plus e to the x, you get... and I think we did this one earlier. If it wasn't earlier, then it would have been in another question. But I'm going to look for it, because I'm pretty sure we did. Okay, if we haven't, it's fine if we work it out again, because this one is actually not the easiest thing to think about. Alright, so the idea is to... Let me think. What would the idea be? Let's make a u substitution. So, let's integrate this bad boy down here. Integral of 1 over 1 plus e to the x dx. And I'm pretty sure we did this one. It was either in this video or the other 100 integrals. Alright, so let u equal to e to the x, right? And then it's easy to find a differential because if you take natural log on both sides and then you differentiate, then you get this. And right, and then you get this integral. This is 1 plus u now. Yeah, this is 1 plus u in the bottom. And then you're multiplying by a du over u. Okay? And from here, what you can do is you can multiply the u in. And you get... Yeah, and you get u squared plus u in the bottom. I think you can do partial fractions, and I'm not sure if the weird factoring method works. I'll give it a shot. But if it doesn't, we're going to come back and do partial fractions. So, from here, what we can do is factor out a u squared from both of these. So, factor out a u squared from the first term just leaves you with a 1, and the second term gives you u to the negative 1. Du. And then what you can do is bring the u squared to the top by making it u to the negative 2, and have it be over 1 plus u to the negative 1. Notice the top is the derivative of the bottom, at least close enough. I think it just needs to be negative, right? Yeah, okay. So let's multiply negative on both the outside and on the inside, and what you end up getting is that this is well, the top is the derivative of the bottom, so there's no need to make a further u substitution. The negative stays on the outside, and this becomes a natural log of the bottom, because the top is the derivative of the bottom. Alright, and from here, you can turn this u to the negative 1 up into 1 over u. And then you can combine these fractions by making this u plus 1 over u, right? We just made the first one u over u and then combined the fractions. So notice that you can actually split this up since this is a natural log of a quotient. So you can split this into negative natural log of u. Well, actually, if you ignore the negative sign, then it would be negative natural log of u since the u is in the denominator. Add another negative sign, double negative makes a positive. So you get natural log of u. And then up here, u plus 1, you just have minus ln of u plus 1. Notice that u is always positive, e to the x, so these are always positive. Alright, and then let's write this in terms of x again. So, plugging in e to the x here, you just get normal x. Plugging in e to the x here, you can't do much about that, so you just minus natural log of e to the x plus 1. And at the end of the day, this is your the result for your integral from the integration by parts. So you're not done. Alright, so you just fill that in. Notice that, well, either way you're going to be integrating 1 times an x minus natural log of e to the x plus 1. So why don't we do this the cool way and just have one more row for integration by parts, right? Since either way you're going to be integrating this expression by itself, since this went to 1, right? Okay, so for this one, first of all, you're able to integrate the x. It just becomes a 1. Yeah? Alright, and then you have a minus natural log of e to the x plus 1. And I'm pretty sure that part is non-elementary. So let me think about what we do. So I think we can try making a substitution, or we could just do integration by parts again, but, well, no, I don't think we can. Let's try an integration by, integrating this x, you actually get 1/2 x squared. That's my bad. Alright, and I'm pretty sure, let's try a substitution. Okay, let's do this over here. So we're trying to integrate just this last term here. And I'm going to put down a negative sign in advance just to remember that we have a negative here. We're integrating natural log of e to the x plus 1. If you do DI method, again, because this is a natural log, what you get back is just that, right? And you would get this times that, which is your original integral. So that doesn't help because you're just reversing what you just did. So I think what you need to do for this one is, I think a u substitution is necessary. Yeah, and not the entire thing either, just e to the x. And let's actually have it be equal to negative u, since, well, let's just try it. Let negative u equal to e to the x. Since this gives us the natural log of 1 minus u that's required for the capital Li2 integral, whatever that is called. So finding the differential, you get negative du is equal to e to the x dx. This is just u, so dividing u on both sides, you get negative du over u is equal to dx. And this is nice because now you have the numerator, and if you multiply in the differential, you have the denominator. So from here, integral of natural log, this first one is negative u, so I'm going to put the 1 down first, and then have it be minus u. Alright, and second of all, we're dividing by u. We have a negative, so I'm going to bring that outside. And then we have the du. This is just, this is the special integral. So the integral alone, without the negative sign, is negative Li2 of u. With the negative, double negative makes a positive. So this is positive Li2 of u. And u is just, well, if you move the negative to the other side, u equals negative e to the x. Like such. And I'm pretty sure there's no identity you can mess around to get this to look any better. So integrating this term right here, you get that. Li2 of negative e to the x. Alright, and there we go. Multiply diagonals and integrate rows. This is just one big integration by parts question. And there's no row to integrate. This went to 0. So our final answer is x times that thing. So we have x minus ln e to the x plus 1. Then we subtract that, right? So we just flip the signs for both of these terms because distributing the negative does that. This becomes negative 1/2 x squared. And this other guy right here becomes a positive. Negative is a positive. Li2 of negative e to the x. And we're almost done. We just have one last step, and that's to distribute out this x. X squared minus x ln e to the x plus 1 plus li2 negative e to the x. Finally, minus 1/2 x squared plus c. That is the antiderivative of this, and it originally didn't look too intimidating, right? It's like, oh, maybe I can figure this out, but then, you end up with that. Regardless, that's it. There's no common terms. Well, actually there is. This x squared up here, minus 1/2 x squared gives you a positive 1/2 x squared. So just doing that real quick, and then rewrite everything else that we have. Add c, and now you're done. Okay. So that's number 53. Pretty cool. And sorry, this is 54. Did I skip 53? No, this is 54. Okay. Alright, and what's the next one? Alright, and yeah, that's number 53. Let's erase the work. But number 54 looks relatively, well, it looks almost the same. So however, we just swapped the places of the e to the x, and this is also number 55. So that's the only difference with 55. However, I think this one is much simpler if you just see what to do. This bottom is linear, and it almost looks like the argument of the exponential function. You just need a plus 1 up there, right? And actually, introducing a plus 1, there's no difference in the actual function itself. You're just multiplying by a constant. Think about it like this. This is the integral of 1 plus x e to the, I'm going to add a 1 up here, right? And then I'm going to subtract it right away. That way, these first two terms and these two terms, we can use the exponential integral. However, we still have this last one right here. And we can break this off as times e to the negative 1. E to the negative 1 is just 1 over e. So it's just this, and then this negative 1 becomes 1 over e. So we can move the 1 over e outside, and then we're left with something that we can do with the exponential integral, because notice, if we just made a substitution where another variable equals to this and also that, then dx would equal, well, the differential would be the same, and then you can just integrate it as such. So the 1 over e stays outside, and then you would have the exponential integral of this right here, x plus 1. And it's actually pretty simple, although non-elementary. Add c. And yeah, that's it for number 55. Okay, and for number 56, I think it looks pretty cool. Alright, number 56, we've got integral of e to the x dx. Don't panic. Remember what we did earlier. We can let e to the x be a variable, and then we've done it like 3-4 times at this point. If you let u equal to e to the x, then this would mean du over u would be equal to x. Figure it out yourself. We've done this like 3 times in the past hour. So from here, what we can do is argument of this first exponential function out here, this base e, right? That's u. So we have e to the u. And this is actually dx, my bad. Now we want to replace the dx with du over u. So if we put down a du over u here, well, we can move the over u to over here, and boom, what do we got? The exponential integral. So this becomes ei of e to the u. Sorry, no. Close. This is not ei of e to the u. This is just ei of u. But then u is what? E to the x. So this is just ei of e to the x. Add 1. No, add c. Why did I say add 1? And that's it for number 56. Alright. So those are a few pretty simple ones to like, just satisfying. And we have another one that's, instead of nested exponential functions, however, we have nested natural log functions. As such. You might be thinking, let's make a u substitution. And I'm going to say, well, hold on to that thought, because you're able to differentiate this just like any other natural log. So let's do this with the di method. Differentiate this, right, and then integrate 1, because multiply 1 into there, and you get the original integrand back. Differentiating this looks kind of tough at first. Well, let's differentiate the big guy on the outside, ln x. Well, ln of whatever is just 1 over that whatever, so there's ln x in the denominator. However, this is the inside function, ln x, and you want to multiply by the derivative of that, so you just get 1 over x. That means there's an x here, down here too. So, and then there's x up here. Multiply diagonals, and integrate the rows. Multiplying the diagonals, you get x times ln of ln x minus integral of this times that. X and x cancel, so you're left with a 1 over ln x inside dx, right? And then finally, this is a special function. This is the logarithmic integral, li. I typically don't curl the l. Li of x, yeah? And if you made a substitution in the first place, that's okay, because you could have gone to this li of x because it would have given you an exponential integral of ln x, and that would have given you this li of x. So either way, you would have gotten this same answer. All right, so that's nice. It's number 57. All right, number 58. Let's straight up just integrate some of the special functions we found. Let's start with si of x. The first one we got familiar with. Maybe there's a chance, but that's the one. It's si of x, yeah. Number 58. Integral of si of x dx. Integration by parts, because you know how to differentiate this, of course, but you don't know how to integrate it. So, differentiating si of x, integrating 1. So, differentiating this, you get sine x over x, since the integral of sine x over x is equal to si of x. Integrating this, you get x. Multiply by diagonals, integrate rows. Multiplying diagonals, you get this times that, x times si of x. Secondly, for the next term, notice that this and that cancel, so you have the negative on the outside, right? You have the integral, but then you just have the sine x left. And of course, integrating a negative sine x, you get a positive cosine of x. And then, yeah, add c, and that's actually this one done. It's not all that bad. The thing with these special integrals is that special function, is that you would use integration by parts. And this one is very nice. Alright, and then we've got number 59, which is almost the same, just missing a letter. And then here, of course, this is not 58, it's 59 now. s of x. Alright, for this one, and yeah, I rewrote it because this is my second take trying to do this, because this one, there are some constants that you have to mess around with and try to get to work. You're integrating this, so let's just set up the integration by parts. Right? Differentiate what? Differentiate this, because, I mean, you more or less know how to differentiate this. Keep in mind that it isn't just sine of x squared, because when you integrated sine of x squared, consider that you had other variables going on, constants being multiplied on. So let's try to figure out what the derivative of this actually is. And let's start off by writing down what we know. We know that the integral of sine of x squared, right, is equal to, and in fact here I'm going to use a different variable. Let's use t. Okay, because we're going to be using x, well, later in a different way. This is equal to root of pi over 2 on the outside. On the inside you have s of, here you have root of 2 over pi, and then multiply by t, yeah? First of all, you have this guy you need to get rid of, right? Because you're trying to isolate s of a variable. So to get rid of this, we want to multiply this by on both the left and the right side. So multiplying the left side by the inverse, you would multiply by this on both sides to cancel with that, right? Okay, and then the constant multiple on the outside disappears, and we just have this one left to deal with. And this one's a little bit more difficult since it's multiplied directly in the argument. So I propose we make a substitution. Let's write x is equal to that, right? Since we have s of x, and if we let x equal to this inside part right here, then we get what we're trying to differentiate, right? So if we let x equal to root of 2 over pi t, well, now, sure, we can do whatever we want on the right-hand side since there's no differential to mess around with, right? What about on the left-hand side? Well, the left-hand side, there is a differential, and, well, we would need to plug in something for t. Okay, so, first of all, let's isolate t so we know what to plug in, right? That's step one. This implies that when multiplying by a root pi over 2 on both sides, like this, well, that cancels with the right-hand side, and you just get t left. So the t in here, you're going to be plugging in this thing for, okay? Second part, you need to find dt. From here, we can just differentiate both sides. And differentiating this, well, this is just linear, so you get your constant right here times the derivative of x, and on the right side you have derivative of t. So now we know what to plug in for this side if we want everything in terms of x, which we do, right? Since that will give us what s of x equals. And then what we can do is we can just differentiate both sides to get rid of the integral sign, and then we also get the derivative of s of x. Okay, so we have a little bit more left. We still have the root of 2 over pi on the left-hand side. And then inside here, we got sine of t squared. T we saw would be this, right? And then squaring this guy right here, it cancels with the square root, so you get a pi over 2. But then the x is also squared, okay? And then finding the dt. Dt is just that, root of pi over 2 dx. So now everything on the left-hand side, it's an integral with respect to x. On the right-hand side is very simple. You just replace the inside, which we set to be x, with just x, right? That's the whole point. Notice this is a constant multiple. This is a constant multiple. They're multiplicative inverses of each other. So this entire thing cancels with that entire thing. You get that integral of sine of pi over 2 x squared is equal to s of x. This isn't the s, this is an integral. Hopefully there's a distinction. Don't forget the dx, which I just did. Alright, and then finally, we're trying to differentiate f of x. So let's differentiate both sides. Differentiating this side with respect to x, you just get the integrand back. So you get sine of pi over 2x squared. That is equal to differentiating the right-hand side with respect to x. You get d over dx of s of x. So we now know what the derivative of s of x is equal to. It's just this right here. So we can plop this in here. Sine of pi over 2 x squared. Of course, we integrating 1, you get x. Okay, and then multiply diagonals, you get x, s of x. And then integrating rows, you would get, well, minus the integral of, let's put this x down first, and then the sine. That was probably the most difficult part of this entire thing, because what we have left is trying to integrate this guy. Now, in here you have a quadratic, so, and the derivative of this inside right here is almost this x dx right out here. So let's make another substitution. Let u equal to pi over 2x squared. Differentiating both sides, you get du is equal to pi over 2. Well, okay, first of all, take the 2 down so it cancels with this 2. So you just have a pi left, and then you have an x. And then the dx, okay? You have the x dx here, no pi, so you have to divide by pi on both sides. So 1 over pi du is equal to x dx. So from here, s times s of x is equal to, sorry, no, not is equal to, minus 1 over pi is multiplicative, so you would take that out here. Integral of x dx is 1 over pi du. We put down the 1 over pi, du comes at the end, and then we have the sine of that. So let's put down the sine. That doesn't change, but the argument does, because we set it to be u. And then, of course, the du, as mentioned earlier, integral of negative sine gives you positive cosine. So almost done. The constant stays outside, however, the negative sign turns into a positive cosine. And then your argument, which is u, is just that. Pi over 2x squared. So this one, it looked just as simple as your SI of x sine integral, but it took a lot more time because we had the constants, and I tried to explain it as clearly as possible, and I feel like, well, I wanted to give an intuition for those who already have some experience working with variables, right? And differentials, of course. That's number 59, and our last, our last normal integration problem is pretty quirky. You've probably seen this function used in algebra. Never, maybe integrated before, but we have number 60, integral of the Lambert W function of x dx. This is the inverse of a function, so let's just make a u substitution. Let u equal to w of x, right? In fact, I'm going to use t. T is nicer to write, and I'm going to be writing that a lot in this case. Let's isolate our x, and x would just be t e to the t, right? All right, now we got to differentiate both sides. Well, on the left-hand side, differentiating t e to the t just gives you t plus 1 e to the t, and then this is equal to, and then we have our dt. And this comes from a formula, but you can also just use product rule, right? And then combine it, and you have the e to the t left. Really doesn't matter. dx. Alright, so from here, what you can do is, notice w of x is just a t, and then dx is just this whole thing. So let's put down t plus 1 times e to the t dt. This is a polynomial, this is an exponential, so let's use integration by parts. So you're differentiating, and let's expand this out so it's easier to think about. You get t squared plus t, integrate e to the t. Differentiating this, you get 2t plus 1, and then differentiating again, you get 2, and then differentiating again, you get 0. Integrating e to the t, e to the t, e to the t, e to the t. You just multiply diagonals. That's all the integration necessary, yeah? And because you hit 0, no more integration. From here, we now have to expand it out. So I'm going to distribute these guys on into the e to the t. So you get t squared e to the t for the and then plus t e to the t for your first diagonal. Second diagonal, notice the subtraction, 2t e to the t. And then distribute the subtraction. 1 times e to the t is just minus e to the t. Here, add 2 times e to the t. Alright, so this one isn't like to anything else. As a result, we're going to just be keeping it. And in fact, I'm going to rewrite it. I'm going to rewrite it as t times t e to the t, because notice that this is just our x. But that comes later, since right now our primary objective is to combine like terms. One of these guys minus 2 of these guys is negative 1 of these guys. So you get negative t e to the t. Alright? So that's it for these two. And then for these two of these guys minus 1 of these guys is just 1 of those guys. So plus e to the t. Okay. Finally, we can replace all of these with in terms of x. T e to the t, notice, is just x. T by itself is w of x. T e to the t is just x. And then e to the t, well, there's multiple ways of expressing this, but you can write this as w of x, sure. E to the w of x, sorry. So that's one possible way of doing this, but it makes many people uncomfortable to see, a w of x in the exponent, right? So what you can do is you can, for this term right here, you can multiply a w of x on both the side, on both the top, right, and the bottom. And notice that wx times e to the w of x just gives you x, because that's a property of inverse functions. So this is really equal to x over w of x. So we are able to rewrite that term as that as well. So you get x w of x minus x plus, you can replace that with this, x over w of x. Add c, and that's your second way of writing this antiderivative. And yeah, that's number 60. That's the integral of the Lambert W function. I think that's pretty cool, especially considering that most people never consider the Lambert W function in terms of calculus. But yeah, that's number 60. Moving on, we've got a lot of, well, different stuff compared to what we've been doing so far. Alright, we're now on day 3 of trying to finish these 100 integrals, well, 100 more integrals from last time, and we're actually more than halfway through, but this is also where it starts to get difficult, right? We're after question 60 now. Let's do number 61. And this isn't just an integral. We want to find p such that integral from 1 to infinity of 1 over x to the p dx converges. So how do you go about thinking about this? Well, there's 2 ways you can find an antiderivative for this guy right here. So you're able to plug in bounds and evaluate. The first one is, well, if p is equal to 1, then you can't use power rule, because then you get 1 over x, and that gives you natural log of x, right? However, if p is any other value, then you're able to use power rule, reverse power rule, to integrate find the antiderivative of this function. So first, let's see what happens when we have p is equal to 1. We get the integral from 0 to infinity of 1 over x to the first power dx. Antiderivative of 1 over x dx is just ln x, and from 1 to infinity. And see here that if you plug in 1, then this becomes 0. And then if you plug in infinity, natural log of infinity, it still diverges. So let's put down this right here. Diverges. Yeah? Okay, so if p is equal to 1, it diverges. So it can't equal 1. So let's try p is not equal to 1, because then we have an abstract, not an abstract, but a case of just reverse power rule. So we have an integral from 1 to infinity of 1 over x to the p dx. And we can just do reverse power rule. So what we get is, this is just x to the negative p, and then we add 1 to the exponent and divide by a new exponent. So we get 1 over 1 minus p times x to the 1 minus p. And keep in mind here that you need to evaluate from 1 to infinity. When you evaluate at 1, if p is any number, then it's going to converge, right? So we don't need to worry about this. Let's worry about the infinity instead. If we have an infinity here, well, we need it such that it needs to get progressively smaller, right? Meaning this exponent right here can't be greater than 0. It has to be less than 0, I'm pretty sure. Right. Because if it's less than 0, then that means that x is now, well, if you can look at it as a positive exponent in the denominator, which is exactly what this case is if p were positive, right? So, yeah, and this means it would get progressively smaller. So that means p has, well, this has to be less than 0. So that 1 minus p has to be less than 0. Add p on both sides, you get, well, p is greater than 1, right? So that's actually your final answer. P just must be greater than 1 for this right here to converge. Alright, next we have number 62, and I'm going to do this down here since it doesn't take too much thought. Let's do the integral from 0 to infinity of sine x dx. This guy right here, the antiderivative of sine is negative cosine. So technically we would have negative cosine evaluated at your bounds, 0 to infinity. We know cosine of 0, however, cosine of infinity doesn't exist. So in fact, this diverges. Even though the area always stays bounded, it's always between either negative 1 or 1, it always diverges. Alright, so let's put out a diverge, well, just div for divergent here. And then, yeah, because it never approaches any single value. Okay. Whew. Alright. So yeah, that's these two. Number 63, we have a improper integral from 2 to infinity of 1 over square root of x squared minus 1 dx. For this one, I think it's a good idea to use trig sub, right? So, in fact, what I'm going to do is I'm going to find the antiderivative of the inside first and then evaluate the bounds. So let's do that over here. Because if we do it right here, then we have to drag the bounds with us, and that gets kind of annoying. So let's just evaluate the antiderivative of it on the side. 1 over the square root of x squared minus 1 dx. This is trig sub. Let x equal to secant theta. And then your dx would equal to secant theta tangent theta d theta. Hopefully you can see that. And then we can plug it all in. So 1 times dx, which is this, goes on top. So I'm going to put down secant theta tangent theta on top. And then d theta on the side right here. Over in the bottom, plug in secant here. Secant squared minus 1 is tangent squared. Root of tangent squared is just normal tangent. So you just get one tangent out of this. This cancels with that, and you're left with the integral of secant, which can be expressed as the natural log of the absolute value of secant theta plus tangent theta. Okay. And from here, our job is pretty simple. It's just to find the value of these trig functions evaluated at theta. And theta is the angle, well, no. Theta, the secant of theta is hypotenuse over adjacent. Our ratio is x over 1, therefore x is our hypotenuse and 1 is our adjacent. Don't forget the right angle here. And then that means on this side we have root of x squared minus 1. Okay, and then finally just go ahead and plug stuff in. So the natural log on the outside stays. On the inside, however, you have secant theta, which is x over 1. So it's just x. Plus tangent theta, and tangent theta is opposite over adjacent, so we just have opposite over, well, it's just square root of x squared minus 1. Alright, so we found our antiderivative, so let's put that over here and plug in bounds. So this is equal to the natural log of absolute value of x plus square root of x squared minus 1 close. And then we want to evaluate this guy from 2 to infinity. So 2, this is bounded. We don't need to necessarily think about what it is, because if you think about infinity, plug infinity into here, well, infinity plus infinity squared, which is still infinity, minus 1, which is still infinity, and then there's a square root over it, which is still infinity. You get infinity plus infinity, natural log of infinity, it diverges. So before we go any further, we already see that this is a divergent integral. Yeah. Alright. But that's number 63. Alright. For number 64, this one is the integral from 0 to infinity of x times e to the negative x squared dx. Okay, for this one, notice that even though this is an improper integral, and it looks kind of, well, I mean, just make a substitution, right? Let u equal to x squared, and then this guy will be our differential. So differentiating both sides, you get du is equal to 2x dx. So you have an x dx, you have a 2, no, you don't have a 2, sorry. You're dividing both sides by 2. 1/2 du is equal to x dx. Alright, and from here, what you can do is, well, 1/2 is multiplicative, bring it outside, integral. Okay, well, this is an x bound, this is also an x bound. So let's figure out the top bound. If x is equal to infinity, infinity squared is still infinity. U is therefore equal to that infinity. 0. 0 squared is 0, u is 0. So, yeah. Alright, and in here, the x dx make up our 1/2 du, so we just have e to the negative x squared. X squared is just u, so it's technically e to the negative u. Du. From here, this is a really easy integral. Well, the 1/2 stays outside. Reverse power rule says divide by the negative. Sorry, not power rule, reverse chain rule. And then you just have e to the negative u, which repeats, and now you're evaluating from 0 to infinity. Notice that, well, maybe I should write this in black. But notice that this infinity right here, if you plug it in, e to the negative infinity, if you look at the graph of e to the x, right, then it looks something like that. This is, as you approach negative infinity, the y value gets closer and closer to 0. So when you go to negative infinity, e to the negative infinity, then this thing approaches 0. So this infinity is empty. Alright, and then you're subtracting off the second bound. So minus, and then negative 1, well, sorry. You're subtracting off this thing evaluated at the second bound, so don't forget that. So when u is equal to 0, e to the 0 is just 1, so you get negative 1/2. So you're subtracting off negative 1/2, which is just positive 1/2. So that's the evaluation of number 64. This integral evaluates to 1/2. Alright, let's see if we have room to do the next one. This is number 64 is just a prerequisite, because number 65 is the main deal. We have the Gaussian integral, and we're gonna derive it. Well, not derive it. We're gonna solve it using polar coordinates, just like everyone else does. So the Gaussian integral is integral from 0 to infinity of e to the negative x squared dx. Okay, this is non-elementary, so you're unable to find an antiderivative that's in terms of standard functions, right? So instead, what we do is the first step is to, well, square this. So you would let this equal to I, because, you know, we want some medium to keep track of it, right? This is just a number. Squaring it makes it such that, well, I squared, you just multiply the integral twice. So we have our original guy, and then we want to multiply it by itself. Okay, but for the guy we're going to multiply in, I'm going to use different variables. I'm going to use y instead, and you'll see y in a second. Yeah. Okay, now, this is valid because recognize that this represents a number. This is the area under a curve, right? And this is the area under the same curve. If you had this be the output, right? Just call the output maybe f. Then, well, it's going to look like that. You're looking for this area under here. So whether you call this axis your x-axis or your y-axis, it means the same thing. Regardless, it's going to be the area under from here all the way out to infinity. So that's how that works. And we can now bring these two integrals together. And then we've got one big integral. So let's do this in the order of dy dx. Okay. So we're going to take this red integral and plop it inside of the black integral. So our black integral comes on the outside. So this is our black bound, and then this is our red bound. Think of it like that. Inside we still have e. When you multiply e to the negative y squared and e to the negative x squared, it's just adding the exponent. So you have e to the negative x squared minus y squared. So e to the negative x squared, and then minus y squared. Then on the inside we have our dy dx. And if you look at this in 3 dimensions, it's symmetric in almost every way you can think about. So you can actually interchange these bounds. However, that's not our main goal. Let's work on the inside first and see what we can do. So this is equal to the double integral from 0 to infinity of e to the, in the roof, well, no, not in the roof. In the attic of e, let's factor out a negative. So you get negative x squared plus y squared. And right here, it's time for us to introduce polar coordinates. Okay. Polar coordinates are basically, if you look at this plane right here as the input plane, because we have two inputs. We have an x input and a y input. They're both inputs, right? And we're trying to look for, well, I'll call this the y-axis and the x-axis. What polar coordinates are is a system of, well, instead of going to this point in the x and then, well, this point in the y, right? Instead of writing this as x comma y, like straight up Cartesian coordinates, what we can do is turn a certain angle from the x-axis, right? So like say this much. Let's call this pi over 4, right? And then we want a certain radius as well. So we rotate angle theta and then we go out a certain radius to reach our point. And because of this, we're going to call our variables x equal to r times, because that's how long it should be, times cosine theta, because cosine gives us the the x like projection, right? And then similarly, y would be equal to r sine theta. And this works well because if you notice this or not, x squared plus y squared, that's just equal to r. Because if you, well, think about it, yeah. X squared plus y squared is just equal to r. How should I explain this? If you just take both of these guys, r cosine, right, square it, and then add r sine, which is your y, and then square it, then, well, r squared, right, you can move this out and actually factor it out, since there's an r squared here and an r squared here, and then you get a cosine squared plus a sine squared. And this goes to 1, so that leaves you with r squared. So this guy right here is r squared, and that makes it much more convenient for us. However, okay. First of all, let's try to find, let's write this down first. X squared plus y squared equals r squared. These are our 3 points. Now, we gotta find what our differentials are equal to. And to do this, we gotta find the Jacobian. Now, the Jacobian is a determinant. So, we have a determinant, and then I'm pretty sure this is partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta. So we're trying to look for the determinant of this matrix right there, because that will give us what our equivalent of dy dx is. And in this case, it would really be dx dy, but as I mentioned earlier, we're free to interchange the bounds if we'd like to, because this is symmetrical. Okay. From here, let's just compute the determinant, right? So we would multiply this diagonal, so you get dx dr, well, partial, right? Because we're working with 2 input variables, so we're looking at a partial derivative only with respect to one variable, treating the other one as a constant. And then we have partial y, partial theta, subtract off this other diagonal, so partial y, partial r, and then partial x, partial theta. So this is taking us from dx dy to dr d theta, right? Because those are going to be our 2 variables that we're going to work with. So from here, I'm going to drag this across right here. Let's compute what each of these are. Well, x is just taking the derivative of this guy with respect to r. Cosine theta would be treated as a constant. So this is just power rule. R goes away and you're left with the constant. So this is cosine theta. And and one more thing I should probably mention, it would be the absolute value of this guy, right? So if there were absolute value to be taken, then the Jacobian is actually the absolute value of this determinant right here. Yeah, anyways, moving on. Partial y, partial theta. Take y and then differentiate with respect to theta. In this case, you derivative of r is a constant, right? So you would just have that stay on the outside, and then derivative of sine theta with respect to theta is cosine theta. Okay, next up, dy dr. So let's take a look at y, but now let's differentiate with respect to r. In the r world, sine theta is a constant and r is a variable. So differentiating that, it would just leave you with the constant. So sine theta. And then dx d theta, differentiating this with respect to theta. R is treated as a constant, move it outside, and then differentiating cosine with respect to theta. We just get, cosine theta with respect to theta, we just get negative sine theta. All right, notice that here, that becomes a positive, and this negative disappears. All right, so from here, let's rewrite these terms. This becomes r, and then there's 2 cosines multiplied together, so this is r cosine squared plus this r on the outside first, and then this sine times this sine. All right, factor out an r, and then cosine squared plus sine squared is equal to 1. So this is simply equal to r. And in fact, this is really saying dy dx is equal to this guy times dr d theta, right? So that distinction is necessary. I should have just multiplied it in the dr d theta to begin with, but just know that dy dx is equal to r dr d theta, right? Typically, you'd include dr d theta. Don't worry, there's going to be more change of bounds going on later. So dr d theta, I should put that down. We're out of room though. So this is r dr. dy dx is r dr d theta. Okay, and just remember this because conversion from these coordinates to the polar coordinates, very, very commonly used. So just remember that your differential, dy dx or dx dy, either way, depends on whether you can interchange them or not. It's going to be r dr d theta either way. All right. So from here, let's keep going. So we're going to have two integrals. Well, the two integral signs. A double integral. On the inside, let's put down what is on the inside first. So we have e to the negative x squared plus y squared. Notice is r squared. We have dy dx, which is r dr d theta. However, now we need these bounds. So the inside integral is for our radius, right? And if you take a look at what we're integrating on, well, from here, x is always from 0 to infinity. So if you look at the x-axis, by the way, this is the entire input plane. We're starting from here and we're going off to infinity, right? And then in our other dimension, right, y, we're also going from 0 to infinity. So we're also sweeping this entire guy up in this direction. So basically, essentially, it's just the entire first quadrant. So in terms of radius, this can go from 0 to infinity, since it can go as far as it can, and then it would still approach our current, these bounds right here. But then theta, on the other hand, it's only going to be on a pi over 2 rotation to sweep across the entire thing. So this is going to be from 0 to pi over 2. All right, so that's how you would think about it. That was kind of a weird explanation. Maybe later we're going to go over some more change of bounds for double integrals, and I'll go over it a little bit better. For now, we actually evaluated this inner integral, the integral from 0 to infinity of r times e to the negative r squared dr. Just that our variable is x. That's why I kept this on here, because the inside just evaluates to simply 1/2. So that gives us a lot of, well, it gets us ahead. So the inside is now 1/2. We still have to evaluate with respect to theta, right? Integrating 1/2 with respect to theta just gives you 1/2 theta. Don't forget to plug in bounds from 0 to pi over 2. Okay, at pi over 2, okay, well, first of all, this 0 is empty, right? Obviously. And then at pi over 2, this is just 1/2 times pi over 2, which is pi over 4. All right, so pretty cool how pi over 4 comes out of that, like full of ease, right? However, notice that this is just I squared because, well, our double integral came from squaring our original integral. So to get back from, let me put this down here, right? Notice that this is still I squared. So to get back from I squared to I, just take the square root on both sides, and you get that this is the square root of pi. Square root of 4 is 2, and that's equal to simply I. So there we go. That is the Gaussian integral using polar coordinates. Yeah. Pretty cool, right? Okay, so that's number 65. That's a famous one. Integral from 0 to infinity of e to the negative x squared is square root of pi over 2. Yeah. And because e to the negative x squared is even, if you went from negative infinity to positive infinity, then you would get, well, double of that, which is just root pi. Okay, that was number 65. Number 66. We have another improper integral. Find p. Yeah, it's another one of those. Such that integral from 1 to e, the improper integral from 1 to e of 1 over x times ln x to the p power dx is, well, convergent. Yeah? Okay. For this one, let's make a u substitution, right? And then we'll see what we get. If we let u equal to ln x, because notice that 1 over x dx is our differential, then you get that, well, differentiating both sides, you get du is equal to 1 over x dx. Yeah. All right. And then that means this is equal to integral from, well, these are in terms of x. So let's plug it into here and then find u. 1, ln of 1 is just 0. So in terms of u, this lower bound is 0. Ln e is equal to 1. So u is equal to 1 for our upper bound. From here, the 1 on top stays the same. And then the ln x, we just replace it with the u. Everything else, the 1 over x dx becomes our du. And don't forget the ln x is to the pth power. I almost forgot about that. Okay, for this, it looks almost like what we were doing earlier, right? We were doing a 1 to infinity of this thing. However, we want this to be convergent now. But the idea, the way we approach it is the same. It has two possible, there's two possible situations. You have p is equal to 1, right? Because then we realize that this is just, you can't use reverse power rule, u to the first, right? Du. This would give you ln u, and then you would need to plug this in from 0 to 1, and obviously ln 1 is 0, and then ln 0, it diverges to negative infinity. Yeah, so this first one here is divergent. And when p is not equal to 1, then in this case, we can use reverse power rule. So we have integral from 0 to 1 of 1 over u to the p du. Alright, and this is equal to, this is u to the negative p. Once again, using the reverse power rule, you get 1 over 1 minus p times u to the 1 minus p. And now you're plugging in from 0 to 1. Okay, so 1, once again, this always converges, right? 1 to any power is always convergent. And then as long as this p isn't 1, which we already tested, then the fraction multiplied in, always going to be defined. So this 1 is fine. What about at 0? Well, only thing we can't have when it's 0 is a negative exponent, right? So when u is equal to 0, well, exponent can't be negative. And that means the exponent can never be negative, since we're always going to be evaluating at 0, right? Regardless of what p is. So this guy can never be negative. So we'll put this down. 1 minus p right here must be greater than 0. Add p on both sides, you get p is less than, sorry, not 0, 1. P must be less than 1. Pretty interesting, yeah? So that's number 66. Alright, and we're not done with the improper integrals. We're far from done. Next up, we've got number 67. Number 67 is the integral from 0 to pi over 2 of tangent x dx. Let's just find the antiderivative and plug it in. Antiderivative of tangent is natural log of secant, and we don't need the absolute value since our domain is always positive and secant in that space is always positive. So from 0 to pi over 2. Alright, plugging in secant of 0, well, secant is 1 over cosine, right? So think of it like this. This is 1 over cosine, which is cosine to the negative 1th power, right? Take the negative outside, then you get negative natural log of cosine. And then now we're evaluating at 0. What was I going to say? Cosine of 0 is just 1. Ln of 1 is 0. So this 0 is an empty 0. What about at pi over 2? So we just are plugging in pi over 2 now. Well, cosine of pi over 2 approaches 0, right? And it's from the positive direction as well. Because if you think about it, we're going from 0 to pi over 2, right? So 0 to pi over 2, we're approaching from the left side. And when we approach cosine at pi over 2 from the left side, right? Notice that we're approaching from the positive direction. So now if you take a, so that's part 1. Now what about the natural log? Well, then this is going to be natural log of 0 from the positive direction. If you take a look at the graph of natural log, well, if you approach 0 from the positive direction, it's going to shoot down, and it's going to end up at negative infinity. So negative infinity is positive infinity. This is divergent. Well, let's write down just positive infinity. This is divergent, yeah? That's number 67. Okay, next we got 68. 68 is, I think it's pretty cool. We have the integral from 0 to 1 of natural log of x dx. It is improper because, once again, if we draw out the graph of natural log like we had here earlier, right, then, well, we're going from 0 to 1, right? So we're looking for this area down here. And it approaches negative infinity, so, well, you might think it's divergent. Well, let's just work it out first and see how that goes. From 0 to 1 of ln x. Maybe we worked this out earlier, maybe we didn't, but, I mean, you know what? Let's work this out again. But, I mean, for advanced integration purposes, this is also pretty standard. An integral of natural log of x. And you derive that from using integration by parts. As such, multiply diagonals, integrate rows. Multiplying diagonals, you get x ln x, right? And then minus integral of 1 over x times x is just integral of 1, which is just integral of dx, yeah? Integrating dx, and don't forget, bounds remain the same for this one, and for this one, the bounds also remain the same, yeah? And then finally, sorry, not x minus ln x, x times ln x. X ln x minus this guy, x. So, and this one's evaluated from the same bounds, so we can evaluate the entire thing from 0 to 1. Okay, well, this one is a little more tough because it's 0 times infinity, negative infinity, right? However, this one right here is a little easier. So let's evaluate the first term first, right? So this is still, you know what, how about let's evaluate at 1, since I noticed that this first term is nice at 1. Okay, let's just do it mentally. At 1, if you plug in 1 to this natural log, that zeroes it out, right? So this first term is 0, and then just plug in 1 to x, you get negative 1. So the 1 evaluates to negative 1. For the next one, you can write it as a limit, right? Since ln of 0, you can express it as a limit. So you're subtracting off the limit as x approaches 0 plus, since that's an important distinction to make when it looks like this, right? It's not approaching it from the other side as well, of this guy. And then plugging in 0 here, well, you just get 0. Subtracting 0 doesn't do anything, so it's just this limit right here. So we don't need these parentheses. All right, what do we do with this one? Well, let's drop the x down twice. So we get negative 1 minus ln x stays on top. Well, we need the limit. The limit as x approaches 0 plus. We have ln x on top, but then we can rewrite the bottom as 1 over x. So now if you plug in 0 plus, this becomes negative infinity over infinity. So infinity over infinity, feel free to use L'Hopital's rule. So from here, we're using L'Hopital's rule. -1 minus limit as x approaches 0 plus of differentiating the top, you get 1 over x. Differentiating the bottom, you get 1 over x, -1 over x squared. Okay. And don't forget the parentheses. Now you can do some algebra because this is now just powers, right? So from here, I'm going to just do this like that because I'm too lazy to rewrite everything. Multiply both the top and the bottom by an x squared. The top, you just get x, and the bottom, everything cancels, except for the negative, so you're going to put that out front, right? And limit as x approaches 0 plus of -x. It's still going to be 0, so this entire thing, well, goes to 0, right? Because all you're left with is that. And therefore, this improper integral evaluates to what's left. So that's just -1. That means this area right here, if that is the graph of natural log of x, is just -1. Alright, the next one's pretty difficult, but I think I know how to do it. And this is actually my first time doing all of these, so if I was a little bad at explaining some things here or there, except for like the Gaussian integral, I guess, or the question we did before that, this is my first time doing any of these questions. Like maybe I have some intuition, but it's less than you would expect. So this next one, I have an idea on how to do it, but I'm not completely sure. Number 69. We have integral from 0 to pi over 2 of 1 plus secant x dx. Notice that this is an improper integral since, well, let's just graph out secant at this point. No more 1 over cosine of bs. Secant looks like this. You have a vertical asymptote at what is it? It's -pi over 2, and then pi over 2, and then from pi over 2 to pi. 3 pi over 2, and then down here is the same, right? So here this asymptote is -pi over 2. Here this is 1, right? +1 right here. That's the y value. And then here you have another asymptote at pi over 2. So if we ever need to do any analysis as to, well, an integral with a secant in it, well, we can just refer to this. And, okay, well, I drew this wrong because these guys never, secant is never equal to 0, if you think about it. So these guys are actually should be below the x-axis. So let's try that again. Yeah, like that. And then here, like that. And then this is -1. All right, so this vertical asymptote is at pi over 2, which is what we have here. However, let's still try to figure out the antiderivative and give this a shot. Okay. What can we do? Well, let's rewrite the secant as 1 over cosine. So you get 0 to pi over 2 of root of 1 plus the secant is just 1 over cosine. Notice that if you wanted to combine the two terms, you can just make this cosine over cosine. And then what you get is integral from 0 to pi over 2 of root of the numerator becomes cosine x plus 1 all over cosine. Alright. Now let's multiply conjugate on both the top and the bottom so that the top becomes sine squared. So you multiply 1 minus cosine on the top and the bottom. You can just flip the orders of addition if it looks better. So yeah, 0 to pi over 2, and then square root of. On top, 1 plus cosine times 1 minus cosine gives you 1 minus cosine squared, which is just sine squared. And that cancels with the root. It becomes simply sine by itself. On the bottom, cosine x, well, you multiply this guy with your, what's it called? Conjugate. Like this. Now you can see we can make a u substitution. So let's do that. Let u equal to cosine. And then differentiating both signs, you get du is equal to negative sine x dx. Here we have a normal sign. We don't have the negative, so let's introduce a negative by multiplying a double negative. One on the outside, one on the inside. All right, from here, let's work out our bounds. So when when x is equal to 0, cosine of 0 is 1. So u would be equal to 1, right? And then when x is equal to pi over 2, cosine of pi over 2 is 0, so the top bound is 0. And feel free to use this negative that we just introduced right here to switch the order of the bounds. So this would now be 0 to 1 instead of 1 to 0. Next, the top, negative sine x dx is just du. And in the bottom, in the root, we have cosine times minus cosine squared if you distribute the cosine in. Cosine, of course, is just u, so you get u minus u squared. Yeah, all right. And now we have something that looks much better, and we can do by completing the square. First of all, in here, let's factor out a negative, all right? And then we have u squared minus u. And to complete the square for this, we want a positive 1/4 in here. That means we also have to immediately subtract 1/4, right? Like this. You can bring this 1/4 outside. This negative makes a positive. So 0 to 1. In here, you have positive 1/4 that we brought outside, and we want to subtract off. Now this becomes a perfect square trinomial, so you can rewrite it as u minus 1/2, all squared. I apologize if I'm writing maybe a little bit small, but... And now you can make another substitution here. So, well, actually, if you made a substitution, then your differential would remain the same. So we can treat this as its own variable. Notice that this is in the form of a squared minus x squared, where a is 1/2. And we worked this formula out in question number 3. This is just inverse sine of, well, x, which is u minus 1/2, over a. So this is actually the inverse sine of x, u minus 1/2, over a. Yeah, and then evaluate it from 0 to pi over, 0 to 1. Okay. This is the graph of secant. Just keep this in mind, right? It's just the reciprocal of cosine. And then from here we can do inverse sine of, this is just the 2. You can bring it up to the numerator by multiplying both the top and the bottom by 2. What you get is a 2, and then distribute it in, you get 2u minus 1. So the argument becomes 2u minus 1. You're still evaluating at the same bounds, all right? So at 1, you get 2 times 1 minus 1, which is 2 minus 1, which is just 1. So you get inverse sine of 1, right? And then you want to subtract off, plug in 0. 2 times 0 is 0. Then you just left with the negative 1. So you're evaluating inverse sine of negative 1. And sine of what is equal to 1? Well, sine of pi over 2 is equal to 1. Alright. And then here, sine of what is equal to negative 1? Sine of negative pi over 2 is equal to negative 1. So negative pi over 2. Negative makes a positive. Pi over 2 plus pi over 2 is just normal pi, so you're just left with pi. So it's not divergent after all. Pretty cool. That Mexican Coke is good. So that's number 69. I want to do, well, I'll do one more. And then I'm going to take a short break. Okay. So these are getting a little more and more difficult. And I think number 70 is the last one we can evaluate traditionally. The last bounded integral we can, bounded, either a definite or indefinite integral we can evaluate traditionally. Not definite or indefinite, sorry. Proper or improper. And this one is actually, let me think about it. Yeah, it's this one's improper. We have 1 to 2 of a rational expression 1 over x squared minus x plus 2 dx. Now this is improper because if you plug in 1 to the bottom, then it evaluates to 0, so you have a vertical asymptote in there. However, let's still work out the math, right, just to make sure. Since previously, like in the last question, we have had vertical asymptotes that are convergent, right? So here at the bottom, this, you might not be able to spot it very nicely, but you can factor it. Factoring this, you get x minus 1. Wait, how would you factor this guy? Did I write down the... Okay, that's why. I flipped these guys. So this is plus 1, minus 2. Yeah, and then plugging in 1 now, that would yield your vertical asymptote. And now you can factor this, and this becomes x minus 1, x plus 2. All right, there you go. And still the 1 on top, and then the dx. Let's do partial fraction decomposition. 1 over x minus 1, x plus 2, is equal to a over x minus 1 plus b over x plus 2. Alright, cover up method, set x to be 1 for the denominator to 0, and then we cover this factor, plug in x is equal to 1, a is equal to 1/3. What about b? Set x to be negative 2 to 0, the denominator, cover out the second factor, plug in negative 2, you get b is equal to negative 1/3. Alright, from here what you can do is go straight back in, but then you can factor out a 1/3. And then you get your integral from 0 to 2 of 1 over, 1 over the first factor, x minus 1. And then, the second one is negative, so you're subtracting 1 over the second factor, x plus 2 dx. And, this comes from the partial fraction decomposition, right? And you see that it's equal to this, and you can bring it down like that. And these are just both natural logs, so that makes our life really easy. First one is natural log of, no absolute value necessary, since these guys are both positive, and when evaluated at x minus 1 and x plus 2, they're still positive. Okay, plugging in 1 here, you get negative infinity. Plugging in 1 there, you get plugging in 1 here, you get ln3, right? And then the 2, it's finite. So if this 1 is divergent, and then this one of the terms approaches negative infinity, the 2 is finite, then in that case, this would be divergent. So this, this approaches negative infinity, and therefore is divergent. Sorry about the factoring, the incorrectly written polynomial earlier on, but yeah, you got it down either way. Alright, that's it for number 70. Alright, and next we have number 71. So for 71, we have an improper integral from 0 to 1 of natural log of x over x minus 1 dx. Okay, and obviously this is non-elementary, so you can't find an antiderivative like we've been doing previously. So what do we do now? Well, first of all, wouldn't it be nice to have just a single variable in the denominator so it's not additive, right? So we can make a substitution. Let u equal to the denominator, and then there's an x here, so let's isolate x to see what that is. U plus 1 is equal to x, and then just differentiating both sides gives you the differentials are equal. We also have to find the bounds, so this is the x bound, 0 minus 1 is negative 1, so we're integrating from negative 1 to, and plug in 1, you just get 0. Natural log of x is natural log of u plus 1. And then in the bottom, we have x minus 1, which is just u. And then du is equal to dx, so we can put that down. All right. So this is still, of course, going to be non-elementary, right? If you have a non-elementary integral, making a substitution is not going to change that. However, what we can do now, we see natural log of u plus 1. It has a pretty nice power series representation. And that power series is the natural log of 1 plus u is equal to, the cap needs to, okay. This is equal to the infinite sum from n equals 0 to infinity of, this is alternating, so it's negative 1 to the n over n plus 1 times u to the n plus 1, right? So it's that. I'm not going to derive it right now because that takes a lot of time, but we can go ahead and replace it with that in the integral because it's nice to deal with. All right, so negative 1 to 0. This 1 over u is not involved, so I'm going to move that outside. And then we have our power series on the inside, infinite sum n equals 0 to infinity of negative 1 to the nth power over n plus 1, and then u to the n plus 1. du. All right, from here, notice that these are just a bunch of terms being added together. If you distribute this 1 over u in, then, well, all of them are going to be divided by u, right? So that has the effect of subtracting 1 from the power. So what this really is the integral from negative 1 to 0 of the infinite sum going from n equals 0 to infinity of, that part stays the same, negative 1 to the n over n plus 1, u to the n. No more plus 1 since we divided everything by u and du. Now let's go ahead and integrate the inside, yeah? We can swap the order of these, and it's not going to be I'm not going to do this as rigorously, but take my word for it. From here, add 1 to the power and then divide by a new power. So the infinite sum stays on the outside. The infinite sum, going from n equals 0 to infinity, of this part doesn't change. So we have negative 1 to the nth power over n plus 1. All right, adding 1 to the power and then dividing. First dividing, we're going to multiply an n plus 1 into the denominator. So that has the effect of squaring it. Secondly, we have u to the n plus 1. Evaluate from negative 1 to 0. So having this be 0, that the entire thing evaluates to 0. So this is empty. So all we're doing is subtracting off this thing evaluated at negative 1. So we're subtracting off this thing evaluated at negative 1. So we're subtracting the infinite sum of n equals 0 to infinity of negative 1 to the nth power over n plus 1 squared, and then plug in a negative 1, you get negative 1 to the n. Negative 1 to the n plus 1 is the same thing as negative 1 to the n times negative 1. So let's have negative 1 to the n and then negative 1, right? And what you notice is that this and that, it's these two factors right here, they're always going to cancel out to be a positive one, right? Since when this is negative, then this is negative. Double negative makes it positive. When this is positive, that's positive, so it doesn't change. So this cancels with that. Since this negative one is persistent in every single term, feel free to factor out of the infinite amount of terms and then cancels with the negative on the outside. So in here, all you're left with is an infinite sum going from n equals to 0 to infinity of 1 over n plus 1 squared. Let's go up here. And that might be looking kind of familiar. If you just shifted this to go from n equals 1 to infinity, then this would be just 1 over n squared, right? And that is a famous infinite summation. So let's go from n equals 1 to infinity. And that has the effect of, from here this would just start at 1 squared, and then, right? So here, if you wanted to start at 1 squared again, you would just need to have 1 over n squared. That's a very rough explanation. Because plugging in 1 gives you 1 squared again. So this right here is famously the, what was it called? Basel problem, was it? But this famously evaluates to pi squared over 6. So this integral is just an integral this right here is an integral representation of the famous Basel problem. The summation from 1 to infinity of 1 over n squared, pi squared over 6. That's pretty cool. So you can box that. Yeah. And we use an infinite sum to get there. Alright. So that's number 71. And number 72 looks almost the same. I'll just drop the eraser. But all we're going to do is flip it. So instead of ln x over x minus 1, we're going to have x minus 1 over ln x. So this is 72. And in here we have x minus 1 over ln x. And this is like kind of hard to spot, but I just remembered. Let's try our first round of differentiation under the integral sign, also known as Feynman technique for integration, but So we would let I as a function of another variable. This is our parameter t be equal to something very similar to this integral. We're going from 0 to 1, but we have x to the t minus 1 over ln x. And so we define a new function. However, notice that this is just a number. And to get this number right here, t would just need to be simply equal to 1, right? Okay, from here, notice that if x to the power of t, reason why we're doing this is because if we differentiate with respect to t, well, we can just differentiate the inside. And what that gives you is, think of it as an exponential function with base x, right? So you get x to the t, ln x, and then it cancels. So that has the potential of giving you something nice. So let's try to differentiate it now. di of t dt, okay? And this would give you, you could differentiate on the outside, but you can also take the derivative to the inside. And I mean, you would need to prove this for this to be more rigorous, but it becomes a partial derivative with respect to t since you're working with two variables, right? And x is not a function of t, so this is going to be a partial. And then x to the t minus 1 over ln x dx. 1 over ln x is a constant, with respect to t at least, right? So all you're really working on is x to the tth power. Now, as I said earlier, let's take the 1 over ln x here, first of all. And then differentiating x to the to the t power with respect to t. That would kind of be like differentiating b to the x with respect to x, right? Since the variable you're differentiating with respect to is in the exponent. So if you differentiate this is going to give you b to the x ln b. So basically, here it's going to give you a repeat, right, x to the t, but then ln of the base, which is x. So, and differentiating the 1, it goes to 0. So here you get x to the t ln x. And yeah, if you could have seen far enough ahead, you could have seen why we did this is because this and that cancel. So you're just integrating x to the t from 0 to 1. And with respect to x. So now, in this state, having differentiated with respect to t, now we can integrate it with respect to x. This is differentiation under the integral sign is basically seeing that, well, you can't integrate in this state, so let's add a variable and differentiate with respect to that variable. Since, with respect to x, it's going to stay the same. Since if you differentiate only with respect to other variable, then you're not changing anything about your current variable that you're working with, right? So you're just putting it in a different form by introducing another variable to differentiate with, and then you can integrate, right? But notice that we are still in the world of di dt. We need to go back to normal I, right? And then we plug in 1 for t. Yeah, and then for that we just integrate with respect to t, and that should be pretty simple. If that was a good explanation, I'm not sure. But yeah, basically idea is put it in a new form by differentiating with respect to a new variable that you introduced. That, and hopefully this new form is easier to integrate with respect to your original variable, and it is. And then later on, you're working with respect to another variable, have it integrate it with respect to that variable so it goes back to being your original form, and then plug in a number for that parameter such that it is now the original integral. And in this case, it would be I of 1. But let's integrate this first. This is power rule, right? Since integrating with respect to x, add 1 to the power and then divide by the power, you get 1 over t plus 1 times x to the t plus 1. And evaluating from 0 to 1, obviously this 0 is going to evaluate to 0, right? What about this one? This one is, well, if you plug in 1 to x, then 1 to the anything is always going to be 1. So this is just equal to 1 over t plus 1. So keep in mind that this is just I prime of t, right? So now we have this. So there's no more x's to work with. So we finished the integration part. And now we need to go back to we need to integrate both sides to be able to go back to I of t to be able to plug it in, right? So integrating both sides with respect to t, integrating this side with respect to t, you just get normal I of t back. And then this is equal to the integral of 1 over t plus 1 dt. And of course there's going to be a constant, but we're going to put the constant here on the right hand side. This is very simply ln of t plus 1. And considering that we don't plug in a negative value for t or a 0, any value that's below, that's equal to or below x negative 1 for t, then we'll be fine. And of course we're going to be plugging in t is equal to 1, so we don't need it. At least for this, right? Okay, and don't forget to add c because you integrated. However, notice that this isn't our final result. This is in terms of t. This right here represents the area under a certain curve. And that is just a number. We have a function, right? To be able to get this function, this back, just notice if you plug in 1 into where t is, so I of 1, right, that gives you x minus 1 over ln x, right? So you're looking for I of 1. However, there's this c right here, and that's kind of bothering me. So let's plug in some numbers and, and try to solve for the value of c. Okay, so from here, let's try I of t equals to 0, right? To try to solve for this value c. So if we plug 0 into where t is, then we get integral from 0 to 1 of x to the 0 is just going to be 1, so you get 1 minus 1 over ln x dx, right? And plugging in 0 equals, this is also an equivalent form of I of t. So plugging in 0 into here, you get ln of 0 plus 1. So this is equal to the other form that we found for I of t, which is ln of 0 plus 1. Well, when evaluated at 0. And then we still have the plus c, which is what we're solving for. Notice that the numerator evaluates to 0, so the entire fraction evaluates to 0. Integrating 0 from 0 to 1 gives you 0. So the left-hand side evaluates to 0. Yeah. And then this right-hand side right here, ln of 1 just gives you 0. So 0 equals 0 plus c. Therefore, c is equal to 0, yeah? So that's now equal to 0. So let's go over here. Let's put down I of t is simply equal to natural log of t plus 1. And now we know that c is equal to 0. So all we're dealing with is just this function right here. Now remember, we can represent our original integral by plugging in t equals 1, right? Think about it. And we see that this right here is actually equivalent to this. So, because they're both I of t, right? So we just plug in I of 1 into here. And you get this is equal to the natural log of 1 plus 1, which is equal to ln 2. And this is the area under that right there. Pretty cool. So yeah, that's the idea of differentiation under the integral sign. It's basically changing your original integral with respect to another variable by differentiating it and then evaluating it with respect to your original variable, because it's probably going to be in an easier form, right? Like this. And then we're going to go backwards so we can have our original function back, but in a different form. So in that case, this form is equivalent to this form, and then we just plug in a number that would make it equal to our original integral. And then we plug it into our new form, which is easier to evaluate, and we get that. So yeah, if that explanation, which I explained like 3 or so times, made sense, then that's good. So because we're going to be using this more from now on. Okay, next one is integral. Well, let's write down number 73. Number 73 is the integral from 0 to infinity of ln x over 1 plus x squared. Okay, so here, what can we try? Well, for this one, you can leverage some symmetry, right? And it might be, this is like the last thing you might notice when just simply observing a function, but I'm going to tell you that it works. So let's make a substitution. Let x equal to 1 over u. Alright? And that means u equals to 1 over x. So there's a nice symmetry going on there. And then differentiating both sides, you get, you want to find dx in terms of u, so let's differentiate the first guy right here. Differentiating x, you get dx. Differentiating 1 over u, you get negative 1 over u squared. And then multiply by du. Okay, so in addition, you want to evaluate the bounds. So let's do that real quick. So this is equivalent to that, so we can plug our x bounds into here to find our u bounds, all right? So we're this 0 right here, since we're integrating from 0 to infinity, well, we can approach it from the right-hand side, right? And that would just be 0 plus. So plugging in 1 over 0 plus gives you infinity for our lower bound. For the upper bound, 1 over infinity always approaches 0. Next, so those are our bounds. Next, take a look at this differential. Take a look at the negative sign. We can use the negative sign to swap the places of these two. And all we have to remember is to not include that negative sign when we actually write it down. All right, next we have ln of x, which is 1 over u, over 1 plus 1 over u squared. And then time for a differential, but remember we used the negative already to swap the places of those bounds, so this is just positive 1 over u squared du. Alright, notice that here you're able to just put the square only on the bottom, so let's do that. Okay, so the bounds stay the same for this next step. Notice that ln of 1 over u is just ln of u to the negative 1. Put the negative out front, so negative ln u over, okay, let's distribute this guy into the denominator. This times that, well, they cancel, so it's just going to be 1. And this times the 1 is just u squared. Well, let's put this in red, since that's typically what I do. And this negative we can actually take outside using the linearity of the integral. But yeah, this is an equivalent form for that, since all we made was some substitutions, right? But the substitution doesn't change the fact that it is still equal. Okay, now I want you to think about it like this. Whatever this graph looks like, we're going from like, we're going from 0 to infinity, right? So we're looking for like this area under here. And well, this is with respect to x, so let's call this the x-axis, and let's call this f of, well, let's just call the output y. Here, well, this is actually the exact same graph, just negative, right? So if you ignore the negative sign, then this part is also the area under this exact same curve. Right? Multiplying the negative in, of course, is going to flip over the x-axis. But my point is that you can call this the u-axis. The area is going to be the same. So if we call this I and call that I, well, so then let integral of 0 to infinity of ln, I'm going to use a variable that we haven't used before just to make it clear that the variable can be anything, since all it represents is just a number, since it's the area under that curve. So let's use t, let ln t over 1 plus t squared dt equal to I. So notice that this is I, and that is I. So on the left-hand side, up here, we have an I, right? And then notice that this is equal to that, this is equal to that. So this is also directly equal to that. This is equal to, there's a negative sign out here, and then we have another I in here, since it's of the exact same form, just the variable slightly different. I is equal to negative I. Adding I on both sides, you get 2y is equal to 0. And then dividing 2 on both sides, you get that I by itself is equal to 0. And I, of course, is our original integral. And that is exactly the number we were trying to find. And we found that it is equal to 0, so let's rewrite this out one last time in a more satisfying form. I, we know, is that, but we can also just replace all the t's here with the x because they're independent of each other, and all it represents is, once again, a number. I'm reiterating this because that's very, very important, right? Like, the variable you use doesn't change what number it is. So I is also that, so let's write that. So you get the integral from 0 to infinity of ln x over 1 plus x squared dx. And keep in mind, all we did was replace the left-hand side with that. The right-hand side is also just a number. So this is your original integral. It's equal to 0. Pretty cool, pretty cool. That is actually really cool. Okay, that's it for number 73. And number 74, Well, now that we've gotten onto the idea of leveraging symmetries, let's try that for number 74 too. Because number 74 is, well, I'm guessing you could probably do it elementarily. Well, it is probably elementary. However, you tell me whether or not you want to do it that way. We have 1 over 1 plus x squared times 1 plus x squared to the 0 to the 2 to the 2. No, this is x to the 2022. Tell me how you want to do this. You want to expand this out? Good luck. You want to do partial fraction decomposition? Good luck. But I'm telling you, we can leverage some symmetries like we did last time, and it'll work out nicely. And we can use the exact same thing. Let u equal to 1 over x, right? X is equal to 1 over u, same idea. And then let's find our differential. So differentiating both sides, you get dx is equal to negative 1 over u squared du. Alright. So now, let's work on the bounds first. These are x, so we plug in x and we want a u out, right? So 1 over 0, this is once again 0 plus, since you're integrating from 0 to infinity, so you're approaching it from the right side, the positive side, which is why it's 0 plus. So 1 over 0 plus is infinity, so we have an infinity on the bottom, and 1 over infinity always approaches 0, which is on the top. Once again, we use the negative from our differential to swap the order. Just remember to not include the negative later on. So we have 0 to infinity again. Alright, and now let's replace all of this with, in terms of u. So we have, this would just be 1 plus, well, how should I write this? 1 over u squared. Then this is 1 plus 1 over, well, no, this should be in red. 1 over u, and it's to the 2022. And then on the right side here, we have our differential. Dx is equal to, well, that thing. But remember, we got rid of the negative, so it's going to be just positive 1 over u squared du. Alright, from here, let's take it slowly because it might be kind of confusing. Let's distribute this u squared into this first factor right here, because they're all multiplying, so you can distribute into one factor. 0 to infinity. All that does, u squared and u squared cancel, and then the u squared times 1 makes just another u squared. So this just becomes 1 plus u squared. Alright, and this term on the right side, no, not this term, the factor on the right side here stays the same. 1 over u to the 2022. And there's just du left. Okay. Here, if we want to get rid of the complex fraction, we multiply both the top and the bottom by u to the 2022. So imagine a u to the 2022 sitting here. We want to take it and multiply it only into this factor. Don't distribute it, right? We multiply it because these two are also multiplied. You could distribute if they're adding, however they're not. They're multiplying. And this is another factor, so you can multiply it into only one of them, right? So this is still integral from 0 to infinity. Multiplying u to the 2022 on the top and the bottom. On the top, you get u to the 2022. Down here you get 1 plus u squared, and over here you get u to the 2022 times this first term gives you a 1. And then multiply it by 1, you get u to the 2022 by itself. Alright. So, just like last time, this is equal to that. Now, they're not the exact same integral this time, right? But that's not the point. The point is to realize that they are equal to each other. So let's call this guy right here I. Well, you know what? No, let's do it like this. So implies, let's put this down here and then the equal sign and then this. Let's write it in terms of x instead. Because once again, just like I mentioned earlier, this is just a number. This is the area from x equals 0 to like infinity of, right, 0 to infinity of the area under this graph. So regardless, it's just a number. It just represents an area. Okay. So whether you call it the u-axis, like we do down here, or the x-axis, like we do up there, it doesn't matter. Sorry, no. Whether you call this the u-axis or, and my previous statement, I take that back because they're not the exact same integral. But if you only look at this one, whether you call this the u-axis, right, like we are doing it right now. We can switch it to be the t-axis if we wanted to by just replacing all of our variables with t, right? It's still the same area, or call it the x-axis if we wanted to, and that's the whole point. We're going to rename this. We're going to replace all the u's with x's. Okay, so implies up there takes 0 to infinity of 1 over 1 plus x squared times 1 plus x to the 2022. And this is equal to integral from 0 to infinity. And I'm going to write this one now. So we have, on the bottom, we have 1 plus x squared times 1 plus x to the 2022. And then on top, we have x to the 2022 dx. Now, okay, so that's cool, and you might see this coming, right? Because if we had just had a 1 plus up here, then we can cancel with this term and then just integrate this. It's just inverse tangent. So what we're going to do is double this, right, by adding this to itself on the left side and adding this to that on the right side. All right? Because, yeah, add this integral on both the left and the right. On the left side, adding this integral to itself has the effect of doubling it. So you get 2 times this integral from 0 to infinity of, well, just all that crap. And then, yeah, dx. And this is equal to, well, ignore the 2. Remember what we did originally. We added this integral on the right and the left-hand side. So let's add it on the right-hand side. Notice that you can combine the integrals since the denominator is the same, the bounds are the same. So let's just combine the integral and then the fraction, right? So all you're really doing is adding a 1. 0 to infinity of 1 plus x to the 2022. And then here we have a factor 1 plus x squared. And then we have a factor 1 plus x to the 2022 dx. All right, and finally, this cancels with that, and we're left with just 1 over 1 plus x squared. Now, our original integral is this. We didn't have the 2, so let's divide both sides by 2 so we get our original integral back. So we get integral from 0 to infinity of all this crap again, 1 plus x squared times 1 plus x to the 2022, 1 and the dx. And then dividing both sides by 1/2, remember, so we do that, and then we do that. And then now this is just 1 over 1 plus x squared dx. Okay, almost done. From here, this is equal to 1/2. Keep the coefficient on the outside, find the antiderivative inside. And an antiderivative is inverse tangent, and then x, right? And then we plug in from 0 to infinity. So 0 to infinity. Inverse tangent 0 is just 0. So we subtract off a 0. So that doesn't do anything. So we're just evaluating at inverse tangent infinity. And the horizontal asymptote of inverse tangent towards infinity, positive infinity, is just pi over 2. So this is 1/2 times pi over 2. Therefore, combining these, you get pi over 4. So pi over 4 represents the area under that curve right there. Yeah. All right. So this is the multiplicative inverse that is commonly used when we're finding symmetries and integrals. But for the next question, let's try the additive inverse, which is just, instead of x is equal to 1 divided by u, let's try x is equal to negative u. And you'll see why. So this is number 75. 75 is the integral from -1 to 1 of sine x. Sorry, no, not sine x. X squared over 1 plus 2 to the sine x. All right, so this is even, this is odd. So if we could do something, using properties of even odd function, and namely, that property is just inputting the negative variable, so x, right? And then we can put in a negative u, and we can leverage some of the properties of these functions, right, using the negative sign. So let's let x equal to u. Negative u. As I was saying, dx just simply be equal to negative du. Okay, so the bounds first. This is in terms of x, right? So plug in -1 here. And -1 equals negative u, divide both sides by -1, you get 1 is equal to u, so therefore the lower bound is 1. And same idea with up here. Plug in 1 up here, 1 is equal to negative u would equal to -1. And then notice this negative in the du, we can use that to swap the order of the bounds. So we go from -1 to 1. And later when we put on the differential, just make sure we don't include the negative and we'll be fine. Alright, next, we have the x squared, which is negative u squared. In the bottom, we have 1 plus 2 to the sine of negative u. And then just du, because the negative we use to interchange the bounds. Alright, this is even. That right there is odd. So what we can do is, well, for the top, negative u squared is the same thing as just u squared by itself, because if you think of it as -1 times u all squared, then you can distribute the 2. -1 squared is just 1, u squared is just u squared. So it's just 1 times u squared, which is just simply u squared. In the bottom, 1 plus 2 to the sine of negative u, well, this is an odd function, so you can take the negative in the argument and then put it on the outside, so you get negative sine of u du. Okay, so what can you do with this? Well, first of all, just like before, I want to write an x in all of these variables. So, yeah, because, it doesn't matter what axis we're working on. It's the same exact graph, and we're measuring from at the same exact bounds, right? So let's replace all the u's here with x's, because it represents the same exact number. This is just a number. So we get x squared over 1 plus 2 to the negative sine x dx. Whew, okay. And then what can we do now? Okay, it was like, let me think. So you can multiply a 2 to the sine x. Oh, right, so here, we're not done yet. Let's multiply 2 to the sine x on the top and the bottom, so we can get rid of this negative exponent. So, -1 to 1, once again, multiplying the bottom by 2 to the sine x, well, this first guy cancels, right? So you just have 2 to the negative sine x plus sine x. The negative sine x plus sine x gives you 0. 2 to the 0 is just 1, so they cancel. 1 times 2 to the sine x is just 2 to the sine x. Alright, now on top. Let's take the 2 to the outside. Well, wait, no, that's not how this works. This is 2 in the base to the sine x. So, of course, we're just going to have to put it down as, well, we said. So, x squared, and then multiply by, we'll multiply on the top and the bottom, 2 to the sine x dx. Alright, now let's add this and that. Because notice, when you add them, there's an x squared in common. You can factor it out and you get 1 plus 2 to the sine x, which is exactly what's in the denominator, right? So, let's add the 2. And because they're equal, well, just like last time, let's just put it down like we did last time. So we got to go from -1 to 1 of x squared over 1 plus 2 to the sine x dx. We know is equal to that. And they go from -1 to 1. So the bounds are the same, so we can add them. The denominators are the same, so we can combine the exponent, because this one's denominator is also 1 plus 2 to the sine x. Numerator is x squared 2 to the sine x dx. So if we add this guy on both the left and the right side, well, on the left side it has the effective doubling. On the right side, we can combine everything. So on the left side, as I said, we have the double of this integral. And then on the right side, since we get -1 to 1. Adding this, combine the integral since the bounds are the same, combine the fraction since the denominator is the same, x squared just ends up here, and then we have our original integral, which is x squared times 2 to the sine x over 1 plus 2 to the sine of x dx. Divide both sides by a 2, and then you're left with your original integral isolated by itself, right? So, here you would -1 to 1, x squared over 1 plus 2 to the sine x dx. Here you have a 1/2. Alright, and then one more thing. Factor out the x squared. So you get x squared times 1, right? That comes from this first term, and then 2 to the sine x. In the second term, over 1 plus 2 to the sine x. Okay, finally, this cancels with that. Yeah, all right. And then, from here we can just straight up integrate. 1/2 times integral. Oh, and also notice that this is really just integral from -1 to 1 of x squared dx, right? And x squared is an even function, so what we can do is multiply by a 2 and then integrate from only 0 to 1, right? Since on both sides the area is going to be the same under the curve, so it's effectively doubling it and only considering what's on one side, because it's the same idea. So we're going from 0 to 1 now. X squared dx. This right here and that right there cancel. This right here, this gives you 1/3 of x cubed. Plugging in 0 is going to give you 0, so all you have is plugging in 1. All right, 1/3 times 1 to the third is just 1/3. So this ends up giving you 1/3. That's it. And there's actually a pretty cool formula for integrals that look like that. And they can all be done using this exact method, using the additive inverse symmetry. So any integral from -a to a, right? These are symmetrical bounds times an even function on top. In this case, our even function is x squared, right? But it can be any even function. And then 1 plus 2, well, not 2, not even 2. It can be any number, any base. 2, not sine either. An odd function, right? And this is important because, first of all, the negative, once you make the substitution, disappears. And the negative in the odd function comes out to the outside, and you can multiply it in something to fix it. This, with respect to x, is always equal to that right here. So instead of going from -1 to 1, we're going from 0 to 1. In this case, 1 is a, so we're going from 0 to a. And then we just have our, even function left. So, really convoluted, but if you see a problem with the structure, keep that in mind, right? So yeah, that's number 75. All right, and next one is number 76, and I'm not erasing anything because it looks very similar. We're just swapping the place of the two functions. So instead of, give me 1 second. Is it 78? No, 76. So instead of 2 to the sine, we have 2 to the x squared, and instead of x squared, we have sine. How do we do this? Okay, so this is odd. This is odd. I did an explainer in how to do this kind of stuff geometrically in my last 100 integrals, the original one. But if you have an odd function on top, and then you divide it by an even function on the bottom, which this is, right? Think of 2 to the x squared as like a parabola being inputted to an exponential function, right? So even though the exponential might not be even or odd, if you input a parabola into this, then it's going to be the same values traced. Yeah, so the shape of the outside function doesn't really matter as long as the inside function is even, right? Then this is also going to be even, right? I'm not going to explain too much about this. However, just know the bottom is an even function, because if it's even and then increasing it by 1, well, it's still symmetrical over the y-axis, so yeah. This is even. Odd over even, as I explained before, and as you might be able to derive, is odd. You can also do the test. So, and we actually didn't do that last time, so let's try it now. So, let's plug in a negative x, right? Sine of negative x is equal to, no, sorry, not equal to, 1 over 1 plus 2 times negative x squared. This negative x squared becomes positive x squared, right? Because the same idea as with the last question, the negative gets negated by the square. You can bring this negative sign outside, so like this, and then sine of x over 1 plus 2 to the x squared. Now the point of this is, remember, an odd function, which is what we're looking for right now since the bounds are symmetrical. Odd function is defined by negative f of x should be equal to f of negative x. And evidently here, that is the case. Since we put in a negative x, where we saw an x here, right, like here, and what we ended up getting out was a negative version of our original. So this is odd, therefore, whole thing is equal to 0. That was a really bad box. Alright, and yeah, that's it for this one. This one's just more symmetry. More symmetry. A lot of symmetry going on. Alright, we have 77. 77, we have an integral with the same bounds, -1 to 1, but we have cosine x times inverse cosine x dx. Okay. For this one, you can try to make a substitution. I'll just tell you that it probably won't work that well. So, instead, what we can do is change this inverse cosine into its counterpart, right? This is an even function times an even function. That doesn't really mean anything. It's another even function, so you still can't determine anything. Of course, you can change this from 0 to, well, like, you can multiply this entire thing by 2 and then change this symmetrical bound to be starting from 0. It doesn't help much because we don't know what it is. So, let's turn that inverse cosine into its equivalent form in terms of inverse sine, because we know that inverse sine is odd. No, actually, is inverse cosine even? I don't think it is. So yeah, that you can't do anything with that. But we can turn it into an odd function, and I think we did this earlier. But inverse cosine is pi over 2 minus inverse sine, and we might have done this the other way around. But regardless, this property, I think it works, right? Yeah, okay, it is. So, now what we can do is distribute this in. So our first one is integral from -1 to 1 of pi over 2, which I'm going to bring outside, times cosine x dx. Next one, you're subtracting off this times that. So integral from -1 to 1, cosine x times inverse sine, dx. All right, so this you're able to integrate. So let's do that real quick. This is pi over 2, and then we have sine. Plug in -1 to 1. Okay. And then this one right here. Cosine is even. Inverse sine is odd. Even times odd is odd, and these bounds are symmetrical. So therefore, this entire thing evaluates to, well, let's not even do that, just 0. Yeah. So all we're left with is this. And we can plug in sine of 1, subtract sine of -1. Okay, so I think the better option would have been to just leverage this evenness and then integrate from 0 to 1 of just normal pi, but and then multiply normal pi, but here there's another way to do this using the odd symmetry, the odd function property. So plugging in 1, you just get 1, right? And then subtracting sine of -1. Now, here, it may not look like you can do much, however, the sine is an odd function. You can take the negative on the inside, plop it on the outside, so this becomes a positive. So this cancels, and this becomes positive. So, all in all, you have sine of 1 plus sine of 1, you get 2 times sine of 1. Cancel the 2 in the denominator with the 2 up here, you get pi times sine of 1. There we go. Add C, and you're done. Yeah. And I forgot to close this guy, so I'm going to do that. Alright. That's it for number 77. Alright, and then we have 3 big boy integrals from here. Let's start off with something relatively lightweight. Comparatively speaking. Number 78. You have the integral from 0 to infinity of sine x over x dx. This right here is the Dirichlet integral. Famously, you can use Laplace transforms. However, fundamentally, where you get the property from the Laplace transforms from is, once again, Feynman integration, or I don't like to call it that, differentiation under the integral sign. So let's do that. Let's define a new function with that is in terms of t, a new variable, right? And it may seem kind of random to choose this at first, but we want to multiply an e to the negative tx dt. This may look like, this is actually exactly what the Laplace transform is. So, you can use either way. Laplace transforms has some nice properties, but then once again, like I said earlier, the properties are derived from this differentiation under the integral sign. Okay, so what you can do now is, so first of all, in order to get from here to here, since this is just a number, right? What number do we have to plug in for t? Well, plug in t equals 0, right? Because then this e to the negative tx thing evaluates to 1, and then it's multiplied with this, so it's just, and this isn't dt, this is dx. So if this thing evaluates to 1, then you're just left with our original integral. So this is equal to I of t equals 1, right? So yeah, let's make sure we get that down before we start the differentiating. All right, now let's differentiate with respect to t to put this thing in a hopefully better form so we can integrate it with respect to x. This implies that, differentiating with respect to t, I prime of t. Once again, just like last time, you can take the d over dt from the outside and put it inside. The sine x over x is not affected by your, it's just a constant if your operator is partial over partial t, because partial derivative, once again, only affects your variable that you're looking at, and anything else is treated as a constant. So now you have partial t, and you're looking at e to the negative tx dx. From here, t is our variable, x is a constant. So if you're differentiating, chain rule says multiply that constant on the side and then repeat the exponential. So we have integral from 0 to infinity of sine x over x. And then this becomes, well, the negative and the x, right? And then you have a repeat. Firstly, this and that cancel. You have a negative still. So let's put that outside. And now you're left with sine x. Well, let's put down the e to the negative tx. Looks kind of intimidating. You can use integration by parts for this. Yeah, let's use integration by parts, sorry. And I'm going to actually integrate a negative there. And then, no, in fact, I'm going to integrate sine x, so that way, because chain rule is typically easier to consider than its counterpart. So we differentiate negative e to the negative tx and integrate sine x. And here, because both functions are repeating like cases, then we're looking for a repeating case. So integrating sine x, you get negative cosine x. Differentiating this with respect to x now, okay, with respect to x, right, since we're solving this integral which is with respect to x. Negative t is a constant, so we multiply that on the side. Negative is a positive, so you're left with a positive e to, well, no, sorry, there's a t down here now that you multiplied on. T times e to the negative tx. No repeat yet. We're looking for, remember, we're looking for something with e to the negative tx times sine x in it. So let's do this one more time. And actually the second row is negative, and then the third row is positive. So, from here, go down again. The t is just a constant on the side. However, you multiply negative t down, so this becomes negative t squared on the side. And then the exponential repeats. Integrating cosine, you get sine. Now you have e to the negative tx and a sine in here. Right? So let's multiply diagonals and integrate our row. So from here, well, you know what? Let's put down an implication symbol. This thing we now know, we did integrate by parts. It's equal to, well, whatever we got for this. So 0 to infinity of negative e to the negative tx sine x dx is equal to this times that. Negative makes a positive, so you're left with just positive e to the negative tx times cosine x. And then second diagonal, negative makes a positive once again. Your t, you can consider it a constant, leave it outside. And then you have e to the negative tx and then sine x. Final row, negative makes a positive. And since you're integrating with respect to x, this t squared that's being multiplied on, you can just bring it outside since it has no x in it. Oh, don't forget the bounds, of course. So these two that are outside of integral, you still have to evaluate from 0 to infinity. And we'll do that in a second. But for now, this. So e to the negative tx times sine x, because the negative we already canceled out, made a positive on the outside. Yeah. And don't forget the bound for the integral stays the same. So we have e to the negative tx sine x dx. All right. So from here, this integral is the same as that integral. So, and there's t squared of these on this side, right? So let's subtract t squared of these integrals on both sides. So on this side, what you get is 1 integral minus t squared integrals gives you, well, 1 minus t squared integrals, right? Then you're integrating from 0 to infinity of e to the negative tx sine x dx. And then right now, what we want to evaluate is this guy right here. Okay, to do this, let's factor out an e to the negative tx. And then we have a cosine x plus t sine x. Alright. And then 0 to infinity. Let's plug in an infinity first, right? So the infinity, when it goes into e to the negative tx, well, okay, first of all, consider that this is always bounded, right? If t is, well, any value of t, any number for t, is going to keep this inside part right here bounded. It's never going to go to infinity. It's always finite. That's the important part. Because if you plug in infinity into here, notice that it approaches 0, right? Since e to the negative infinity is 0. 0 times anything finite is just going to evaluate to 0. So this infinity right here evaluates to 0. Now let's plug in a 0. Well, a 0 into here gives you a 1, right? E to the 0 is 1. Cosine of 0 is pi over... Sorry, no. Wait, no. Cosine of 0, x value is 1, so this is just 1. And then sine of 0 is 0, so this t doesn't matter, therefore this is just equal to 1. Yeah? And, oh, right, also, you're subtracting off this thing evaluated at the second amount. So technically this would be negative 1. Yeah? Is that correct? Okay, I mean, I think so. So this is equal to negative 1, right? Alright. From here, we can divide both sides by 1 minus t squared. Did I get something incorrect? It doesn't look like I got anything correct. You know, I'll stick with it, and then we'll see where it takes us. So, dividing both sides by 1 minus t squared. This is 0 to infinity of e to the negative tx sine x dx is equal to, well, you're just dividing negative 1 by that, so. And the negative, we can use it to reverse the order of subtraction in there. So we just have simply 1 over t squared minus 1. Okay, so now this is equal to I prime of t. Because notice that here we got this guy right here. Wait, hold on. Okay, that's where we went wrong. Okay, this is negative right here. This negative is on the outside, so this would be a negative 1 minus t squared. So this would, so what we did wasn't wrong, it just seemed wrong. Because I forgot there was a negative here. This integral, if you had the negative on the inside, it's not the exact same. They're not the same. This one is the negative version of that. So you can't just do it like that. Let's take the negative outside and have it be negative 1. So negative 1 of these integrals minus t squared of those integrals gives you negative 1 minus t squared as a coefficient on the outside, right? From there, we can divide both sides by that. So the negative 1 is here. And then dividing both sides by negative 1 minus t squared. And then you can see all the negatives just cancel, right? Multiplying a negative 1 to both the top and the bottom, this, that. And this gives you 1 over 1 plus t squared. Alright. Keep in mind that this right here, this is negative that, right? So that means if you take this negative outside, that's what's been causing our problems the entire time. Well, I prime of t is this entire thing, including the negative. This is the negative version of that. So, therefore, this is also the negative version of I prime of t. So, this would be negative I prime of t. And this is equal to 1 over 1 plus t squared. Divide both sides by negative, you get, and I'm going to notate this as di dt. You get negative, negative 1 over 1 plus t squared. And now let's integrate both sides with respect to t to go back to simply I by itself. So, yeah, like this. This dt and that dt cancel out. Integrating di simply gives you I. So, yeah, let's bring this over here. So on the left-hand side, you're simply left with an I of t, remember, the I is a function of t. On the right side, right here, you have a negative, and then integrating this thing, 1 over 1 plus t squared with respect to t, you get inverse tangent of t. And then a plus c. Alright, so now you have that. Let's find out what c is. So let's move this to the top. And yeah. So we have I of t. Right. And remember what we did earlier, we just set t to be any value, since t, well, it can be anything on, well, anywhere it's defined, right? So, because, yeah, we know that this is equal to that. So, t can be anything. T is just a variable. But if we know that this is equal to that, then that means t can be anything and is still equal. Alright, so let's just set t to be something. That'll make it easy for us, right? If we look at I of t, it is also equal to this. So this is equal to that. If we set t to be equal to, say, infinity, well, so not equal to, but approaching infinity, then what you get is that e to the negative infinity approaches 0. So this entire integrand becomes 0. Integrating 0 from 0 to infinity is, well, 0. So on one hand, this equals 0, right? Notice that this, because this is I of t, well, it's also equal to this, negative inverse tangent of t plus c. And plugging in 0 for the inverse tangent, you also get 0, right? And then don't forget the plus c. So I of t where t approaches infinity, is 0 coming from this, and 0 plus c coming from that. So equals 0, which is also equal to 0 plus c. And that means c is equal to 0. So that guy is negligible. Finally, I of t would therefore be equal to be inverse, would equal inverse tangent of t. Alright, and then last step. Earlier we determined that this original integral we were trying to solve is I of t, where t is equal to 1. So let's just plug in 1. Inverse tangent of, wait. 1. Sorry, no, not 1. 0, 0, 0, 0. Alright. Did we get that right? Wait a second. No, we didn't, because we let t approach infinity. We didn't plug in t equals 0. So allow me to try this again. Alright, so starting from here, right? Earlier, the mistake I made was plugging in 0 into here. Earlier we set t to approach infinity. So here, it should also approach infinity, right? My mistake was plugging in 0 here. So this would be equal to negative inverse tangent of, I'm just going to write this very informally, infinity. Negative inverse tangent of infinity would be negative stays on the outside, and then inverse tangent of infinity becomes pi over 2 plus c. Adding pi over 2 on both sides, you get c is equal to pi over 2. So c isn't 0, it's pi over 2. Alright, and from here, we can go on to here. So I of t would therefore be inverse tangent of t, negative inverse tangent of t, plus c, and c is pi over 2, so plus pi over 2. Now, notice that evaluating, well, okay, if you plug in a 0 here, this e to the negative tx thing becomes 1, so you get your original guy back. So therefore, I of t equals 0, I of 0 is equal to your original integral. So here, all you need to do is plug in I of 0. And that would give you negative inverse tangent of 0, which is just 0. So you're left with your constant out here, pi over 2. There you go. Therefore, notice that this is equal to that. Therefore, this is equal to that, right? They're all equal to each other. So, finally, we can say that the integral from 0 to infinity of sine x over x dx is equal to I of t equals 0, right? Which is equal to pi over 2. Done. That is integration by parts. No, not integration by parts. Well, we use integration by parts, but that is differentiation under the integral sign applied. Ooh. Alright. So that's number 78. Really cool. We're going to be using this in the future, so let's make that note. This board looks pretty cluttered, but yeah, I mean, at the end we got to our result. Okay, so I'm going to note down what this integral is equal to because we'll be using it in the future. Note. Integral from 0 to infinity of sine x over x is equal to pi over 2. Notice that this is an odd divided by an odd function that gives you an even function. So if you made the bound symmetrical, since this is currently 0, if you made it symmetrical by saying this is the negative version of the top bound, so negative infinity, this would just be double of this current value. So it becomes pi instead of pi over 2. Right? Yeah. So let's just leave that there. And yeah, that's it for number 78. So this one's pretty tame. Well, I mean, it sets out the fundamentals for what we're about to do. And what we're about to do is simply raise it to a higher power. Number 79. Number 79, we have the same exact idea. This becomes a sine squared and an x squared. Okay, for this one, let me try to remember what we do. Do we do integration by parts? Yeah, because notice how you can differentiate sine squared and you can integrate 1 over x squared, and they all become nicer forms, arguably. So, that's the derivative. Differentiating sine squared, integrating 1 over x squared. Negative, and then power rule first, so you lower the 2, subtract 1, just becomes sine to the first. Derivative of the inside, which is sine, becomes cosine. Integrating this, you get negative 1 over x, right? That, and then like that. Okay, so yeah, from here, I think we can notice that this is equal to sine of 2x. So we're going to be using this. All right, from here, multiply diagonals. You get negative sine squared x over x evaluated from 0 to infinity. Next, we're subtracting the integral from 0 to infinity of this guy right here. So we have sine of 2x and then times this, which is just over this. Oh, and this is actually double negative, so it gives us a positive dx. How would you evaluate this one? Notice that sine squared of anything always stays finite. It's always between negative 1 and 1. If x approaches infinity, then overall it's going to approach 0, regardless of what the top is. The top can be any finite number, and if the denominator approaches infinity, then the whole thing becomes 0. So, this is a 0. Alright, so now, next we have to subtract this function evaluated at 0. And what that is, that's a good question. But subtracting this function, well, there's a negative, so this becomes a positive of just this by itself. So, sine squared of x over x evaluated at 0. So, this gives you a 0 over 0. Use L'Hopital's rule. And I probably shouldn't do that. I should do... Well, you know what? Yeah, that's fine. Let's do this. Use L'Hopital's rule to differentiate the top. Earlier we saw the derivative of sine squared is 2 sine x, well, sine of 2x, right? and differentiating the bottom gives you 1. And you might say this is unfair because typically you can't differentiate sine x. You can't use that L'Hopital's rule on sine x over x because that violates that circular reasoning. However, this is sine squared. I argue we can do that. Probably not, but this isn't used in proving on the derivative of sine, so I argue it's fair. Plug 0 into here, so I'm just going to do that directly. It just gives you 0. Sine of 2 times 0 is sine of 0, which is 0, so not even necessary to write another line. This entire thing just becomes 0. Okay, next, let's focus on this. This almost looks like the Dirichlet integral, right? Here we have a 2x. But remember, let's just make a substitution. Life doesn't need to be hard. Let u equal to 2x. Du equals to 1/2. Sorry, what? 2 dx. So here you have a dx, you don't have a 2, so let's multiply a 2 on the top and a 1/2 on the side, so they cancel to make 1 again. Alright, so from here, we're adding, the 1/2 stays outside, we have 0 to infinity, 2 times dx is your du. So we're gonna put that down later. Okay, you know what, actually, maybe that wasn't necessary, because we have an x down here to work with. So, let's do this in a more elegant manner. This x right here is, if you divide both sides by 2, using that, you get 1/2 u. So this x is 1/2 u. And therefore, in this differential, we can divide 1/2 on both. We can divide 2 on both sides and get 1/2 du is equal to dx. All right. 0 to infinity. Sine of 2x. 2x is u, so this is sine u. Over. Oh, and this is 0 infinity works because, well, if you plug in, these are both in terms of x, remember? If you want them in terms of u, well, just plug them in. 2 times 0 is still 0. 2 times infinity, right, is still infinity. So 0 to infinity. This x is 1/2 u. And on the side here, you have 1/2 du. This 1/2 and that 2 in the bottom cancel. So you just get integral of 0 to infinity of sine u over u, which is, once again, pi over 2. All right, that's number 79. And that, I would argue, is pretty cool. So, yeah, let's move on to number 80. So we saw that squaring this entire integrand still gives you pi over 2. Well, now what if we cube it? What if we cube the integrand? So that would be sine cubed over x cubed. Now this one is a little bit more difficult to do. And we're going to use Feynman integration again, right? Not in the way we originally did it. Here, we're just going to set the argument of sine to be tx. So let I of t be equal to this integral. However, in the argument, there's a tx instead of just an x. And the reason why we couldn't do this originally is because notice if you put a tx in there and you differentiate it with respect to t, yeah, sure, the x would come out as a result of a chain rule. However, when you cancel it, you're still integrating from the same bounds, so you can't integrate with respect to x, right? Since integrating, it would become cosine of tx from 0 to infinity. Well, cosine infinity does not exist. So yeah, that's why we had to do that differently. However, this isn't as direct, so we can still use tx to try to cancel with some of the x's in the denominator. All right, from here, what do? Differentiate, all right? Before we do that though, however, notice that if t were equal to 1, then this would equal to the original one. So this would be equal to I of t equals 1. So keep that in mind. From here, let's differentiate. D over dt of the left sign is equal to, well, you can drag the derivative to the inside again. This 1 over x cubed can stay on the outside. And here it becomes a partial because it's inside of an integral with respect to a different variable. This is respect to t, sorry. And we're differentiating sine cubed of tx dx. From here, well, I mean, this becomes I prime, right? So keep that in mind. But yeah, I'm hoping you would understand. From here, let's differentiate that guy. So, and you can think about it as if it's in the numerator of the x cubed. I moved it outside because, you know, just for the sake of being able to look at that clearer. All right, so put the x cubed in the denominator. In the top, what do you get? Take the 3 to the front, right? So because of power rule, and it gets reduced to a 2, so you get sine squared of tx. Next, take the derivative of the inside function, which is sine of tx. And that is just cosine of tx. Finally, you want to take the derivative of the innermost function, the tx. And remember, this is with respect to t. So t is our variable, x is a constant, so the x gets multiplied to the outside, like this. And in the bottom, we still have our x cubed. Notice that, oh, and we still have our dx. Notice that this x cancels with one of these guys. So we've reduced the power. Next, we have to, how should we do this? Let's rewrite this. 0 to infinity of 3 sine squared of tx cosine tx. Okay, well, I mean, we have sine squared, so do we use trig identities now? I guess we can. Yeah, let's try some trig identities. So, this sine squared right here, we can change it to something equivalent with cosine. So 3 is here, and then this becomes 1/2 times, well, so we're multiplying this in. So therefore, if we have if we turn this into, well, like cosine of, well, 1 minus cosine of 2tx all over 2, then the all over 2 is multiplicative, so we can move the 3 to the outside and the over 2 to the outside. And here you're just left with the 1 minus cosine of 2tx, right? And then you have to multiply this all by your remaining cosine of tx. Don't forget, denominator is still x squared. Alright, and from here, I'm pretty sure you can distribute it out. No, okay. No, that's not the identity we use. We turn this sine squared into 1 minus cosine squared. That's the identity we use. So this becomes 3 times 1 minus cosine squared of tx. Since we want to work with cosines with argument tx, right? And that would make our life easier, hopefully. Here we have a remaining cosine of tx. There we go. I found it. That's why that didn't seem very right. X squared dx. From here, distribute this out, right? So this is not 3. This is infinity. That would be crazy. I don't think it would be elementary. I don't think it would be doable. Let me take a sip of water. Alright, from here, let's take the 3 outside for now, for the sake of brevity. We have integral from 0 to infinity. Distribute this out, you have 1 times cosine, so you have a simple cosine of tx here, and you're subtracting off a cosine times a cosine squared, which is a cosine cubed of tx. Put that there. All over x squared dx. Okay, now what do we do? Well, now we can use a trig identity, right? This cosine cubed kind of ugly. So let's break it up into our friends, well, its equivalent form using triple angle identity. Most people don't know what this is. Most people don't know the triple angle identity for cosine off the back of their mind either. So let's derive it. Okay, so where should we do this? Let's do this down here. And this is temporary because we're running out of board space. So we start with cosine of 3 theta. This is equal to cosine of 2 theta plus theta. And by the way, if you remember, we did this back for question, what was it? 2? Something like that. Yeah, we did sine of 3 theta, not cosine. So now we're doing cosine of 3 theta. Cosine angle addition is slightly different. We have cosine of the first times cosine of the second, and subtract off sine of the first times sine of the second. Alright. This one right here turns into cosine squared theta minus sine squared theta, and you have a cosine theta multiplied on. Here, the sine of 2 theta becomes a 2 sine theta cosine theta, and then you still have the sine theta waiting outside. Alright, cosine cubed theta, right, minus sine squared is also 1 minus cosine, so 1 minus cosine squared. And then we distribute that cosine theta in here. The sine squared and the sine, the sine and the sine make a sine squared, and we can do with that is replace that with 1 minus cosine squared. Since we want everything in terms of cosine, that's why we're replacing all the signs with cosine. Alright, and from here, distribute the negative, well, distribute everything in. So the cosine cubed, here stays. Negative cosine times 1 is minus cosine. Negative negative is a positive. Cosine times cosine squared makes cosine cubed. From here, negative 2 times 1 is negative 2, and then multiply by the cosine. And then negative negative is a positive. 2 times cosine squared times cosine is 2 cosine cubed. Almost done. We have this, this, and that. So we have 1 cosine cubed, 2 cosine cubed, 4 cosine cubed. 2. This is 2 of them. So we have 4 cosine cubed. And negative 1 minus 2 is negative 3. Alright. And from here, the table is really dirty. I don't know what I expected. Alright, anyways. From here, what we do is notice that this is still equal to this. That's where it came from. And right here, what we have is a cosine cubed. So we want to isolate that. So add 3 cosine both sides and then divide everything by 4. So you end up with cosine cubed by itself. And this is equal to, well, dividing it by 4 gives you 1/4 cosine 3 theta. And then this other term plus 3 cosine theta dividing by 4 just gives you 3/4 cosine theta. This red pen is really running out. I'm gonna try to finish it off though. So yeah, we can replace that with this. Okay, and we have our 3 integral from 0 to infinity. Cosine tx stays. However, we're subtracting off, and let's distribute the negative into these 2 terms right here. Minus 1/4 cosine of 3 theta. So minus 1/4 cosine of 3 theta. And theta is, in our case, just the argument of cosine, which is tx. And then we have the negative distributes, once again, into the second term, which is 3/4 cosine theta. Minus 3/4 cosine of normal theta. And theta, once again, is tx. Yeah, okay, and then yeah, here we can divide everything by x squared. Alright, so that was this right here, and I'm going to get rid of it now because we're not going to be needing it, but that's where the cosine cubed comes from. You can derive it again using that if you'd like. Okay, and now we have this. What do we do with this? So there's like terms here and here. So 1 minus 3/4 of the same exact thing gives you 1/4 of that thing. So you're able to factor out 1/4 of this and 1/4 of this. So factoring that out gives you 3, still is on the outside. However, now you factor out 1/4, so you're dividing it by 4. And then you're integrating from 0 to infinity. All right, so you factor out the 1/4 out of all of these, and remember, 1 minus 3/4 was 1/4. So you have just positive 1/4. Factor the 1/4 out, you have positive cosine of tx. So you just have 1 cosine of tx now. Here, there's a negative, so you have minus cosine of 3tx over x squared dx. And now we find I double prime, since there's no other way we can get rid of the x in the denominator, right? Yeah, we find I double prime. So this is I prime. Let's differentiate again. But that means we have to integrate twice coming back, but that's the least of our concerns right now, considering the way this horrendous thing works. All right. This right here is I prime. Let's find I double prime. Second derivative. So the 3/4 stays outside, 0 to infinity. Let's not even bother with writing the partial derivative with respect to t. Let's just differentiate this with respect to t. The over x squared, once again, stays on the bottom. So we're only working on what's on top. Differentiating cosine of tx gives you negative sine of tx. And remember, we're working with respect to t, so t is a variable, x is a constant. You move the x outside. Negative. Well, differentiating negative cosine gives you positive sine. So plus sine. And then t is your variable. 3x is your constant. So you can multiply that outside using chain rule like that. So here, an x here, and an x here, and an x here all disappear. Not sure how you come back. Do you do differential equations? Do you need to know all the intermediary steps? Nah, I don't think you need to. Okay. So yeah, as long as you know that this is the second derivative, then yeah. But I'm gonna erase everything from here on. All right. Now what we can do is break into two integrals, since notice there's one here and one here. So I double prime of t is equal to, so the first integral, you factor out a negative, we'll just put the negative outside, and you have the 3/4 times the integral from 0 to infinity of sine of tx over x. Yeah, dx. How would you evaluate that? That's a really good question, because you have another parameter in there. Yeah. Okay. And then from here, we have this 3 times sine of 3tx. Move the 3 outside, so you get 9 over 4. So here you get 9 over 4 times the integral of, from 0 to infinity, of sine of 3tx over x. Okay, from here, you can make a substitution for this one and this one, where u equals to tx, and now you're working with respect to x now, no longer considering t as your differential variable, right? So dx. So if you let u equals to tx, then a bunch of crap happens, but yeah, let's start from here. Let u equals to tx, du is equal to, well, u is dependent on x, not t. t. And yeah, t is going to be 1 regardless. So let's just say du is equal to, well, differentiating this with respect to x, right? The x is your variable, t is a constant, so the t stays, and then you have a dx. And same idea applies here. However, let's isolate so you got 1 over t du is equal to dx. Right here, same idea, except now we have a 3tx. So instead of just u equals tx, we want u equals 3tx. And let's use a different variable. Let w equals to 3tx. And then dw would equal to 3t, because those are our constants, and then dx. And therefore, 1 over 3t dw is equal to dx. At least that's how I think it works. Yeah. Okay, so from here, plug it in. This is equal to negative 3 over 4. And 1 over t is multiplicative. Let's take it outside because it doesn't have any u's inside of it, which is what we're working with. One more thing. As x approaches infinity, infinity times t is always going to be bounded, so it's always going to be infinity. So u is always going to be infinity, sorry. And our lower bound, 0 times anything bounded, is also going to be 0, so that makes sense. Sine of u over, and right here, the x is going to be, if you divide both sides by t, right here, so you get u over t is equal to x. Right. And then your du comes from 1 over t du. This 1 over t cancels with the t in the denominator of the denominator. So you're just left with that. Over here, you're adding 9 over 4, integral from 0 to infinity. Sine, you have 3tx, which is equal to w. And then x is, well, divide both sides by 3t, you get, well, wait a second. Yeah, divide both sides by 3t, you get w over 3t is equal to x. So that's what goes in the denominator. Your differential is 1 over 3t dw. This right here and the denominator of the denominator also cancel. So what are you left with? Negative 3 over 4 times integral of 0 to infinity, from 0 to infinity of sine u over u. U is a dummy variable, so no need to like try to backtrack or anything. 9 over 4 times the integral from 0 to infinity, sine w over w. dw. Okay, and finally you're done with your integration, since this is that. This is that. This is pi over 2, that's pi over 2. So, from here, this is negative 3/4 times pi over 2. Well, actually, not done with the integration yet. This is I double prime. However, it's not going to be that bad, since you see that I double prime, at the end of the day, it just evaluates to become a constant. And then here you get plus 9/4 times pi over 2. So this is, let's get rid of this. Yeah, let's get rid of this. So here, 4 times 2 is 8, so you get negative 3 pi over 8 plus 9. Pi is in the numerator, 4 times 2 is 8. So negative 3 pi plus 9 pi, right? You can combine the fractions. So this is equal to 6 pi over 8, which is 3 pi over 4. Notice that this is equal to that, 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 is equal to I double prime. All right. So we know that this is also happen to equal I double prime. Now, to go back to just simply I, right, which is our original function, plug in 1. Let's integrate both sides with respect to t. Integral of 3 pi over 4 with respect to t is equal to, I'm going to notate this I double prime using the integral of I double prime is just d squared I of t, of course, over dt squared, and then dt. This dt and the square cancel, and then you're left with just simply di of t. So, wait, no. Well, okay, here, let's go work on this side first. This is just a constant, and then times t, right? This, an implication symbol. Right here, this is d, how should I notate this? I of t. Being quirky with these guys is so difficult, you know? Finally, let's integrate one more time. So, integrating this right here, 3 pi t over 4 with respect to t. And then the right side, integrating this with respect to t. Like this. This and that cancel. And integral of di of t is just I of t by itself. So right here. 3 pi over 4 is a constant. Let's keep that outside, right? And then what we're really doing is integrating t, which is 1/2 t squared. This is equal to, as I said earlier, integral of di of t is just simply I of t. Okay. And there's 2 plus c's technically. However, do we want to play this fairly or do we want to not? If you notice that right here, right, 3/4 t, and if you were to add c, right, then what you could have done is plugged in 0 for t. I of 0, let's trace it back to here. The first derivative. Well, how do I tell you this? The first derivative, all I know is that it had a sign of something t times whatever else, right? In the numerator. Now, and by the way, this is I prime, right? And then there's like an integral from 0 to infinity or something like that. But regardless, if there's a sign of that, of t times that in the numerator, and you wanted to see what, well, I mean, you replaced it with that, and you would let t equal to 0 to solve for c. This first of all is equal to 0. So 0 plus c is just c, right? So c would be equal to whatever this is, which is whatever we had, evaluated at 0. Sine of 0 times anything is just sine of 0, which is 0. 0 over anything is 0. Integrating 0 from 0 to infinity is still 0. So c is therefore equal to 0. This thing, if you plugged in t equal to 0, that would be equal to 0. So c, for the first c would be equal to 0. So let's call this c1. Alright, and c2 right here, same idea. If you plugged in 0 here, left side goes to 0. So that means 0 is equal to something plus c2. And let's find I of 0 then, because t we set to be 0. It's just this. So put a 0 where t is, right? You get sine cubed of 0, which is just 0. Integrating 0 from 0 to infinity is 0. Okay, so 0 is equal to 0 plus c2. c2 would be equal to 0. That guy is negligible. Let's bring this up one last time. It's this, right? So 3 pi over, well, 4 times 2 is 8. So 3 pi over 8 times t squared, finally, is equal to I of t. Finally, plugging in t is equal to 1 on both sides. On the left-hand side, t is equal to 1. 1 squared is just 1. 3 pi over 8 times 1 is just 3 pi over 8. 3 pi over 8 is equal to I of t equals 1. And yeah, notice that our original integral is I of t equals 1. And so is this number. So therefore, 3 pi over 8. That's it for this one. God damn. Alright, that's number 80. These three were a fiasco. I think they're really fun. Because even though they all look similar, they all take slightly different methods to solve. And the first one especially is pretty rewarding. Especially if you start to begin to understand differentiation under the integral sign. It's pretty cool. Yeah. And that's it for the single integrals. That's it. All the single integrals. Done. We just have a bunch of double integrals left. Yeah. Pretty cool. Okay. It's, what, day 4 now? Let's do some of the double integrals. We have 81 all the way to the end. So, yeah. Okay. Number 81. Double integral. That's cool. From 0 to 1. And then from pi y to x. To pi, from pi y to pi. I can't see, I think I'm blind. Yeah. Of sine x over x. And then this is dx dy. I thought we just finished trying to integrate this stupid function. Now we have to integrate it first with respect to x, right? And that's not an elementary. So what do we do with it? Well, we can switch the bounds, because if we were to integrate with respect to y first, then we can introduce a y, and then it'll help cancel with the x after you plug in bounds. So let's see how this works. So we have a graph, and everything here is positive, right? On the y-axis we have 0 to 1, and on the x-axis we have from pi y to pi. So if x is equal to pi y, then this means that y is equal to 1 over pi x. So it's going to look something like that, right? So this line right here is both of these. So I'll put down x is equal to pi y, or y is equal to 1 over pi x. And right here, the x value for this would be pi, right? Okay, and we're integrating first from pi y to pi. So we're going from this line right here all the way to pi, right? And then we have 0 to 1. So we're integrating over, should be this area, I think. Yeah, because we're going from the line, the linear expression, to the this x value, right? So now we have to express this in terms of y first. So instead of dx dy, we want this to be dy dx. So we have a double integral. The inside's gonna stay the same, but now we want dy dx. Alright, so first we want to go, we want to take a look at where we're integrating from on the y-axis. And by the way, this is y and this is x, yeah? So on the y-axis, if you see, we're going from y equals 0 all the way up to the line, right? So we go from 0 to the line, and the line, we want it to be in terms of, well, x. Y in terms of x, right? So this is going to be 1 over pi x. All right, and then from the and then on the outside we have the x value, and we're just simply going from 0 to pi. So hopefully this works better for us. Yeah. So now let's integrate the inside integral with respect to y. Sine x over x does not have any y in it, right? So, and x is independent from y because this is an input plane. The entire thing is the input, right? So therefore x is independent. We can treat it like a constant. So integrating a constant with respect to y, well, we need to just multiply in a y, right? And that would look like this. Okay, and don't forget we have these inner bounds going from 0 to x over pi. And then this is dx. Alright, let's plug these in. If you plug in 0 to y, then the entire thing goes to 0, so this is empty. And then if you plug in x over pi, well, you get integral from 0 to pi of, so yeah, let's just write it down like this. Sine x over x times x over pi. Notice that the whole reason why we did the bound change was, first of all, it's impossible to integrate it like this, right? And now this is a lot nicer since the x's just simply cancel. There's an x here and an x here. The 1 over pi, we can bring it outside. And what we get is 1 over pi times the integral from 0 to pi of sine x dx. And this is a simple case of integration. We get, integrating sine x, we get negative cosine, so negative cosine x. Don't forget about our 1 over pi constant multiple on the outside. And then finally, evaluate from 0 to pi. Okay, so evaluating this, I'm going to do it up here. Negative 1 over pi. So evaluating it at pi, cosine of pi is just negative 1. So let's do it like this. So negative 1, right? And then you're subtracting off this the cosine evaluated at the second bound, 0, which is just simply 1. So what you get is negative 1 over pi times negative 2. The negative and the negative cancel, right? And you just end up with 2 over pi. Alright, and I'm not sure if I should explain what the intuition is behind integrating a double integral, right? That looks like this. Essentially, if you take this input plane and then you rotate it on its side, so it looks like this, right? So let's say you're integrating over this area right here. So on the y-axis, it corresponds to that. On the x-axis, it corresponds to that. Well, your z-axis, which is going to go up, there's going to be some kind of surface for you to integrate over. Jesus Christ. It's going to look like that. Well, let me try this again. Hold on. Right, so this is going to be your surface in the third dimension, and this actually represents a function f of xy is equal to z, and f of xy is right here. So what you're doing is, if you're integrating over this area right here, then what you're doing is you're finding a volume. You're drawing walls up, right, from here and there all the way up to this surface up here. Right, so that's the hypotenuse of this triangle that I drew. And then you're basically drawing walls that go all the way up until it hits this function. And you're looking for the volume of that area that you just walled in. So that's really cool. Yeah, and in our case, if you drew the function f of xy is equal to sine x over x, then the area you'll be finding is between this right triangle and that surface. So. And sorry, not area, volume, and this volume is 2 over pi. Okay, that's number 81. Okay, number 82. Integral from 0 to 1, and then inverse tangent to pi over 4. Inverse tangent x, sorry, to pi over 4 of our integrand is cosine y dy dx. Okay, we can just straight up integrate it since our first integral is with respect to y and it looks pretty easy to do. So let's do that. You still have the outer integral 0 to 1. Integrating cosine y with respect to y, you get sine y. And you plug in your bounds from inverse tangent x to pi over 4. And on the outside you have dx. Alright, so you have inverse sine of pi over 4, well, I'm sorry, not inverse sine, normal sine of pi over 4. And then you want to subtract off sine of inverse tangent x. Alright, so first of all, this one is just a constant. You get root 2 over 2. So we'll put that down like this. Secondly, this one right here, it's a trig function of an inverse trig function. So we can draw out a right triangle and try to figure out what is going on. So inverse tangent, the argument is a ratio of the tangent ratio, right? It's opposite over adjacent. So if we called this our, just theta, right? Then, well, let's just call it theta for now. Then if we let, well, in fact, we can use y. Because if you notice here that this bound is y is equal to inverse tangent x, therefore tangent y would be equal to x. Tangent y being equal to x is opposite over adjacent, and that's x over 1, so opposite over adjacent. And then here we have our third side. We're trying to find the sine of y, right, since y is equal to inverse tangent once again. And this would just be x squared plus 1. So you're subtracting off, sine is opposite over hypotenuse. So you get x over square root of x squared plus 1 dx. Alright, and from here you can actually integrate one more time. Since if you notice that, well, if you just multiply 2 down here and a 2 up there, then what you get is that if you just ignore the top for now, this looks like, well, you differentiated the square root of x squared plus 1. And on top is your result of chain rule. So therefore you know that the antiderivative of this, you can also make a u substitution if you'd like, is just the square root of x squared plus 1. So we got this integral from 0 to 1 of, well, actually no, because we can evaluate the integral now. So well, all we've got is root 2 over 2, the integral of root 2 over 2 in the x world is just that times x. And then here we get the root of x squared plus 1. Don't forget, we have to evaluate from 0 to 1. Plugging in 1, you get root 2 over 2 minus root of 1 squared plus 1, which is just root 2. Plugging in 0, this becomes 0, and then minus, so, okay, first of all, you want to subtract off that, right? So this first guy becomes 0, and then the second guy right here, if you plug in 0, you get negative square root of 0 plus 1, negative square root of 1, negative 1. So, here we go. Okay, first of all, if you look at this, you can combine these guys, right? This becomes 2 root 2 over 2, right? Think about it. And then you have root 2 minus 2 root 2, all over 2. That's a little bit hard to think about, actually. So, well, let's do it manually. But first of all, we notice that this just gives you positive 1. This one right here, you're adding, you want a denominator of 2 for both. So for this one, you just keep it, right? For this one, you multiply a 2 on both the top and the bottom. You get root 2 minus 2 root 2 all over 2. And then this should give you a factor out of root 2. If you factor out a root 2 on the inside, you have 1 minus 2, which is negative 1. So you have root 2 times negative 1 all over 2, which is just negative root 2 over 2, yeah. So this becomes a negative root 2 over 2. Yeah, there we go. This is the volume under that surface at these bounds. So, okay. So that's number 82. Number 83. For number 83, we have a double integral from 0 to 1, and then y to 1, of 1 over 1 plus x to the 4th dx dy. For this one, notice that it's really difficult to integrate with respect to x, but we have two integrals, so let's just try to interchange them using some geometry. So first of all, what do our integration bounds look like? Well, in the x world, right, this integral corresponds to x. We're going from x is equal to y, which looks like this. So this can be expressed two ways, right? To 1. So this is x is equal to 1. So it'll be right there, 1. And then in the y world, we're going from 0 all the way up to 1. So we have 0 to 1. So since we're going from here all the way up to there, we're going from this linear line right here all the way up to x is equal to 1. It's going to be the space in between the two. Okay, so we're integrating over this area right here. So if we wanted to interchange it, we would want something dy dx. So let's set that up. 1 over 1 plus x to the 4. And just switch the order of the differentials. So we're integrating with respect to y first. Now, if we're integrating with respect to y, then we want everything on the outside to be a constant. On the inside, we want it to be with respect to x, so that way we plug it in and everything is in the x world, so we can integrate it easily. So for the inner bounds, they need to be in terms, well, they need to be y in terms of x. So going from, in this area, we go from 0 to up to the line if we're taking the y value first, right? So we go from 0, y equals 0, all the way up to that line, y equals x. So we go from 0 to x. And then for the x value, which is on the outside, we go from 0 to 1. Alright, and now let's try to integrate this guy. So we got 0 to 1. Integral of this guy with respect to x, it's nothing but y times it, because it's a constant if you're working with respect to x. Plugging in bounds 0 to x, and then dx. Notice that if you plug in 0, this thing would become 0. So you would just plug in x. Alright, and from here, you can make a substitution if it's not obvious. Maybe we did this earlier, maybe it was in the other video. I don't remember. But what we can do is integral from 0 to 1 of 1 plus, we write this as x squared squared, and then you notice that the top is just the differential if you let u equal to x squared. So let u equal to x squared, differentiating both sides gets you du equals 2x dx. You don't have a 2 here, let's just let's multiply it like that. Alright, so you have a 2x dx for your du. 1/2 stays on the outside. Now we want to evaluate bounds. So when x is equal to 0, then plug in 0 here. You want it in terms of u, right? So plug in 0 and you get 0. And then when x is equal to 1, plug in 1 here. It's u is equal to 1. And then here, the top is your differential, so you get du on top over 1 plus u squared. Alright, and from here, let's move it up there. We get inverse tangent of u, right? 1/2. Antiderivative of that gives you inverse tangent of u. Ranges from u equals 0 to u equals 1. At u equals 0, inverse tangent of 0 is just 0, so that's empty. So this is really just 1/2 times the inverse tangent of 1. And the inverse tangent of 1 is pi over 4. 1/2 times pi over 4, well, that's just pi over 8. Okay, box your final answer. That's it. Okay, so that's it for number 83. think my black pen is slowly running out, so I'll finish maybe a few more and then I'll go replace it. We've got number 84. This is number 84. Integral from 0 to 1 of integral from root x to 1 of cosine y cubed dy dx. Notice that the inside cosine y cubed dy is not elementary. You can't find an antiderivative for that. So instead, let's swap the order of our integration. Yeah? So root x looks like that. Kind of. That's really wrong, actually. That looks more like a sideways catenary curve. Yeah, so that's what root x roughly looks like. It's like a sideways parabola. So in our y world, we're integrating from root x. So we start, this is our lower bound, and then we go all the way up to y is equal to 1, yeah? From root x to 1. Okay, and then from for the x values, we go from 0 to 1. So 0, and then notice that where y is equal to 1, where it meets, it's also going to be 1. And it looks kind of, expanded, but this is a very rough sketch. All we need is a way to change the bounds. So we're integrating over this area, since root x to 1, and then we have 0 to 1. Yeah? To change the bounds, we want x on the inside. So we do a double integral. So for x, expressing this as a function of y, then this is y equals to root x, meaning this is x is equal to y squared. So if we wanted cosine of y cubed dx dy, then what you get is, well, the inside, it has to be in terms of y. So we're going in horizontally first. So we're going from x is equal to 0 up until this curve. So we're sweeping up until that curve, right? So we start at 0, and then we go up to, not root x, but we want this in terms of y, right? So this is x is equal to y squared. All right, and then for the y value, we're going from 0 to just 1, yeah? Okay, and from here, what we can do is we can integrate, because now we're just integrating with respect to x. Integrating the inside, the outside stays the same, more or less. Integrating this with respect to x, well, this is just a constant in the x world, so this is x cosine of y cubed from 0 to y squared. Notice that our 0 is empty. If you plug in 0 into x, you get nothing. So this is just y squared. And don't forget your differential on the outside, dy. Okay, so in here, the x is just y squared. Cosine of y cubed. Okay, now notice you're able to make a u substitution. Let u equal to the inside of y cubed. Let u be equal to the inside of the cosine, so that's just y cubed. Because y squared dy is very close to your differential, which is 3y squared dy. Alright, so you have a y squared dy, however you don't have the 3. So let's divide 3 on both sides. Okay, and from here, let's evaluate the bounds too. These are in terms of y, we want them in terms of u. So plug them into y, and it'll spit out a value of u. 0 cubed is just 0, so u is equal to 0. Now for the upper bound, plug in 1 into y, you get 1 cubed is equal to 1, so u is equal to 1. Alright. This 1/3 is multiplicative, let's bring it outside. On the inside, the y squared dy became our differential, so we just have the cosine of y cubed left. Remember, y cubed is u, so we'll just put a u in there, and then we have a du, and all that. That's all that's left. We have 1/3. And no, this we can just integrate. So this we get a negative sine u. And then this goes from u is equal to 0 to 1. Sine of 0 is 0, so we don't need to plug that in. Sine of 1 is just, well, simply 1. Oh no, and there's no negative. There's no negative. So this is 1/3 times sine evaluated at 1 radian. And, well, there's not much other ways you can express this. Right, so that is our final answer. Okay, yeah, that's number 84. Whew, next one looks, well, let me think about this. All right, so yeah, that's number 84. Let's move on to number 85. Okay, for number 85, we've got integral of, well, let's write down the bounds first. We have 0 to 1 over root 3. So these are our first bounds. And the second bound is inverse tangent to pi over 6. And this is inverse tangent x to pi over 6. Okay, and then on the our integrand is secant to the 5th of y, and this should be dy dx, right? Okay, from here, this is a little bit difficult to integrate in the y rule, so let's try to switch the bounds. From here, let's draw our input plane. This is y, and this is x. First, let's take a look at the y bounds. We're going from y is equal to inverse tangent of x to y equals pi over 6. So let this be y equals to pi over 6. And inverse tangent looks something like that, right? So we're going from y is equal to inverse tangent x to pi over 6. And next we have 0 to 1 over root 3. And 1 over root 3 happens to be exactly where pi over 6 is, so that makes sense. Since inverse tangent of your x value, 1 over root 3 gives you pi over 6. So you're going from this curve up to that line, so you're integrating this area. And you're going from 0 to 1 over root 3, which makes sense. Okay, and now let's rewrite these all in terms, well, let's rewrite this in terms of y. So we want x as a function of y, so we have x is equal to, take tangent on both sides, you get x is equal to tangent y. Alright, next up, equal sign. Integral, we want this to be, well, let's put down secant to the 5th first. And we want this to be dx dy. So first we're scanning across horizontally, because we switched to the x first. So going horizontally, we start at 0, and then we go to our curve, which is tangent y. So we go from 0 to tangent y. Alright, and then we have our y value, which just goes from 0 to pi over 6. So this is much cleaner now, because we're integrating with respect to x first. No more nightmarish, well, you know. So integrating with respect to x, you get x times that. Evaluate from x is equal to 0 to x is equal to tangent y. Notice that if you plug in 0 into here, 0 times secant to the 5th is always just 0. So this is 0. And then all we need to do is plug in a tangent y. And you might see where this is going. We can take out a secant to join the tangent y. 0 to pi over 6. Alright. So let's rewrite this as secant to the 4. And then let's take out a secant to join our tangent. So notice that this is now just the derivative of secant. So let u equal to secant y. Then du would just be what we have down here, secant y tangent y. Like that. Alright, and then we can go ahead and, first of all, what are our bounds? Secant of 0 is just 1 over cosine of 0. Cosine of 0 is 1, so it's 1 over 1, which is just 1. And then secant of pi over 6 is, it's just 1 over cosine of pi over 6. Cosine of pi over 6 is equal to root 3 over 2. And then secant is the reciprocal, so this is 2 over root 3. I think. Yeah. Alright. And then on the inside right here, we have secant to the 4th power. The secant is u, so it's u to the 4th power. And then we have secant y tangent y dy, which is just du. Alright, so this is just a case of reverse power rule now. You get 1/5 u to the 5th. And you also want to keep in mind that you're evaluating at these bounds. So let's evaluate from 1 to 2 over root 3. Okay, evaluating at 1, plugging 1 in, you just get 1 over 5, so. And then evaluating at 2 over root 3, let's just plug that in. 2 over root 3 all to the 5th. And then you want to subtract this thing evaluated at 1, which earlier we determined was just 1 over 5. Alright, and now what you can do, 2 to the 5th power is 32. So, and I'm going to combine the fractions here. So, root 3 to the, I'm going to put this down. 2 to the 5th is 32, as I mentioned, and then root 3 to the 5th is root 3 to the 4th times 3. Root 3 to the 4th is 9, and then times root 3. So 5 times 9 root 3. And you're still subtracting 1/5, sorry. And from here, you're almost done. You get 32 over, combine the 9 and the 5, you get 45. The root 3 is still there, and then you're still subtracting 1 over 5. So yeah, this is your volume. Alright, so that's number 85. Yeah. And I'm not going to rationalize the denominator. We're not babies anymore, at least. So yeah. Okay, next up, we've got another trig one. This one's pretty cool, I think. We're going from, this is number 86. I think it's about time I get a new black pen, actually. Give me 1 second. Alright. Got a new black pen. And we're ready to go. Number 86, we've got double integral. Outside is from 0 to root pi over 2. Okay. And then we have our second bound is 0 to, that says x squared. Integrand is x secant squared y. And then this is dy dx. From here, this is pretty easily integratable. You're able to integrate with respect to y first because that's just tangent. So let's go ahead and do that. No need to switch the bounds. Okay, so integrating with respect to y, x is just a constant. We leave that there. And then integral secant squared y with respect to y is just tangent y. And evaluating from 0 to x squared dx. Tangent of 0 is just 0, so this can go to hell. And then we can just plug in x squared. So we get x tangent of x squared dx. And this is pretty simple because, we can make a u substitution. Let u equal to x squared, and then x dx is your differential. So differentiating both sides, you get 2x dx. You have an x dx, right? You don't have the 2, so let's isolate the x dx. Divide both sides by 2. 1/2 du is equal to x dx. Alright, and then we have, our next step is to, just plug it in. And don't forget to evaluate the new bounds. So, we have to, these are in terms of x, we want them in terms of u, so you just plug it into x and then get the corresponding u value out. Plug in 0 into x, u is still equal to 0. Plug in root pi over 2 to x, you get u is equal to pi over 4. 1/2 is multiplicative, let's take it outside. And on the inside, all you're left with is, well, tangent of u. And then du. Okay, from here, the antiderivative of tangent is just natural log of absolute value of secant. And we're evaluating from 0 to pi over 4. Plugging 0 into secant, you get 1. Natural log of 1 is just 0, so the 0 disappears. And then we evaluate secant of pi over 4. Secant of pi over 4 is just root 2, because 1 over cosine of pi over 4 is just 1 over root 2 over 2, right? Multiply a 2 on both the top and the bottom, you get 2 over root 2. Dividing a root 2 on both the top and the bottom, 2 over root 2 is just root 2. Yeah, okay. Well, so now you just have 1/2 natural log of secant evaluated at pi over 4, which as mentioned is root 2. This is just 2 to the 1/2. Bring the 1/2 outside, you get 1/4 natural log of 2. And that's it. Cool. Alright, that's number 86. Number 87. Finally one that's not trig. Not quite, at least. We have a double integral from 0 to 4, and then from 0 to y of 2 over x plus 1 y plus 1 dx dy. Okay, notice that this, well, if you interchange the bounds, it doesn't change what you have to do in here. This is more or less symmetrical. So and by the way, this isn't partial fraction decomposition either, since these are different variables. If we're integrating with respect to x, then you can treat the y plus 1 being multiplied in as just a constant. So you really just have 2 over y plus 1 on the outside, right? And then you have 1 over x plus 1. Right. In fact, what you can do is you can just break these two integrals apart. So let's think about it like this. The inside is with respect to x, so the 2 over y plus 1, we can move it outside. So let's move that outside. Right. Okay, and then we have your integral from 0 to y of 1 over x plus 1 dx dy. Notice that you can't, there's nothing in here. Well, okay, this is going from 0 to y, so let's integrate it like this now. But you can break it apart by taking that out. And now this is much more intuitive for you to work with. So, you still get 0 to 4. You still get 2 over y plus 1. In here, if you integrate with respect to x, you get natural log of x plus 1. And you're evaluating from x is equal to 0 to x is equal to y dy. Alright, notice that if you plug in 0, natural log of 1 is 0. So it goes to 0, so you have natural log of y plus 1. So on the outside, 0 to 4. Let's bring the 2 outside, actually. So you just have natural log of, well, let's make that a parentheses, since we're going from y is equal to 0 to y is equal to 4. It's always positive. So, and yeah, we replace that with the y. So y plus 1 over y plus 1. Let's make a substitution where u equals y plus 1 really quickly. Let u equals to y plus 1. Actually, let's do the natural log of y plus 1. Because notice that we have our differential down here. 1 over y plus 1 dy. Yeah. And taking the derivative on both sides, you get du is equal to 1 over y plus 1, and then times the derivative of y plus 1 with respect to y, which is nothing but dy. Okay. From here, we have 2 on the outside still. Plugging in 0, these are in terms of y, we want them in terms of u. Plugging in 0 into here, you get ln of 0 plus 1, which is just 0. Plugging a 4 into here, you get ln of 4 plus 1, which is ln 5. On the inside, you replace the top with just u, right? And then you have 1 over y plus 1 times dy, which is du. You can integrate 2u du, and that just gives you x squared. So if you were to drag the 2 inside, it wouldn't change, it's still x squared. Sorry, not x squared, u squared. U squared. And you're evaluating from 0 to ln 5. Notice that plugging in 0 goes to 0. Plug in ln 5, well, you can't simplify a log to a power, so it's just ln 5, but squared. Yeah. This number right here represents the area, well, the volume. Okay. That's number 87. Okay, number 88. Looks pretty intimidating, but we'll see how it goes. So, should we, let me think about it. No. Okay. Number 88. Double integral, once again, where outside is 0 to root pi, and inside is 0 to pi. And then you have y times sine of x plus y squared d what? dx dy. From here, integrating with respect to x, I think, would that be easier? Probably, because y squared is just a constant, so so is this y being multiplied. So let's just integrate. Straight up integrate. So outside stays 0 to root pi. Inside, integrating this guy with respect to x, treat y squared just as a number. So it could be like x plus k, right? And you're still integrating with respect to x. And if you made a substitution, u is equal to x plus k, well, you're still going to get negative cosine of x plus k after you do the differential and you integrate it. So regardless, the argument stays the same and there's no implications on the outside. The y just stays outside as a constant multiple. So you have y times integrating sine, you get negative cosine of the same argument because it is linear in terms of x at least. And you're evaluating from x is equal to 0, from x to x is equal to pi, dy. So from here, 0 to root pi. Shifting this, okay, well, first of all, plugging in a pi there, shifting a cosine by pi, I need to work this out. So we can keep the y outside, because all we're really evaluating is just the red part right here. So let's do cosine of pi plus y squared minus cosine of 0 plus y squared. And let's work out what the phase shift of pi is equal to, because I don't remember the trig behind that. Cosine looks like this. Oh my god, that's a very... Let me try that again. Cosine looks like this, right? Third attempt. Cosine looks like that. And this is the y-axis, and this is the x-axis, more or less, right? So if you shifted it, this would be at pi over 2, this would be at 3 pi over 2, this would be at pi. So if you shifted the entire thing pi units this way, well, then you would get a graph that looks like this. So notice that if you shifted the pi units to the left, which is what adding pi does, you get a negative version, since it's now the valley that hits the y-axis instead of the peak, the crest. So you get something that looks like that. Then, yeah. So this is just negative cosine, because it's the same idea as flipping it over the y-axis, because all you just did is made it, well, yeah, like flip on itself, right? Where there used to be a valley, there's now a peak. Where there used to be a peak, there's now a valley. So this guy just makes it negative cosine. So equals negative 0 to root pi y times, this is negative cosine of y squared. Yeah. And then this is minus cosine of, well, 0 plus y squared is just y squared, so y squared dy. This gives you negative 2, right? Negative 2 cosine of y squared. You can bring the negative 2 all the way out to the outside. The negative cancels out. You just have a 2 left. So you have 2 times integral from 0 to root pi of y over, times cosine of y squared dy. Notice that if we let u equal to y squared, then we have a 2y dy here to be our differential. So let u equal to y squared, then your differential would be du is equal to 2y dy. And you have 2y dy, yeah? So all we need now is the bounds. This is in terms of y, 1 in terms of u. So plug it into here, and then we'll get a u value out. So 0 squared is just 0. And then root pi squared is just pi. In here, the 2y dy became your differential, so all you're left with is the cosine of y squared. Cosine of y squared is just cosine of u, since y squared is u. And then you have the 2y di on the outside to become your du. Finally, integrating this, you get sine u. And then you want to plug it in from 0 to pi. Now, 0 evaluates to 0, sine 0, 0. And pi values to 0, since if you draw it out, right, your unit circle, if you turn y, then you get to here, and then you get to this point right here. The y value, which is corresponds to the sine, is 0. So they both evaluate to 0, meaning 0 minus 0 no, it's just 0. This whole thing evaluates to just 0. Okay, yeah, that's number 88. Yeah, alright, now let's move on. Number 89. Number 89, no trig here. We'll write it out and we'll analyze it. So 89 is 0 to 2 and then x to 2. On the inside we have x times the root of 1 plus y cubed dy dx. Integrating this with respect to y first, square root of 1 plus y cubed, I don't think is elementary. Maybe it is. Anyways, so let's change the order. So we have to draw out our input space. First of all, let's draw out the inside. In terms of y, we're going from y is equal to x, so that's this line right here, up to y is equal to 2. So that would be this line right here, if this is 2. And then the x, we're going from 0 right here to, 2, right? So it's just this area right here. Okay, well, we want this to be dx dy, so let's draw out our new integral. Keep in mind that the inside still remains the same, but now we just swap the order of integration. So inside should be a x in terms of y. So our lower bound, well, we're going horizontally first, so our lower bound is going to be x is equal to 0, and then we go all the way to this diagonal line right here. So yeah, we go to that, and then we want x in terms of y, and this is just x equals to y, so therefore this is y. And then our second we go vertically, right, in the y direction, start at 0 to go to 2. Yeah. So let's hope this is better. Let's integrate. On the inside, the root of 1 plus y cubed is just a constant. So that'll stay outside. Integrating this with respect to x, you get 1/2 x squared. So let's do 1/2 x squared times root of 1 plus y cubed. This is going from x is equal to 0 to x is equal to y. Notice that when x is equal to 0, the whole thing zeroes out. This becomes 0, and then you have a dy. Alright, and then plug in y where x was. All in all, this gives you, let's move the 1/2 outside. Yeah, 1/2 times the integral from 0 to 2 of, you just have x squared, which is also y squared, since you're just plugging in a y, times the root of 1 plus y cubed dy. Alright, and we can just let the entire inside be u, and then y squared dy is part of our differential. So let 1 plus y cubed equal to u. Differentiating both sides, 3y squared dy is equal to du. We don't have the 3, so let's divide both sides by 3 to isolate the y squared dy. And this is 1/3 du. So over here, 1/2. 1/3 is multiplicative across everything. Let's take it to the outside like this. Bounds. So these are in terms of y, you want them in terms of u. Plugging 0 into here, you get 0 cubed is 0. 1 plus 0 is u, which is also 1. So our lower bound is 1. Plugging in 2 here to get our u value, we get, well, 2 cubed is 8, 1 plus 8 is 9, therefore u is equal to 9. In here, we took care of the y squared dy, it's just a differential. Then we can just have the square root with our u inside of it. So root u, and then we have our du. So now let's evaluate this. On the outside, the 1/2 times 1/3 becomes 1/6. And then you have the, well, let's integrate the inside. So u is just u to the 1/2. Add 1 to the power and divide by the new power. Well, adding 1 to the power, you get 3/2. Dividing by the power, you get multiplying by 2/3. U to the 3/2. You're going from 0 to 9. Sorry, not 0, 1. First of all, notice that you can cancel this to become 1/3 times 1/3, which is just 1/3 squared, which is just 1/9. Alright, here. Let's rewrite this in terms of radicals, because it might help. So this is really, plugging in 9, you get root of 9, and then on the outside we can have the cube. And we're subtracting off, well, root of 1, and then outside you have the cube. Since this root and then cubed is equal to our exponent right here. From here, 1/9, right, and then root of 9 is 3, 3 cubed is 27, and then root of 1 is 1, and then 1 cubed is 1. So 27 minus 1, which is just 26. So all in all, this is 26 over 9. That's our final answer. Okay, and for the standard given double integrals, we have one more. That is question 90. So for number 90, we have integral from 0 to ln2 of the integral from e to the x to 2 to 2, yeah. So e to the x to 2, and then 2xy over ln y dy dx. Integrating with respect to y, I am not sure how you would do that. So yeah, well, you can make a substitution. However, it's a little bit difficult. And also, if you take a look at this, ln2 e to the x2, it's begging for change of variables. So, not change of variables, sorry. Just change in order. Okay, so we're going in the y direction. So from here to here, we have y equals e to the nth. So we're going from here, right, up to 2. So that would be up to here. And this is y is equal to e to the x. And if you were to isolate x is equal to ln y. And then in the in the x direction, sorry, because that's our outer bound, we're going from 0, right, to, well, ln2. Because if you plug in ln2 into e to the x, then you just get 2 out, which is exactly there. So since we're going from e to the x up to 2, we have this area right here. But we want to switch it to dx dy. So double integral. And then, well, our integrand remains the same. And then this becomes dx dy. Alright, on the inside, we want the horizontal movement first. So we're going from 0 up to the curve, right? And the curve, in terms of x, is ln y. And then in the y direction, we're going from y equals to, well, 1 here, right, up to just 2. So 1 to 2. And this looks much better. Okay. Integrating the inside first. In integrating, well, y over ln y, constant, you can just ignore that. You have a 2x here. So let's put the y over ln y out here. And then integrating 2x times the constant is just x squared times the same constant. So the 2x, we can just make that an x squared. And then we have the same constant y over ln y. And then plugging in from 0 to ln y. Plugging in 0 into x, the whole thing gets zeroed out. And then plugging in an ln y into x. Well, let's write it down like this. So this is just integral from 1 to 2 of, well, ln y all squared times y over our original pre-existing ln y, like this. The square on top cancels with the thing on the bottom, so we're left with integral from 1 to 2 of, well, let's write it down like this. Y ln y dy. For this one, let's try integration by parts. So we differentiate the ln y, integrate the y. Differentiating this, you get 1 over y. Integrating this, you get 1/2 y squared. So this is in reality equal to, multiply the diagonals, you get 1/2 y squared ln y. Remember to evaluate from your bounds, right, at your bounds, and then you're subtracting off. The 1/2 is a constant multiple, so let's bring that outside. And then integral with the same bounds, 1 to 2, of y squared times 1 over y, the square and the y cancel, so you're just left with integral from 1 to 2 of y dy. Okay, first of all, we can do a couple things with the bounds here. At 1, ln 1 is 0, immediately it goes to 0, and then you can just evaluate it at 2. Alright, so let's go up here, and let's get rid of this, since it might get in the way, maybe not. Let's work on the first term first. Plugging in 2 into y, you get 2 squared, right, which is 4. Dividing by 2, you get 2, and then you have ln 2. So you have 2 ln 2. Alright, and then for the second term, we subtracting 1/2 still. Integrating y in the y world, you get 1/2 y squared. And then don't forget to plug in bounds, which is from 1 to 2. Bring the 2 up, I guess. You can try that. It makes it look a lot more, a lot better, I guess. Here, the 1/2 times 1/2 is just a constant multiple. We'll take that outside, and then we'll evaluate everything else. So, first, evaluate it at 2, so you get 2 squared. And then you want to subtract off the evaluation at 1, which is 1 squared. 2 squared is 4. 1 squared is 1. 4 minus 1 is 3, so this is 3 times 1/4, which is just 3 over 4. And this is it. Yeah, that's it. So these double integrals, pretty cool. There's 2 layers to it, right? And if one layer is too difficult, just swap the order, and then it ends up not being all that bad. Yeah, that's it for number 90. Okay, so I moved the stool, but next let's go on to the more abstract double integrals. We'll start with number 91. So number 91, we're integrating over region R of e to the negative xy over 2 dA. Now we need to know what R is. R is just if you take a look at a graph, right, then it's just this area that you're integrating over, and then dA is just your differential in x and y. So you have little differentials in area, that's dx times dy, right? I'm doing that infinitely. Okay, so this particular question, number 91, we have the R being the region bounded by y equals 1, y equals 2, x equals 0, and xy is equal to 1, right? So if we draw it out to try to fathom some bounds, then first of all, y equals 1 is here, so let's write that down. Y equals 2 would be here. X is equal to 0 would be this line right here. And then we have xy is equal to 1. So the area bounded by all 4 of these, right, is this right here. So if you try to do dy dx, right, let's try setting it up. So this is equal to the integral from what to what? E to the negative xy over 2. Let's try dy dx. Alright, so if we did dy first, then we need to find out how to go from the y bound to the other y bound, but the other y bound needs to have xy in it, since we need to have a variable in terms of x, right? If we want to be able to integrate this, well, we need to have something in terms of x in the boundary of your y integral, because that way you're able to plug in, right, and find the other one, and plus one of your boundaries in terms of y is 1 over x. However, notice the entire thing, there's part of it that doesn't get bounded by y over x. Sorry, not y over x. There's part of it that doesn't get bounded by y equals 1 over x, right? And to be specific, it's the left half of this black dotted line I just drew. Notice that here the upper bound is y equals 2. Here, though, the upper bound is xy is equal to 1. So don't do it this way unless you want to split it into 2 integrals, because it is possible to only integrate this rectangular area and then integrate this area that's bounded by the xy equal 1. However, dy dx, let's not do it this way. Instead, let's try dx dy. So now, if you were, dx means you're going horizontally first, and now it works. Since the entire upper bound, the entire upper bound in terms of x is xy equals 1. So you're able to have write all this in just one integral. So you're going from x equals 0 to, in terms of y, as x in terms of y, this would be x equals to 1 over y. So you're going from x equals 0 to x is equal to 1 over y. On the outside, y value is pretty easy. You're going from y is equal to 1 to y is equal to 2. 1 to 2. Okay, and now what you can do is integrate. So outer bound, we still have 1 to 2. In here, notice that you're integrating with respect to x, so x is your variable. Negative y over 2 is a constant that's being multiplied by x in the argument of the exponential function. So way you integrate that is, since negative y over 2 is like a constant, you want to divide by it because of reverse chain rule. So dividing by negative y over 2 is the same thing as multiplying by its reciprocal. Negative 2 over y. Alright, sorry, I'm gonna put that like that and like this. And then the function part repeats since it's an exponential function. And don't forget to evaluate from your bounds x is equal to 0 to x is equal to 1 over y, 0 to 1 over y, dy. From here, notice that where you're plugging stuff in is only the exponential function, right? So this part, there's nothing to plug in. We can move that outside, and then we can just plug it in here. This is just a constant in terms of x. So we can move the negative outside as well. And, well, let's move the 2 outside too while we're at it. So we get negative 2 times integral from 1 to 2 of 1 over y is all we're left with. And then in here, you're now plugging stuff in into the e to the negative xy over 2. So, first one, we have e to the negative x, we can just replace with 1 over y, multiply this by y, divided by 2, right? And then you're subtracting off e to the negative 0 times y over 2. And this is pretty magical, because first of all, notice that this numerator right here becomes 1. And then right here, this entire exponent right here becomes 0. So let's do this again. All this really is e. Okay, well, before we do that, this is e to the negative 1/2, and e to the 0 is just 1. So this is e to the negative 1/2 minus 1. Now, this entire thing is just a constant. It's a number minus another number, 1. So let's take it outside. So you have a negative 2 on the outside, and then we can also include our, include this, which is e to the negative 1/2 minus 1. Okay, and then we have integral from 1 to 2 of 1 over y dy, and integrating this, the constant outside stays, so we have 2 times e to the negative 1/2 minus 1. We have the integral from, well, okay, first of all, the antiderivative of 1 over y is ln y, so let's replace it with that. We're not including the absolute value since 1 and 2, which is our bounds, is always positive or non-negative. So now we're integrating from 1 to 2. At 1, ln y evaluates to 0, right? So we really just need to plug in a 2. Okay, let me just make sure we've got everything straight, because let me think. Okay, it looks correct. Okay. So now what we can do is we can, alright, this is correct. Plug in 2, so I'll do that over here. So this is equal to, this black constant on the outside still is there. In fact, let's use the negative to reverse the order of subtraction on the inside, right? So instead of e to the negative 1/2 minus 1, we now have 1 minus e to the negative 1/2. Multiply by ln y. Sorry, there's a 2 on the outside here, so let me include that as well. Multiply by ln y, and remember we were evaluating this at 2 because 1 went to 0, so that. Almost done. Notice that this 2 is multiplying by the ln2, so you can take the 2 up into the exponent there, and then you can call it done. ln4, there you go. And this is your answer to that double integral. Alright, that's it for number 91. Okay, next we've got number 92. Why is this? Alright. Number 92, we're actually working with the exact same integrand. It is still a double integral over a certain region. E to the negative xy over 2 dA. Now we're working with different bounds though. So we've got R being the area, the region, bounded by y is equal to 1/4 x. Y is equal to 2x. Y equals 4 over x. And y is equal to 1 over x. And here, notice that, well, how do we set up the bounds for this? Well, I mean, let's draw it out and see how it goes, right? So everything here is going to be in the positive region. I'll just tell you that. Our first bound right here is y is equal to 1/4 x. Close enough. Second one is y equals 2x, right? So that's going to go through maybe around here. Third one is y equals 4/x, which looks something like this. And then our last one is y equals 1/x, which looks something like that. So we're integrating over this area? I mean, how do we do that, right? I mean, it's not perpendicular, it's not like horizontal or vertical. We can't really... Okay, here's the idea. Notice that this and that are of a very similar form. Let's put the variables on one side and have them equal to a number. So if you do if you divide both sides of these guys by an x, you get y/x is equal to 1/4, and y/x is equal to 2. Same thing here, let's multiply both sides by x, you get xy is equal to 4, and xy is equal to 1. So what we can do is let a new variable equal to this, right? So that way we're not dealing with weird like stuff that isn't really necessarily in terms of x or y directly. So for this, let's let u equal to that, and let's let our v equal to this. And those are going to be our new variables that we're going to be working with. Let u equal to y/x, and v would be equal to xy, because these are the two variables that we're dealing with in terms of our bounds. So yeah. Okay, and next, what's our next step? Well, here we have either dx dy or dy dx, right? It's just, our differential in area. But we need it in terms of u and v to be able to integrate in terms of, with respect to u and v. So how do we do that? Well, remember the Jacobian. Earlier, I showed you guys that, well, here is what it is formally. dy dx is equal to the absolute value, which I'm going to denote as abs for sake of brevity, of the determinant of partial of x over partial of u, partial x over partial v, partial y, partial u, partial y, partial v. du dv, close. Sorry, no, the absolute value doesn't include the du dv, since those could be either negative or positive, but it includes this part right here. So I'm going to move this out a little. So when we did the polar coordinates for the Gaussian integral, this was what I was trying to express right here. dy dx is equal to the absolute value of the determinant of this matrix right here times du dv. Okay. Earlier during the Gaussian integral, we were working with polar coordinates. However, here we are coming up with our own variables, so we need to still calculate the determinant. This thing in here, the absolute value of the determinant of this matrix, is known as the Jacobian, and it can be notated as such. I don't remember if it was partial or a normal d, but partial yx, right? Since originally this was dy dx, the order matters, and then over partial u v. Okay, and what we can do from here is simply evaluate what dy dx is equal to. But to do that, we need to find these partial derivatives. And notice that we need to differentiate x with respect to u. However, here, x isn't isolated. So let's use this system of equations to write x in terms of u and v. Okay. So first of all, let's take these two and multiply together, right? So uv would be equal to y/x times xy. This x on the bottom and this up here cancel. You're left with y squared. Therefore, root of u... Well, actually, you know what? uv is equal to y squared. And then we need to raise both sides to the 1/2 power. So u to the 1/2 times v to the 1/2 is equal to y. Alright, and we do the same thing for x, but instead we can just plug it straight in. So v is equal to x times y, and we know what y is equal to, so let's just set v equals to x times that thing, right? So v is equal to xy, therefore v is equal to x times that, so that's u to the 1/2, v to the 1/2, which is y. So this ends up giving us, if you divide both sides by u to the 1/2 and v to the 1/2, v over v to the 1/2 is just v to the positive 1/2. So we can put this down like this. And then dividing both sides by u to the 1/2, there's nothing to cancel with, so it's just u to the negative 1/2. So v to the 1/2 times u to the negative 1/2. And let's switch the order of these guys. So my third time trying to write this. U to the negative 1/2 times v to the positive 1/2. That's equal to x. Now let's find what each of these derivatives are, respectively, okay? And then we can find just the determinant of that. So partial x, partial u, okay. We're differentiating x with respect to u. V to the 1/2 is just a constant, so let's put that down first because that's just going to repeat. And then here, if you only look at u to the negative 1/2, it's just a case of not reverse. This is normal differentiation, so this is just power rule. Negative 1/2 goes down here, and then you have u to the negative 3/2. Okay. Next, we have partial x, partial v. Now, it's the same thing, but now we want to differentiate with respect to v. U to the negative 1/2 would therefore be a constant multiple, and then reverse, and then normal power rule says take the 1/2 down, subtract 1 from it, so you get 1/2 u to the negative 1/2 v to the negative 1/2. Next, we have partial y, partial u. This right here is taking this equation and then differentiating with respect to u. So what this gives you is, well, since we're working with respect to u, v to the 1/2 is just a constant multiple. U to the 1/2, we work with this. Take the 1/2 down, and then we put u, and subtract 1/2 from the power, you get, subtract 1 from the power, you get negative 1/2. And we're almost done. Now we just find partial y, partial v, which is our last partial derivative in the bottom right corner. For this one, same idea, except we do it with respect to v. So this is 1/2 u to the 1/2 times v to the negative 1/2, it should be. Okay, and now we know how to find what the Jacobian is equal to, and can now just replace this with the determinant. So from here, the Jacobian, partial yx over partial uv is, so we have the absolute value on the outside, and then we have the determinant of this. We're taking, well, partial x, partial u, and then multiplying it by partial y, partial v. So, let's do some more scratch work. Let's do it up here. So now we want to find, well, it's really just this times that, right? So this guy right here is equal to this times that. And then subtracting off the other diagonal. So partial y, partial u. And then partial x, partial v. So this is what that determinant evaluates to. So let's just put this in here. We're taking dx, du, partial x, partial u, multiplying it by partial y, partial v. So we're taking this right here, and then multiplying it with this down here. Negative 1/2 times 1/2 gives you negative 1/4. V to the 1/2 times v to the negative 1/2, they cancel. u to the 1/2 times u to the negative 3 has, you just get u to the negative 1. All right, and then, so that's the first term done. Now we subtract off the other term right here. Partial y partial u times partial x partial v. So we're multiplying this and this. Yeah, I organize it using the kind of bracket. Partial x partial v is that. Partial y partial u is that. So 1/2 times 1/2 first, that just becomes 1/4 on the outside. U to the negative 1/2 times u to the negative 1/2 gives you u to the negative 1. And then v to the 1/2 times v to the negative 1/2, they cancel, so you're done. All right, and then finally, one last line. Factor out the negative 1/4, right? Sorry, no, and we still have our differentials that we have to multiply in, so that's du, dv, right? Here, what we can do is multiply out a negative 1/4. Is that correct? Is that a negative 1/4? Let me check really quickly. Yeah. Actually, no, these are like terms. So what we can do is combine like terms. So this is equal to the absolute value of negative 1/4 times negative 1/4 of this minus 1/4 of this is just negative 1/2 of this. So let's put down negative 1/2 of this, which is u to the negative 1, du dv. Now the absolute value of the product is the product of the absolute value. So you can break this into two. So you have absolute value of the negative 1/2 times the absolute value of u to the negative 1, which is, du dv, of course, which is, of course, just equal to absolute value of negative 1/2 is just positive 1/2. And then u, if you look at what our range of u, so we let u equal to y over x, and then y over x goes from 1/4 to 2. So it's never negative. So therefore, it's just u to the negative 1. Like that. Okay, and you're almost, and of course, partial u, partial v. All right, and we're done with our Jacobian work, because notice that this is just our Jacobian. All right, what do we do from here? So this means u goes from, well, let's just notate it as this. Goes from 1/4 to 2, and then v goes from 1 to 4, right? Okay, so let's put down our integral. So this thing is equal to the double integral of e to the negative xy over 2. So our dA, well, we set it up to be du dv, right? Oh, and one thing, we have to put everything here in terms of u and v. So notice that v is xy, so we'll replace this with e to the negative v over 2. We saw that typically we use dy dx for whatever bounds, but we changed it to equal to our Jacobian right here, which is that. So here we get 1/2, well, 1 over 2u, I guess you can write it like such, and then du dv. Finally, we want our bounds. So first on the inside we have our u, so this is 1/4 to 2. And then on the outside we have our v, which is 1 to 4. Okay, and that's it. That's all the differential work done. So I'm gonna get rid of this now. Just keep this in mind. Yeah? This part. I need to check if my work is actually right. So okay, it appears like it is. So now, yeah, get rid of everything from here down. Yeah. So yeah, we don't need any of this. But we still have to do a lot of change of variable problems in the future, so don't forget that. Now we're just working on this. Okay, notice that here, e to the negative v over 2, we're first going to integrate with respect to u, right? So we can take this outside since it's a constant in the u world, essentially. So 1 to 4, and then we took the e to the negative v over 2 outside of our inner integral, which is integral of 1/4 to 2 of 1 over 2u du dv. Next, notice that nothing inside of this integral right here is going to have a v. So there's no point. So this entire integral right here is a constant, right? In terms of, well, integrating this with respect to v, right? If you just look at this integral as, say, a number, such as k. K has nothing to do with v, right? Just like this entire integral has nothing to do with v. So typically you would take k outside, so let's just take this entire integral outside. So that gives you a pretty cool insight as to how this works. So let's take this u integral outside. And in here you have a 1/2, so let's take that outside. And then you just have a 1 over u left in here, du. And you're multiplying by integral from 1 to 4. E to the negative v over 2, this is a v, dv. Okay, and this brings me back to something I wanted to explain back in the Gaussian integral. If you remember this, we were integrating from 0 to infinity twice, right? And we had e to the negative x squared, we took this 0 to infinity e to the negative x squared dx, then we multiplied it with the dy counterpart, so 0 to infinity e to the negative y squared dy. And what we did was we brought these integral signs together. So it ended up looking like this. This x integral ended up on the outside, the y integral ended up on the inside, and we just had to multiply the insides. So that would give us e to the negative x squared minus y squared. And then we had our y on the inside, right? And then the x on the outside. And the reason why we could do this is because, well, the opposite is true. Is because you could take two guys being multiplied apart together like this, move the function part that's only with respect to one variable to the outside of one of the integrals, and then take the entire inner integral. If it has nothing to do with the other variable, then you can move that outside, and it's equivalent to this. So essentially what we did here, from here to here to here, is the opposite of what we did from here to here. Instead of taking, so here we took the integral and we split it apart into two, so it's easier for us to deal with. And here what we did was took two integrals, put it together so it looked a lot nicer, and we could use polar coordinates. So that's a justification for that step. Okay, back to number 92. This is pretty easy because you're just multiplying two integrals. The first one, 1/2 stays outside, and this is just natural log of u. I'm gonna keep u outside of absolute value since there's no value of u here that is negative. And evaluate this from 1/4 to 2. Multiply by this right here is an exponential. This is a v times negative 1/2. So reverse chain rule says divide by negative 1/2, which is multiplying by negative 2. So you have a negative 2 multiplying on the outside here. And then the exponential part repeats. So we have e to the negative v over 2, and then evaluate from 1 to 4. All right, here, the 1/2 stays outside. You just plug in 2. And then notice that if you plug in ln of 1/4 is equal to negative ln 4. So let's subtract off ln 4. And then this 2, remember these are multiplying. So this 2 and this 1/2, they cancel. And we can take this negative in red right here and put it on the very outside, so like this. Here we plug in 4 for v and 1 for v. So we have e to the negative 4 over 2 is 2. And we subtract off e to the negative 1 over 2 is just, well, 1/2. Almost done. ln2 minus ln4. In fact, what you can do is use this negative on the inside to interchange the order of subtraction, so you get ln4 minus ln2. And, well, the rest stays the same. E to the negative 2 minus e to the negative 1/2. I'm going to keep this like this. You can write this as 1 over e squared, and this you can write as like 1 over root e, and then distribute our final log value, and there's no point. Right here, combine the insides of the logs, you get natural log of 4 over 2, which is just 2. So you get ln2 times, well, let's put this down first. So e to the negative 2 minus e to the negative 1/2 times ln2 is your final answer. Don't plus c, since this is just a number. It represents a volume. Oh my god. That took me like 25 minutes to do one question. But, I mean, I introduced a lot of new concepts, so makes sense. Okay, that's number 92. And yeah, let's keep going. Whew. Alright, number 93. Allow me to check that my phone is still recording, which it is. We have double integral over region R again. So, double integral region R. This time we have a nicer integrand, x squared plus y squared, and then dA. So R this time is, well, a square with corners, well, vertices 0, 1, 1, 0, negative 1, 0, and 0, negative 1. Okay, so from here, what does this look like? Well, I mean, here, take a look at this, right? And then a square with, well, one of the corners is 0, 1, one of them is at 1, 0, one of them is at negative 1, 0, and one of them is at 0, negative 1. So if you connect the dots, you get a square-looking thing. So you're integrating over the entire area enclosed by these. And we need to find a way to put these boundaries into math terms, quantify them. So this one, let's write them all in slope-intercept form. This one is the slope of negative 1, so y equals negative x, and the y-intercept is 1. This one is y is equal to, the slope is positive, and then your y-intercept is 1. So this is just y equals x plus 1. This one, negative slope, negative y-intercept, so this is y equals negative x minus 1. This one right here is y is equal to negative intercept and positive slope, so x minus 1. Alright, so from here, recognize that you can't really put it straight into the bounds if you're working with only x and y. So just like last time, let's isolate the number, and then let's see what kind of change in variable we can make. So from here, notice that, let's work with this equation. If you subtract x on both sides, you get y minus x is equal to 1, right? Same idea with this one. Y, subtract x on both sides. Y minus x is equal to negative 1. For this equation up here, you get, if you isolate the number, you get y plus x is equal to 1. And then down here, add x on both sides again, you get y plus x is equal to negative 1. Okay, so change in variable. Y minus x we can call u, and y plus x we can call w. I'm going to use w this time because v looks kind of like y, so it tripped me up a couple times. Alright, and now our next task is to find our, well, you know what, yeah, this is xy. And then this is, let's call this uw. next task is to find our Jacobian. So we're looking for the determinant of, well, let's just put it down like this. So absolute value of the determinant is, well, yeah, let's just put it down. And then let's fill in the matrix with our values. So upper left corner, we have partial x, partial u. Actually, first of all, we need to isolate x and y in terms of u and v. So here we can just add the two. We get 2y is equal to u plus w. Therefore, y would be equal to u plus w over 2. And then, if you subtracted the 2, then you get negative x. Well, the y's would cancel. You get u minus w equals negative 2x. Dividing both sides by negative 2, you get w minus u over 2. Okay, so x is equal to w minus u over 2. Right? Does it make sense? Does it make sense? Okay, I'm guessing it does. Let me work this out one more time in my head. Okay, that makes sense. So, now we gotta find partial x, partial u. Take x, differentiate with respect to u. In fact, let's split these guys up. So we can rewrite this as w over 2 minus u over 2 to make it clear that these are two different terms. This one let's put as w over 2 plus u over 2 to make it clear that there are two different terms. dx, du. Right here, w over 2 is a constant that goes away. And then the u right here, negative u over 2, sorry. The derivative of that is just negative 1 over 2, so negative 1 over 2. Alright, secondly, we have x with respect to w, right? Same idea, except, yeah, now this is our constant, and then the w over 2, we're differentiating that. That just gives us simply 1/2. Y, dy, du is 1/2, and then here we get 1/2 again. Okay, so yeah. Now let's solve for what this is. So this is the absolute value of this times that is negative 1/4. This times that is positive 1/4. Does that make any sense? Does that make sense? Wait a second, because if this is positive 1/4, no, you're subtracting off that, so minus, right? So this times that minus this times that. That's what I forgot. So you're subtracting off 1/4. du dw. This is equal to, well, absolute value of negative 1/4 minus 1/4. Negative 1/4 minus 1/4 is negative 1/2. Absolute value of negative 1/2 is just positive 1/2. So you get 1/2 du dw. So this is your new variable. Okay. Here, notice that this right here, y minus x, we set as our u. So u ranges from negative 1 to 1. And then same idea here. This is our v. It also ranges from negative 1 to 1. Sorry, not v, w. And this also ranges from negative 1 to 1. Yeah, as such. So let's rewrite this up there. Okay, here we have our double integral. Remember, well, you know what? Let's put down the inside first. We still need to solve for x squared plus y squared. So let's just take each of these guys and square them. So to find what the inside would be equal to. W, and what we can do right now is factor 1/2 out of each of these. So x squared, well, x squared plus y squared is equal to 1/2 times w plus u, right, all squared, and then add it with, you can also factor 1/2 out of here, 1/2 w minus u all squared. Here the 1/2 squared gives you 1/4, and the 1/2 squared here gets you 1/4 as well, so you can factor that out both. Now you just have w plus u squared, which is w squared plus 2uw plus u squared. Here, w minus u squared just gives you w squared minus 2uw plus w, sorry, not w, plus u squared. Okay, from here, the 2uw and the 2uw cancel, so that's really nice. Right. And then you can combine the w squareds and the u squared. So you get 1/4 times 2w squared plus 2u squared. Okay, from here, what we can do, factor 2 out, you get 2/4. That's just 1/2. You get 1/2 times w squared plus u squared. Okay, and then here, this is now your new integrand, so let's put that in. 1/2, of course, is a constant multiple, and we can drag that outside. And this 1/2 is also a constant multiple, so we also drag that outside. In here, w squared plus u squared, so we can switch the order, whatever, it doesn't matter. Out here, we put the 1/2 outside, so this is just dw, sorry. U bound, -1 to 1, so that's on the inside, and then w bound, -1 to 1. You can split this into 2, right? Well, no, you can't. These are additive, so let's just work on it as such. Okay, from here, we're almost done. Since the primary exercise of these guys is to do the change of variables, so let's work out the inner integral. So the 1/4 stays outside. You have -1 to 1. Integrating u squared plus w squared with respect to u, you get 1/3 u cubed, and then you multiply u into the w squared, because that's a constant in the u world, and you're evaluating from -1 to 1. So I have a dw on the outside. Okay, equals 1/4. -1 to 1. In here, plug in a 1. You just get 1/3 in the first term. So you can write that. And then plus 1 times w squared. So it's just w squared. And then you want to subtract off. Plugging in -1 into there, you get 1/3 times -1, which is -1/3. And then a -1 into there, you get negative w squared. Close, dw. You can add this 1/3, this is positive 1/3, plus positive 1/3. That gives you 2/3, and yeah, so 1/4 times integral -1 to 1. And as we were saying, yeah, just the 2/3 here. Positive w squared times double negative w squared, so that's positive, so you get 2 times w squared. And let's bring the 2 outside, so 2/4 is 1/2. You get integral from -1 to 1, and this first term becomes 1/3. The second term becomes w squared. Okay, and from here, simply integrate. 1/3 in the w world is just 1/3 w. W squared in the w world is just 1/3 w cubed, and you're almost done. Because all you have to do is evaluate from -1 to 1. Let's factor out the 1/3 first, and you get a 1/6. So in here, our first one, plug in 1. We factor out the 1/3, so you just get a w equals 1, so it's 1. 1 into here also gives you 1, so you're just doing 1 plus 1. Subtract off. -1 to here, you get -1. -1 into here, -1 cubed is -1, so you're -1. Alright. Finally, 1/6. 1 plus 1 is 2. -1 minus 1 is -2. -2 is +2. So all in all, 2 plus 2 is 4. 4/6 is also same thing as 2/3. All that work just to get to that answer right there. Okay. That's number 93. This is a really just a big exercise in doing change of variables. Alright, we're almost done. We got number 94. Yeah. Okay, so number 94. Double integral over region R with integrand, same thing as last time, x squared plus y squared dA. And the r this time is defined as not a unit, well, not a diamond, right? But instead, we've got a unit circle. With center 0, 0. Yeah. Alright, so how do we do this one? Well, you have an x squared plus y squared here, and you also have a unit circle, right? It's kind of difficult to work with the unit circle in standard Cartesian coordinates, so let's change it to polar coordinates, right? So polar coordinates, well, we know how this works. It's just radius and your angle from your origin. Additionally, this right here is basically setting you up for doing that because x squared plus y squared in polar coordinates is just r squared. So, let x equals to r cosine theta, y equal to r sine theta, and then dA, which is like dx dy or dy dx, equal to r dr d theta, which comes from the Jacobian for polar coordinates that we derived a while ago. Alright, yeah, so now we can plug this all in here. So we have the double integral, and we'll decide what the bounds are in a second. Inside, you have x squared plus y squared is just r squared, so we can put down an r squared. Recall that you have your dA being r dr d theta, so there's another r being multiplied in, making this technically r cubed, and then you have your dr d theta. Alright, the inner bounds for the integral just are the radius, right? And this is a unit circle, so the radius is always going to be 1. So you're integrating from 0, sweeping all the way out to 1, right? Like that. And then in the other dimension, you have taking this 0 to 1 radius and then sweeping it the entire way around, right? Your theta. So that's just going to be 2 pi radians. So you're starting at 0 radians and you're going all the way around to 2 pi. Like so. Yeah. And now, just like I demonstrated earlier, you can take the inner integral outside because that has nothing to do with theta, right? It's a constant in the theta world. So you can do this. 0 to 1, r cubed dr times 0 to pi over 2 pi d theta. From here, you can go ahead and solve. Integral of r cubed is 1/4 r to the 4th. Evaluate from 0 to 1. 0, this thing goes to 0, right? And then we have our other guy right here. Integrating d theta just gives you theta, and you also have to evaluate from 0 to 2 pi. At 0, this also goes to 0. So let's just plug in 1 and then 2 pi. So plugging in 1, well, it's just 1/4 times 1 to the 4th, which is just 1/4, right? And then plugging in 2 pi into theta, you just get times 2 pi. So, like so. This 2 over the 4, it reduces down to become a 1/2, so you just have a pi left in the numerator. So this gives you, all in all, pi over 2. Yeah? Yeah. There you go. That's number 94. Okay. Yeah. Okay, next we have number 95. Double integral over region R. And now our integrand is x plus y all squared. And then we've got sine squared of x minus y dA. Alright, and what's our region R? It's the square with vertices, well, square with vertices 0, 1, 1, 0, negative, wait, sorry, 1, 2, sorry. 1, 2, 2, 1, and then 1, 0. So what does that look like? Well, if we take a look, well, this is only in the first quadrant, right? If you take a look at the coordinates, it's only in the first quadrant, so I'm only going to draw that out. All right, so we've got 0, 1, which I'll say is here. We got 1, 0, which I'll say is here. Got 1, 2, so that's 1 out and then 2 out. And then we've got 2, 1, which is over here. So you're integrating over this square right here, right? All right, and just like before, 2 questions ago, number 93, we found the equations for each of these lines, and then we made a change of variable since these are all like not, well, yeah, none of these bounds can be expressed nicely using constants. Unless you were to break it into 2, but that's a different story. How would you break it into 2? I'm not even sure. All right, anyways, so from here, this top line right here is, if you just extended this line, right, you'd find the y-intercept would be equal to 3. So the line, or the expression for this line, and the slope is negative 1, so this is y is equal to negative x plus 3. This right here, if you extended this line down, and then you had the slope continue, this would have a y-intercept of negative 1, and the slope is positive, so y is equal to positive x minus 1. For the third line right here, y-intercept is positive 1 and the slope is negative 1. So y is equal to negative x plus 1. And then right here, we have a positive 1 slope and a positive 1 y-intercept. So y is equal to x plus 1. So these are our 4 bounds. So yeah, as I said, we need to do a change of variable, right? So let's just get all the x's and y's on one side and see how we can do this. So let's work on this one first. So we add x on both sides, you get x, well, let's put it down like this. Y plus x is equal to 3. And then here, add x on both sides, you get y plus x is equal to 1. All right, and for the other 2 sides, we've got subtract x on both sides, you get y minus x is equal to negative 1. And then here you've got y minus x is equal to positive 1. All right, so therefore you can see that we can let one variable be y plus x and then the other variable be y minus x. And we've actually done this in question 93, but let's work out the Jacobian again. Okay, so let u equal to y plus x. Let w, let's use w, equals to y minus x. Okay, and from here, let's set up our Jacobian, all right? So, partial, well, yeah, we'll put it down like this. Partial xy over partial uw equals. Okay, for this one, we're taking the absolute value of the determinant of your partial derivative matrix. So, let's put this down. Absolute. Well, you know what? Yeah, let's put the ABS down, because it looks cleaner, at least. In here, you have the determinant of what? So, determinant of, okay, and now you want to find the partial derivatives of x with respect to u and y with respect to, so you need to be able to isolate y and x. So, just like last time, if we add these two, we get u plus w is, first of all, the x's would cancel out, so you get y, right? And no, 2y actually. It is equal to, and then you just added the 2, so you have w plus u. Divide both sides by 2, you get y is equal to, yeah, like that. All right, what about x? X, you could subtract the 2, right? You get, well, let's subtract this one, u, from w, right? So that way you would get, other way around. So let's subtract w from u. So let's reverse the order of this because Okay. U minus W is just U minus W. Alright. Y minus Y cancels. X minus negative X is just 2X. So 2X is equal to that. Then divide by both sides by 2. You get X is equal to U over 2 minus W over 2. Like this. Okay, so these are your two equations that you're finding partial derivatives of. Alright, in the top left corner, you want to find your partial derivative of X with respect to U. So you take X and differentiate with respect to U. Negative W over 2 becomes 0, and then since you're just differentiating U over 2, and U is your variable, you just get 1/2. Alright. Secondly, for the next one, you get partial X over partial W. So you still take the derivative of this, but with respect to W. U over 2 goes to 0, and then you have the negative 1/2 times W, which just becomes negative 1/2. Then you have dy du, which is taking this and with respect to U. W over 2 goes to 0, and then derivative of U over 2 with respect to U is just 1/2. I'm going to move this negative on top so it looks cleaner. Okay, and then finally we have dy dw, sorry. So just that with respect to W. U over 2 goes to 0. A derivative of W over 2 with respect to W is just 1/2. So this is what we get. Sorry. And your D will order. So you start with U and then dW. So du, dW. Okay. All right, from here, you can go ahead and calculate the determinant. So you get absolute value of this times that minus this times that. Okay, so 1/2 times 1/2 is 1/4. And then subtract off this times that. So that's subtracting negative 1/4, which is just adding 1/4. And this in here just gives you positive 1/2. Yeah. Okay, and the absolute value of positive 1/2 is just going to be positive 1/2. So therefore, this thing is going to equal to 1/2 du dw. All right. So we know that now. We can now set up our integral, because notice that in the integrand, x plus y is one of our variables, right? We have this equal to u, and then x minus y is another one of our variables. It's just negative w, but we can sort out the negative on the inside in just 1 second. So you have double integral, and we'll set up the bounds in a second, right? And then in here we have x plus y, which is a u squared. And then you have sine squared of x minus y, which is, well, negative w. However, sine is odd. So if you think about sine of negative w all squared, which is basically what that is, right? Then you can take the negative to the outside of the sign, so you get negative sine w squared. And then the negative, well, you can bring it outside. Negative 1 squared is just 1, so this is just simply equal to sine squared w. This is even. Sine squared is even, right? We just proved that as well. So that negative w, the negative in the argument is negligible because of some properties of sine. Next, we have differential 1/2 du dw. So let's just put that down. All right, so first, on the inside, we're integrating with respect to u. So with this, what do we do? Well, we want to find your u bounds, right? So what value do you start at? What value do you end at? Well, notice that your u is y plus x, right? Y plus x goes to 3 and starts at 1. So therefore, u goes from 1 to 3, right? You're starting at 1 and going all the way up to 3. So the inner bound is from 1 to 3. What about the outer bound with respect to dw, right? Well, that's y minus x. Y minus x starts at negative 1 and goes to 1. So, and I'm going to put this down as well. There you go. That's your new integral. All right. And yeah, I'm going to get rid of all this, and then we can do some quick integration. So, yeah. I don't think we need any of this. Okay, and from here, what we can do is, well, notice that 1/2 is constant multiple. Let's bring it outside. And then inside consists of purely functions. So you have u squared and then sine squared w du dw. All right, notice, first of all, that you're first integrating with respect to u, so this sine squared w is just a constant multiple, right? Since the sine squared of w has nothing to do with u we're working on first. So let's take that to the outside. So we took the sine squared w outside. We're integrating from 1 to 3, and then we have our u squared du dw. And take a look at this part. From here to the du, none of our bounds have any w's in it, so it has nothing to do with w. It's completely independent. So in the w world, which is what we have on the outside, this is just a constant, because u has nothing to do with w, right? So let's bring that outside once again. And once again, I thoroughly went through what I went over in like question 93 with splitting up the integral into two integrals multiplied together. Yeah. So you have the 1/2 that stays outside of both, and then you can take this guy outside. So you have integral from 1 to 3 u squared du on the outside, and then you have this and then that. So integral from -1 to 1 sine squared w dw. Okay, first thing I want to mention. Earlier, we saw that sine squared w is even, and we're going from -1 to 1. That means we're able to multiply it by 2 and then just start from 0. So we can start from 0 and then multiply this guy by 2. Notice that this 1/2 and this 2 subsequently cancel. All right, so all we need to do is evaluate this and evaluate that. First of all, sine squared, let's change it so that it's 1/2 times 1 minus cosine of 2w, right? And the 1/2 can go outside, so we have another 1/2 out here now. And let's work on this first. So bounds stayed the same. On the inside, we changed it to 1 minus cosine of 2w using an identity, a trig identity. And then we have this thing in red right here. And that's much easier to do. Integrating u squared du, you just get 1/3 u cubed. So you're multiplying by 1/3 u cubed. And then you're going from 1 to 3. Okay. This one, you're almost done. All you need to do is, integrate it. So we got 1/2. Integrating 1 with respect to w, you get w. And then integrating this guy, the negative stays. And then there's a 2 times w on the inside, so you want to divide by the 2 on the outside because of reverse chain rule. Integral of cosine, is sine. And then the argument remains the same. And then let's close this parentheses, and then you're integrating from 0 to 1. Okay, and then that's it for this black part. Let's work on this outer part now. So we're going from 1 to 3, right? So here we're multiplying. Let's plug in 3 first. So we have 1/3 times 3 cubed. And then we're subtracting off this thing, but you plug in 1. So 1 cubed is just 1, so it's just 1/3 times 1, which is just 1/3. Okay, and your next step is, I guess you can simplify this. You can plug in balance for that. So let's go ahead and do that. So, in fact, let's work on this and that first, right? The 1/2 and the 1/3. Since out of both of these terms, notice you can factor a 1/3 out, right? And then after you move 1/3 out, you have it times this 1/2. That would just become 1/6, right? Okay, let's take a look at this. So we factored the 1/3 out of both. So this is now just 3 cubed, 27, minus, 1, right? So that's just, 27 minus 1. All right, in here, notice that If you plugged in 0 into both, 0 minus, well, 1/2 sine of 2 times 0, which is 0, sine 0 is 0, 1/2 times 0 is 0, 0 minus 0 is 0, so this thing's gonna go to hell. And then we just plug in 1. So here, w is 1 minus 1/2 sine of 2 times 1 is just 2. Okay? Alright, next what you can do is move this on top. So 27 minus 1 is just 26, so you get 26 over 6. However, notice that this can reduce down. If you divide both the top and the bottom by 2, this reduces down to a 1/3 over 3. 13 over 3. Okay, so that's these two. And then over here, you're still multiplying by 1 minus 1/2 sine 2. And I'd like to make one more adjustment, distribute this in. So 13 over 3 times 1 is just 13 over 3. 13 over 3 times 1/2 is 13 over 6. So you're subtracting 13 over 6 times sine 2. Okay. Box that, and that is your final answer. Alright, that's it for number 95, and yeah. Let's move on to number 96. Number 96. Where is it? Okay. Well, let me put down 96 first. 96. Double integral over region R. My bad. And then your integrand is natural log of x squared plus y squared plus 1 dA. Where region R is a unit circle centered at 0, 0. So okay. From here, set up bounds. Well, once again, you can use polar coordinates. Let me draw this out real quickly just in case it might be helpful. Well, close enough, right? So you're integrating over this entire region right here. Alright. This is 1, this is 1, this is -1, and this is -1. Alright, so R theta again. Alright, let's use polar coordinates. Also because there's this x squared plus y squared up here. And yeah, we're integrating over a circular region. So let x equal to cosine theta, r cosine theta, and then y would be equal to r sine theta. Your dA, which is dx dy or d by dx, doesn't matter, would be r dr d theta. Okay, so from here, let's go ahead and write this integral. So we have our double integral. I'm gonna put in the bounds later. We have natural log of, well, x squared plus y squared is r squared, and then we have it plus 1. And then dA is r dr d theta. Alright, in here, first notice we're integrating with respect to r, so we want to find the radius. Once again, this is a unit circle, so we're going from 0 to 1, right? Think of it as sweeping from 0 to 1 in this first dimension. And the second dimension, which is your theta, which is like your rotation dimension, you're rotating all the way around. So from 0 radians all the way up to pi over 2 to pi to 3 pi over 2 all the way to 2 pi. So you're starting at 0 and you're sweeping all the way to 2 pi in terms of your angle. Here, well, you can break it up, right? So this inner integral right here has nothing to do with theta. The bounds are constants, so there's no theta on the inside. It's a constant in the theta world. Let's bring it outside. So that looks like this, 0 to 1. Let's put the r in front. R times natural log of r squared plus 1 dr, right? And then we multiply by your outer integral, which is from 0 to 2 pi d theta. Let's work on this one. I noticed this real quick. It's just going to, well, okay, you know, let's do the substitution for here first, because notice that the argument of the natural log is quadratic, and then RDR is linear, so you can use that as your differential. So let u equal to r squared plus 1. du would be equal to 2rdr. Notice that we have the rdr here, no 2, so let's isolate the rdr. You get, 1/2 du is equal to rdr. Alright, from here, first of all, let's move the 1/2 outside. And before we do any of this, I want you to notice that right here, this is very easy. Integrating, you just get theta from 0 to 2 pi. 0 goes to 0, of course, and then just plug in 2 pi, right? So you're just multiplying all of this by what is fundamentally 2 pi. So let's multiply that in first. And then notice the 2's cancel, and then, yeah. So next we have the integral from, these are in terms of r, we want them in terms of u, since our new integral is in terms of u. So let's plug these r values into our r, and then put it out here, u. So plug in 0, 0 squared plus 1 is 1, so u is equal to 1 for our lower bound, and then 1 up here, 1 squared is 1, add 1, that's 2, u is equal to 2, so you're going from 1 to 2. And then you have rdr, we said was our 1/2, and then du, right? So now we just have the natural log. We have natural log of, the inside is just u, and then we have our du as I mentioned earlier. From here, you can do integration by parts. For this, once again, I'm going to consider it a standard form. So first of all, we have this pi on the outside. Well, I'm not going to put this in red. I'm going to put this in black. We have pi. And then we have this guy. So integrating this, we get u ln u minus u, and then we have to plug in bounds 1 to 2. All right, almost done. Let's bring it up here. So we have our pi sitting on the outside, looking really nice and stuff. All right, here, let's plug in 2 first. So you get 2 ln 2 minus 2, right? So 2 ln 2 minus 2, and then you want to subtract off your function evaluated at the other bound, 1. So if you plug in 1 into the first term, ln 1 just 0, so it zeroes out the first term, and then you have this negative u left, which is 1, negative 1. So you're just subtracting off negative 1. Almost done. Right here, this is just plus 1, right? So minus 2 plus 1 is just minus 1. So we got our pi, got our 2 ln 2, and then minus 2 minus minus 1, which is plus 1. Minus 2 plus 1 is just minus 1. Finally, let's take the 2, let's take the 2 up into the exponent. So that makes us ln 4, and at the same time, let's distribute pi. So distributing pi, you get pi, and then you have the log, which we turned into an ln 4, and then distributing the pi into the negative 1, you just get minus pi. All right, nice. So that's this one using polar coordinates. Pretty self-explanatory, I'd say. So, yeah. Okay, that's number 96. Number 97. So we've got, once again, it's a double integral over region R, and we got sine of root of x squared plus y squared dx. Sorry, wait, no, that's not it. That is not it. There's 2 variables, and we haven't set up bounds, so it's dA. That looks pretty nightmarish. You're probably hoping for polar coordinates, so let's define R next. So R is quarter circle, so we do get to use polar coordinates. In the first quadrant, R2 and center 0, 0. So your radius is 2, and then your center is 0, 0. So let's sketch that out. Once again, this is in the first quadrant only, so I'm only going to draw out the first quadrant. Let's say this is 2. Let's say this is 2, right? So it's going to be a quarter circle. that looks like this. And we're integrating over that area. And your center, notice that is 0, 0, right? Alright, so you're integrating over this. Okay, so let's make our substitution into polar coordinates, since obviously this is a semicircle. Let x equal to r cos theta, y is equal to r sine theta, and then your dA is your r dr d theta. Okay, next, let's go ahead and just figure out the bounds and all that stuff. On the inside, sine of, well, x squared plus y squared is r squared in polar coordinates, and then square root of r squared is just r. So this is very nicely just sine r. And then you have your dA, which is r dr d theta. Here, let's set up bounds. So on the inside you have r, right? Your radius, instead of going from 0 to 1 like we do on the unit circle, here the radius is 2. So we want to sweep starting from 0 all the way up to radius 2, right? So let's go from 0 to 2. And then here, because we're only turning a quarter circle, and we're taking what we originally did already, we swept across a line, and then we want to turn it in the other dimension, which is the rotation, only 90 degrees, which would give us a quarter circle. 90 degrees in radians is pi over 2. So let's put down 0 to pi over 2. Start at theta equals 0, all the way up to theta equals pi over 2, right? From here, we can integrate. Notice at the inside, you can actually move it outside again. So this gives you integral from 0 to 2, r sine r dr. Multiply by, then you have the outer integral, you have integral from 0 to pi over 2, and then you just have d theta. Alright, once again here, I want you to notice this integrating is just theta from 0 to pi over 2. Evaluating theta at 0 is just 0, right? So you just evaluate theta at pi over 2, right? Which gives you this, and then this is just pi over 2. So pi over 2 is your multiple. So, okay, so keep that in mind. This entire thing is equal to pi over 2, right? So, but now I want to do integration by parts for this inside part right here. So, differentiate, and then integrate. Differentiating, you want to differentiate the polynomial, because you're able to integrate the other thing, which is just integrate function sine r. Differentiating this, you get 1, and then 0. Integrating sine r, you get negative cosine r. Integrating negative cosine r, you get negative sine r. Multiply diagonals, then the row went to 0, so no integration. From here, we can go ahead and continue. Remember that this thing that's being multiplied on the side is just pi over 2, so let's put that down first. And then we have this guy right here, which is, well, we can split up into that, right? First term is negative r, and then times cosine r. Then negative makes a positive. 1 times sine makes sine. And then don't forget to evaluate from at your bounds, 0 to 2. Okay, notice evaluating at 0, the entire thing is just going to 0 out, right? So this r is going to 0 out this term, and then sine 0 is just 0, which is zeroing out that term. So it's just this thing evaluated at 2. So you're almost done. From here, we can go ahead and let's plug in 2 and also distribute in the pi over 2. So we got pi over 2, and then let's put the negative up front, and then the r becomes a 2, right? And then you have your cosine 2. Alright, next, plus pi over 2 distribute into the second term, and then you have your sine, and then in the argument, r is just 2. So like that. You're almost done. Cross these out, and let's switch the order. So let's have this minus that. So pi over 2, sine 2, and then minus pi cosine 2. That is your answer to number 97. Once again, using polar coordinates. Polar coordinates is a really helpful tool when it comes to dealing with these semicircles, because otherwise you need to set up bounds that well, they look like this. Yeah, so no one wants to do that. And of course you could. I just highly advise against it. Okay. That's it for number 97. Let's move on. We got number 98. Number 98. Double integral over region R again. This time it's a little quirkier. On the inside you have y times sine of xy dA, where R is bounded by xy equals 1, xy equals 4, y equals 1, and y equals 4. So what does that look like? Well, right here. Y is equal to 1 is like here, right? And then y is equal to 4 is like up here. So we're going between these two lines. Then we have our other two bounds, xy is equal to 1, which looks something like this. And then xy is equal to 4, which looks something like that. Right. So it's this area right here. Notice, since this is a constant and this is a constant, well, we can just integrate normally, right? Okay, and this constant is, by the way, this is y equals 4, this is y equals 1, this is xy is equal to 4, and this right here is xy is equal to 1. So let's set up our double integral then. Because there's no change of variable needed, since you have these two curved lines which can be on the inside, right, because they need to be in terms of another variable. However, on the outside you can have these constants. So on the outside, well, okay, you know what, let's set these up. Let's set up the inside first. So we have y times sine of xy. Yeah, okay. And then we have our dA. So dA, we want this to be dx dy, right? Since our y values are constants and the outsides need to be y equals something and they need to be constants too. So let's put the y values down first. So we have 1 to 4 because we're going in between this. And on the inside, we have these curved lines. We need these as x in terms of y, so they need to be in terms of y. Isolating them in terms of y, you get x is equal to 4 over y. And then here you get x is equal to 1 over y. So we're going from... Well, on the top we have 4 over y, on the bottom we have 1 over y. Let's go ahead and integrate this with respect to x. Oh yeah, also notice that integrating with respect to x first, really nice, since y is just a constant, you're just integrating normal sine. Okay, so here we go. Outer, and by the way, this one we can't split up since the bounds are in terms of y, so this does, the inside integral right here does affect the outside one. So let's put down the outer bound and the inner bound. So integrating this guy with respect to x, y is just a constant, let's keep it on the outside. Integrating sine, you get negative cosine, so let's bring the negative outside, and then we have our cosine of our xy. In here, x is our variable, y is a constant, so we have to divide by the constant because it's being multiplied by the variable, because of reverse chain rule. So let's do a 1 over y outside. This and that cancel. That's really nice. And then we have, well, our bounds from 1 over y to 4 over y. And you just have your dy left. Alright, now we can go ahead and plug in bounds. So we've got, what's this? Alright, 4 times, no, negative integral from 1 to 4. On the inside, let's evaluate at upper bound first. So you got cosine of 4 over y times y. And then you're subtracting off this, evaluating it at the lower bound, which is cosine of 1 over y times y. Alright, and then close it and you're done. These cancel. So on the here, what you're left with is integrating from 1 to 4. This is cosine 4 minus cosine 1 because all the variables canceled out. So you can actually move this outside as a constant, which is really, really nice. So You move this outside, this becomes cosine 4 minus cosine 1. Right, and then you have the integral from 1 to 4 dy. Alright, let's reverse the order of subtraction here, so you get cosine 1 minus cosine 4. Here, integrating dy, you just get y, and then plug in bounds from 1 to 4. Okay, so let's go ahead and move this up here. This is a constant on the outside. We only need to evaluate the part in red. So this is cosine 1 minus cosine 4. The y, so from 4 to 1, well 1 to 4. So okay, in here plug in 4 into y, you just get a 4. And then subtract off this function value at the second bound, which is 1. All in all, this becomes a 3. So you're just multiplying a 3. Distributing the 3, you get that this, all in all, is equal to 3 cosine 1 minus 3 cosine 4. Yeah, that's it for number 98. You're almost done. We got like 2 more questions, not including your bonus one, but that's it for this one. Alright, so next we got number 99, almost done. And we're integrating, well, over region R, and our integrand is square root of 1 plus y squared dA. Okay, well, we'll see how this goes, because it looks kind of ugly so far, but introducing our region is a triangle with vertices 0, 0, 0, 1, 1, 1, like that. Alright, next, what you can do is, well, let's draw it out, because it doesn't seem all that bad anymore, right? You can at least do this with normal xy Cartesian coordinates. So 0, 0, 0, 1, which is like up here, and then 1, 1, so like up here. And then this is our little triangle right here. Alright, so this is constant and that's constant. This down here is constant. This height here is the only thing that's in terms of another variable. So let's go ahead and figure out, well, what these lines are. First of all, this one, well, this is y value equals to 1, so this is y equals 1. This down here, the lower y bound is y is equal to 0. This diagonal line is y is equal to x. And then this vertical line right here is x is equal to 0. So yeah, right now it's looking really good. We just gotta plug in our bounds and decide which order we want to integrate in. So let's work on our bounds in a second. Let's put down our square root of 1 plus y squared, and let's figure out what order we want to integrate it in. So integrating with respect to y first, you need a trig substitution, and it's going to end up looking pretty ugly, so I would not do that. Also consider that you also need to plug in a bound that's in terms of another variable, so that might end up looking even worse. So I wouldn't do that. So let's, instead of integrating with respect to y first, let's integrate with respect to x first, and then integrate with respect to y. Hopefully the bounds will clean it up. Okay, our x bounds. So first we're going horizontally, so we want to start x equal to 0. And then we keep going until we hit our line that's in terms of another variable, which is y is equal to x. We want this as x equals 0 and then x equals something else, so therefore this is x equal to y, same idea. Out here, now we're just starting from 0 and going to 1. Can't separate this because you have a bound in terms of y, so not very nice. But yeah. Alright, let's go ahead and integrate the inside, and this is nice because this is just a constant in the x world, so you just multiply in and x. So you get 0 to 1, and then here you get x times your square root of 1 plus y squared. Bounds first. So going from 0 to y. 0 to y, and then dy. Notice that if you plugged in 0, this zeroes out the entire integrand, which is zeroes out the entire integral, which means this evaluates to 0. Now you just have to plug in y. So you're integrating from 0 to 1 of y times root of 1 plus y squared. And yes, it indeed did fix the integral for us to be nicer to integrate, because now you can make a u substitution, y dy is the differential if you let u equal to the inside right there. So let u equal to 1 plus y squared. Du would therefore be 2y dy. Notice here you have a y dy, you don't have the 2, so let's get rid of the 2 on the right-hand side by dividing 2 on both sides. 1/2 du is equal to y dy. All right. So yeah, 1/2 is multiplicative. Let's take it to the outside like that. And then we have our integral and then the bounds, right? You want u bounds, not y bounds. So plug 0 into here. 1 plus 0 squared is 1 plus 0, which is 1. So u is equal to, the lower bound is just 1. Upper bound, plug in 1 into here. 1 squared is 1. 1 plus 1 is 2. So u is equal to 2. And then in here, y dy is just your 1/2 du. So we'll take care of that in a second. Now you just have root of, well, in here is just u. So you have root u, which is also u to the 1/2. So like that. And we can really quickly find the antiderivative. So we have the 1/2 that stays outside, and then we have u to the, add 1 to the power, you get 3/2, and then divide by 3/2, multiplying by its reciprocal 2/3. The 2's cancel. So, and evaluate from 1 to 2. So let's do the evaluation real quickly. We get the 1/3 stays on the outside, and then in here you have, in here you have, u to the 3/2, right? And evaluate it at these bounds. So let's put down 2 to the 3/2, which is, if you think about it, it's just 2 root 2. Because you can separate this into u to the 1 times u to the 1/2. So u to the 1 is just 2, and then u to the 1/2 is just root 2. Subtract off. This evaluated at 1. 1 to the any power is just 1, so you just get 1. And then your last step, I would say, yeah, let's distribute this in. So you get 2 root 2 over 3. And then you have the minus 1, and then now over 3. Box your final answer, because you're done with number 99. Okay, that's number 99. Almost done. 2 more, including our bonus and our last one. So, yeah, let's keep going, keep pushing. We're almost done. Number 100. And also need to flip the page. Uh-oh. Double integral, again, of course. Double integral over region R, with integrand being square root of x squared plus y squared dA. So here, you're probably hoping for polar coordinates, right? Since this entire thing is just an R. Okay, so if you want polar coordinates, well, let me show you the region you're integrating over so far, and we'll see how it goes. You're integrating, well, the region you're integrating over is the area bounded between y equals x and y is equal to x squared. How do you do this? Well, I mean, you could definitely set this up traditionally, right? Let's draw it out and see what it looks like. Looks like this. And then you have your x squared, which looks like that, right? So you're integrating over this region right here. So you can see it is possible, since you can have both bounds on the inside being in terms of, well, x and x squared, right? So you're integrating from, say, well, you start down here, you get y is equal to x squared, up to y is equal to x. Well, you can also do it the other way around, but either way, yeah. And then your x value on the outside is just from where they intersect, which is x is equal to 1, and then x is equal to 0, right? So that's cool and all, and that means you'll be able to integrate this. However, notice that if you wanted to integrate this using Cartesian coordinates, trig sub, and it's really, really, really nasty, so don't do that. Okay, well, what about the polar coordinates we mentioned earlier? How do we do that? I don't think we can. Can we? Well, let's give it a shot. Let's just try polar coordinates, because I'm going to tell you that we can, and then we'll see how we can do it. So, you got the double integral. Determine the bounds later. This is probably gonna be the most difficult part. I'll write these further apart. Okay, well, let's write down our substitution first. Let x equal to r cosine theta, y is equal to r sine theta, dA is dx dy, dy dx, doesn't matter, it's just r dr d theta by the Jacobian. Alright. Here, x squared plus y squared is r squared, root of r squared is r. You have to multiply in another r from the differential, so your integrand is just r squared, and then you have your d theta. Oh, okay. What about, well, let me label these real quick. What about your radius bounds, right? Okay, so if you think about it, I think theta is easier to do since we're starting from here, right? And then we're turning, right? Up to here, and then up to here, and then up to here, and up to here. And then all the way up until you eventually land on this line, y is equal to x. And this has, well, you turn 45 degrees up, which is pi over 4. So you start at 0, go to pi over 4 in terms of your theta. What about the radius? Well, notice that the radius, if you start here, it's always traced along, well, the distance between here and x squared. So we really want to, well, let's do it like, let's say this, right? It's always going along this line right here. This is always what your radius is tracing, right? So let's just find what the radius is by, well, substituting our trig sub in. No, not trig sub, well, our polar coordinates in. Y here is just r sine theta, and then x is r cosine theta, and all squared. So here we just need to isolate r because, well, this and that are equivalent, and r, we know, is just encapsulated by this equation right here. So let's just isolate r, and then we get our, yeah, we get it in terms of our theta. And that's what we are looking for, because in this inner integral, we want them in terms of theta, because our outer integral is in terms of theta too. So, yeah. Ooh, all right. In here, let's draw more implication symbols. If you distribute in the square, this becomes this, r squared cosine squared, right? So, to be able to isolate r, well, let's first divide an r on both sides, right? Because currently what we have is like a repeated solution. So if we just divide one r on both sides, it's still accounted for. Well, kind of, but let me just say that's valid, and we can do that. On the left side, you're left with sine. On the right side, you're left with only one r and then one. Well, the cosine is still squared. So now to get the r by itself, just divide both sides by cosine. You get sine theta. And I'm going to write it like this. So we're dividing one cosine theta here, and then another cosine theta here, right? That's just dividing by cosine squared. Cosine times cosine is cosine squared. And on the right side, you're left with r. And I'll tell you why we did this is because 1 over cosine is secant theta, and then sine over cosine is tangent theta. So we get that the radius is always just secant theta, tangent theta, right? Believe it or not. Because that's how you express x squared in terms of y is equal to x squared in terms of radius. So we're going from radius, well, we know the upper bound, right? We're always like pushed up against the x squared, which is just secant theta, tangent theta. What about the lower bound? Well, if you think about it, we're starting at a point, so the radius is going to be 0. So we're going from 0 to that. So we can't split it apart since we have a bound in terms of theta, so we just got to integrate. Outer bound stays the same, 0 to pi over 4. Inside, you get 1/3, which I'm going to bring outside, and then r cubed. Evaluate from 0 to secant theta, tangent theta, and then with respect to theta. This is 0, 0 cubed is 0, integrating 0 is 0, so this 0 goes to 0. So what you're really doing is just plugging in secant theta, tangent theta into this r. Alright, and from here, what you see is you can get 0, well, 1/3 stays on the outside, and then you have pi over 4, and then you have secant tangent all cubed. You can distribute in the cube, and you get secant cubed, and then tangent cubed. And then you still have your d theta sitting on the outside. All right, from here, if you take out one secant and one tangent from each of these, let me think. Can you do it the other way? No, you can't. Probably not. So yeah, these are both to the odd powers. So if you take out one secant and one tangent each, you first have, well, the differential if you made a change of variables where u is equal to secant, right? Because your differential is now secant theta tangent theta d theta. So let's do that. In here, you get 0 to pi over 4. You get your secant, but now it's squared since you took out one secant. And you also have a tangent squared. However, we want to write everything in here in terms of secant because we already have our differential played out for us. We just took out a secant tangent d theta. So we want to write a tangent squared in terms of secant. So a tangent squared is just, well, secant squared minus 1. So let's just replace it with that. And then don't forget our secant theta tangent theta d theta. And now we can make a u substitution. Let u equal to secant theta. Du would be differentiating both sides. You get the derivative secant theta is secant theta tangent theta d theta. Okay. In here, well, let's move this up here actually. So the 1/3 stays on the outside. You have your integral. And now these are in terms of theta. We want them in terms of u, since our new differential is going to be du. So we want to find the secant of 0. That would just be our lower bound. Secant of 0 is 1 over cosine of 0. Cosine of 0 is 1, so 1 over cosine of 0 is just 1 over 1. 1 over 1 is 1. So our lower bound is 1. Upper bound, plug in pi over 4. Secant of pi over 4 is 1 over cosine of pi over 4. Cosine of pi over 4 is root 2 over 2, so you have 1 over root 2 over 2. Multiply 2 on both the top and the bottom. Well, so right now we're here, right? And this entire thing is underneath at 1. Multiply both the 2 on the top and the bottom, you get 2 over root 2, which reduces down. Since you can express this 2 as root 2 times root 2, these two cancel, you just have a root 2 left. So the top, your upper bound is root 2. Okay, that's your bounds done, and now you can just do the inside. Let's distribute it out. Secant squared times, well, secant is u, so you have u squared times u squared. So that's your first term, which is u to the 4th. And then don't forget you're subtracting u squared times 1, which is just simply u squared. And then the secant theta tangent theta d theta is just replaced with your du. All right, you're almost done. So from here, we can simply integrate. So I'm going to do this over here. 1/3 stays on the outside. In here, the u to the 4 becomes 1/5 u to the 5th. All right, and then you're subtracting off, integrating u squared. You get 1/3 u cubed. Don't forget you're evaluating from bounds 1 to bound root 2. Okay. Notice that at 1, well, actually no, that's not true. So let's just do this manually. Let's distribute in this 1/3. So 1/3 times 1/5 is 1 over 15, right? And then, well, u to the 5th, I guess. Minus 1/3 times 1/3 is 1/9, u cubed. And then, of course, all of this still evaluated at your same bounds, 1 to root 2. And now we can do it. So, yeah, okay. So let's evaluate this function at root 2 first. So in this parentheses. So we got 1 over 15 times root 2 to the 5th power minus 1 over 9 times root 2 to the 3rd power minus this function evaluated at 1. So u to the 5th is just, 1 to the 5th is just 1, so you just get this first term, and then 1 to the 3rd is just 1, so you get 1 over 15 minus 1 over 9. All right. Multiply. Okay. Okay, let's get rid of some of this work so we have more room to finish this off. We're almost there, by the way. Also, we gotta close this last parentheses. So, this first, inside here, root 2 to the 5th power, if you do the math mentally, you get 4 times root 2, right? Since root 2 to the 4th power is just 4, right? And then you still have root 2 multiplied on the side. So, in total, you get 4 root 2 over 15. Next, this term right here, you're subtracting root 2 to the 3rd. Well, it's just root 2 squared, which is 2. And then you have one more root 2, so it's 2 root 2. And it's over 9. And you're subtracting off, well, here, let's get a common denominator and combine those. So 1 over 15 is 3 over 45. 1 over 9 is 5 over 45. So you get 3 minus 5 all over 45. 3 minus 5 is negative 2. Negative 2 over 45. This negative cancels, so you get a positive 2 over 45. So we don't need these parentheses anymore. We're almost done. Let's just combine these like terms. They're almost, right? Let's multiply both the top and the bottom by 3. You would get the top becomes... Well, okay, first of all, you'd find a common denominator of 45. Right, so everything's going to have a common denominator of 45. On top, for this to become 45, you need to... For this to become 45, you need to multiply by 3, so you have a 12, right? So you have a 12 root 2 minus, you would need to multiply this by 5, so you minus 10 root 2. 12 root 2 minus 10 root 2 is 2 root 2. So this first guy becomes 2 root 2 over 45. And then here you just add 2. And that looks right. We are done. That's it for number 100. This is our last double integral for this entire video. And this should be the last question, right? And yeah, I mean, I'd say this is a pretty appropriate finale. You wouldn't expect to be able to easily integrate that. However, it's easier than we otherwise would have gotten it to be, right? By using polar coordinates in a way that's very unexpected, but still possible. And this is our final answer for this one. All right, let's do the bonus one. The bonus one is pretty interesting. All right, that's number 100. Let's do one more. Number 101 as our bonus, right? Number 101, we've got a single integral again. So we're integrating from 0 to 2, and then we've got x times root of x to the ln x times the cube root of x to the ln squared x times the fourth root of x to the ln cubed x dot dot dot. Alright, I'm just going to stop here because even though it would be cool to write this out all the way to infinity, it's not possible with the time we have. And integrating with respect to x, not 3, not 4, x. d4 would be very, very odd and confusing. Anyways, how would you even approach this? Well, notice that all the powers, well, it's like you have an x here, you have an x here, you have an x here, right? And then you can condense down what each of the powers are for x, right? For example, this x is just the first power. This x right here is to the ln x, but then you have a square root, so you're dividing the power by 2. So let's write this out. You're integrating from 0 to 2. This first x is just x to the 1. Then you multiply by x, this next one over here. You have the ln x in the numerator of the exponent, right? Since it's directly to the power of, and then the square root represents times 1/2. Like that. Then your next x over here is to the ln, and the ln is squared in the numerator. However, in the denominator you have, well, it's a cube root that's nested inside of a square root, so it's in total a 6th root. Which you can also express as 3 factorial, since if you notice this is 3 times 2 times 1. And then this is going to be 4 times 3 times 2 is 1 for this next x we have. So let's write down this next x. ln cubed is in your numerator of the exponent. In the denominator, you have 4 times 3 times 2 times 1, which is 4 factorial. So, and then this goes on forever, dx. And let's generalize this. So, right here, you can write this as, well, this is going to be 1 less power from the ln x, right? So, this is ln to the first, that means this is going to be ln to the 0th, and this is 4 factorial, 3 factorial, 2 factorial, this is 1 factorial. And this makes sense. Ln, anything to the 0 is just 1, right? So this is 1 over 1 factorial, which is 1. So this is just x to the 1, which is correct. So in fact, before we do this, let's write out what the generalized form would look like. So you get x to the, in the bottom, let's just call it n factorial. Notice that the power of the natural log is always 1 less than the value of n, right? So if this is 4, then the power of ln is going to be 3. If this is 3, power of ln is going to be 2. So it's always n minus 1. So this is ln x to the n minus 1. And then, of course, you can't just put down a dx. You have to put down dot, 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 since this is infinite, right? You can't just have n is equal to infinity and then stop there. This is infinite. Okay. Now what can we do from here? Well, we already, put it down, right? This is something that you would put as the, well, you can call it an argument in front of the infinite sum. So integration on the outside, 0 to 2, x in the base. But then now we can express this as an infinite sum, right? From n is equal to something to n is equal to infinity, because we're going on forever. And we just have this exact thing, because this represents what all the powers are for each of the vectors. ln x to the n minus 1 over n factorial. What are we starting at? Well, the first term, notice that this is 1 factorial. So, and our n is, well, exactly what we're trying to look for. So we start 1 and then go to 2 and then go to 3 and then go to n. So we start at n is equal to 1, since the first one has n being equal to 1. All right. Now this looks, well, barely usable. I mean, I'd rather not have this negative 1 here. So what this negative 1 is really trying to tell us is we're multiplying in, well, a 1 over ln x, right? Since this is just ln x to the negative 1, which is 1 over ln x, into all of these terms. 1 over ln x has nothing to do with n, so we can factor it out of the infinite summation, all of the terms in here, because it has nothing to do with n. Sorry, it's not varying with n. Move it to the outside. So we got 0 to 2, x to the 1 over ln x, and then we have our infinite summation from n is equal to 1 to infinity of ln x to the nth power over n factorial dx. What does this look suspiciously close to? Well, this is almost an exponential function. Almost, right? Exponential function, well, this thing, it matters less to us because this is the argument of the exponential function, right? No reminder, well, let me put this down. Exponential function, e to the x equals to the summation from two very important parts. N is equal to, we start at 0 to infinity, right? And then the second important part is what we have in here. So we have x to the n over n factorial. So this x is fine. We can always just place it in later. What we're missing right now is this n is equal to 1. Well, what can we do with that? Well, let's write it out first, right? Well, your first term, if you take n is equal to 0 outside, then you can start at n equals 1, right? But remember, we have to add on n is equal to 0. So let's evaluate n is equal to 0, and then we add on the rest. So we have n is equal to 1 to infinity, right? Because we took the 0th one out, so we no longer need to consider that. On the inside, we can just start at 1 instead of 0. It's just the term after evaluating at 0. So this becomes n is equal to 1 and still to infinity of x to the n over n factorial. Now, notice that the first term that we pulled out, where n is equal to 0, well, x to the 0 is just 1, over 0 factorial is just 1. So you just get 1 over 1, therefore this is just 1. E to the x is equal to this. And right here, we have almost e to the x, right? We just have an additional 1 here that we need to account for, right? There we have this. We don't have the 1. So let's isolate this by itself and then just replace it with whatever we find this is equal to. If you subtract 1 on both sides, you get that e to the x minus 1 would be equal to this infinite summation from n is equal to 1 to infinity of x to the n over n factorial. Let's go ahead and, well, notice that this is equal to that, right? And in fact, what you can do here is, if you wanted to replace x with ln x, you can do it on both sides. There's no differentials here. Well, this is discrete calculus, I guess, not continuous calculus. So there's no differential for you to work with. You can go ahead and directly replace x with whatever the hell you want, as long as both sides x is the same thing. So here, this is almost the same as that. It's just that x here is ln x. So let's replace x on both sides with ln x. Then you're done, because this is now identical to that. So you can just replace this entire guy with whatever it's equal to, and we determined it was e to the ln x minus 1. Notice that this just evaluates the x. So you can just do x minus 1. This whole thing right here, not including the 1 over ln x, just that, because see, it's identical to that. It's just x minus 1. So let's replace that. We got x to the 1 over ln x times x minus 1. And if you, okay, well, now what? Now what do we do? I'd rather not have a function both in the exponent and the base, so let's make this base e, and then just make x e to the ln x, because it's the same exact idea, right? We got e to the ln x times, and we can combine these into x minus 1 over ln x dx. Notice that this and that now cancel. The reduction is so nice, because all you're left with now is e to the x minus 1, right? And this minus 1 right here, you can kind of think about it as multiplying on a e to the negative 1. So let's take this to the outside, and then just integrate our e to the x, because e to the negative 1 is a constant, 1 over e. Here, this is exactly what that massive thing up there reduced to, through the power of infinite summations equaling e to the x with, well, a radius of convergence of, well, infinity. I think, I don't exactly remember, but it should be. We get this. It's so simple. So let's just do it. 1 over e stays outside. And then integrating e to the x, you get e to the x. Don't forget that you have to evaluate from 0 to 2. So let's just do this, right? So 1 over e. Evaluating e to the x at 2, you get e squared. And then you want to subtract off evaluating it at the other number. E to the 0 is just 1, so you just get that. Distribute this 1 over e in. 1 over e times e squared, you just divide out an e, right? So you get just simply e by itself. And then this minus sign stays. 1 over e times 1 is just 1 over e. And this, I think, is the best finale to end off with, because look at how satisfying that is. That enormous thing, that right there, just evaluated to e minus 1 over e. E is everywhere. It wants to appear everywhere, right? Alright, that's it. That's number 101. That's your 100 more integrals, along with a bonus one. Okay. That's it. It took me, 5 days to film? Because we finished finals and, well, I've got nothing on my hands, so why not do this, right? Alright. Maybe look forward to a 100 integrals part 3. I know this probably doesn't gather much interest, but I have fun making all this, so thank you.